Hello, 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 hello.
Fucking racist, Espada.
This is why I was wondering how can't
Yeah.
It still looks a little dark, so just adjust the ISO a little bit.
So the sun has not yet come over the horizon. When it does, it's going to be black for days.
Yeah, then you have to adjust it again.
Okay.
Or you can just close the curtains right now.
The colors seem decent.
Just close the color. Just close the curtains right now, and you'll be all good, I think.
If they don't, then you can adjust the white balance here. Yeah. It's on automatic, should be fine.
No, sorry, the blinds. I mean, curtains are fine.
Yeah, the curtains actually won't do much.
Yeah.
We have blinds?
Yes.
Yeah, it's the, well, it's this.
Do you see the chain on the side? I think that's the thingy.
Okay, beat me to it.
It's the glitter.
Let's go.
Should we choose the blackout one?
Sure, you can do that.
What is this? This is...
Which one? Oh, nobody knows how to use the characters of this one. This is trigger mode.
So who ran the cable?
No.
Who ran the cable?
And this one is that's manual.
Yeah?
What is this? Is that we can... Right now it's number...
I actually think these people are never organized.
Cable should always
Okay.
at the back of the table.
And ISO is just...
Or
Should like a machine here from 90.
Yeah.
Because every time someone says if the cables are running down here,
So if you go too fast,
there's a bounce
stop
over
here.
here.
No, yeah, that makes sense. I think, yeah, we just
I see.
went from like that route and then we skipped this from flowers and then this route was like,
Oh, so you did like it, okay.
yeah, we just set it up. And if you go to start, you have to like
Still have time, right?
Got it. So you basically want it as fast as possible without flickering, and then you adjust the ISO to keep that reference.
Actually, you want it as slow as possible without blurring.
Oh, okay.
ISO is what? What do you mean? The fake
Shutter speed.
Yeah, because if you go too fast, you lose depth for the colors.
Oh, I see. Okay.
You lose range.
Yeah.
Yeah. Like that.
Okay, so you actually need a moving subject.
Did you see
That's what it's for.
the Leroy Johnson blast figure? Yeah, this is fine.
Okay. But what if we go lower?
Well, you have a moving subject.
Okay, that is bad.
You know what's a moving subject in this game?
Right.
No, it's a screen.
What?
Yeah, it clearly is moving very fast.
The screen, and that's the reason why it was like giving you the flickering thing,
What?
right?
No.
No.
What's the screen
fine.
completely wrong?
No, because when I put a finger on that screen, it stopped flickering.
No.
What do you mean no?
It stopped flickering because it focused on your finger.
No, it was
does-
out. It was out. It was out.
It does focus on your finger.
It also fixed itself when we pointed it away from the screen.
Yeah, because the flickering is coming from the screen.
So, oh, was this on auto?
Okay. Also, I'm pretending like I don't care, but that sign is completely fine. It gives it very good.
It's a little goofy.
It's a little goofy. Did you see the Leroy Johnson last week?
What? Wait, how did you adjust from the different priority, from shutter priority to manual?
Oh, yo, can you start streaming and recording, please? I had that. When I tried to. Oh, good. Because when I tried.
no, I need another one. It's probably okay. It's full, I think. Okay. Do I need a microphone? I talked into this one, or what do we do? Should use that? Okay. If you are on the Zoom, yeah. Then the video audio will be what is recorded from your. But I'm currently not on a Zoom call. Should I be on a Zoom call? Okay. 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 You're recording from there. Okay, cool. Okay, good. Good. Okay, cool.
Good morning, everyone. Thanks for coming to the keynote here at the third iteration of the WITS workshop. Just one quick program note. In the second session, one of the talks, if you refresh the program, one of the talks, unfortunately, we won't be able to have today during the second session about type class specialization. So that's unfortunate, but I just wanted everyone to know about that. It is updated on the website. I'm thrilled to introduce Martin here. Martin Odersky is the lead of the Scala language and a professor at PFL, and is recently getting into looking at effects and capture tracking. So I think we're going to hear more about that right now. Great, thanks.
Thank you. So the title of my talk is Inside the Scala Capture Checker, but I thought that maybe quite a few of you don't really know what is this capture checking and why are we doing this. So I thought I would do sort of a spiral and first come from the outside and say why capture checking, then what is the type theoretic foundation, and then finally essentially how are we actually checking these types or these things. So let me start with that. So why capture checking? Well, it's a cool idea and it's new, but I mean I'm the designer of Scala, so I cared about it also from the Scala perspective. And why is that? Well, because the world has changed quite a bit from when Scala became first popular. When Scala became first popular, it was just one of a handful of the languages that occupied this Goldilocks spot, sort of almost all the way to Haskell, but not quite, and still retaining state, but being mostly functional and being fairly strongly typed, so having very precise types. Whereas the rest of the world was essentially lingering here either at the bottom, dynamically typed languages, which were sort of functional, such as Lisp and maybe Ruby, or statically typed languages with very small and primitive type systems, which is essentially Java, C#, Go, and all the rest over here. So that was in 2010. But the world has caught up quite a bit. So basically you can say everybody, all the rest, moved sort of towards that spot and fairly close to that spot actually, because if we look at what the situation today is that we have a lot of languages that, let me just go back, that essentially acquired lambdas, acquired Java, and recently acquired pattern matching. So they're getting all the functional features. I remember when we talked with the people at Sun in the 90s when we did pizza, they came back and said, well, you do generics, higher order functions, and pattern matching. We have higher order functions because we have inner classes, that's good enough. Pattern matching is not extensible, that's really bad. We just want your generics. And now Java has all of them. So they acquired everything. And a lot of other languages do the same, and there have been lots of new languages on the scene now that are also in this spot. So whether you look at TypeScript or Swift or Kotlin, They're all sort of fairly rich languages with lots of functional features, fairly elaborate type systems, and they are sort of crowding that space. Yeah, thank you. Okay, and then of course there's also Rust, which essentially goes much further in some of the dimensions of strong statics checking, in that they also check memory references. So the challenge is so you could say, well, Scala was in a sense successful with the other handful of languages. It dragged the whole industry to where they were. So everybody now has these features. And you can say, yes, imitation is really the highest form of flattery. But for the future, clearly Scala is no longer alone in its space. And I believe it's cleaner, simpler, more expressive than most of the others. But to what degree does that really matter? In industry, it doesn't seem to matter much. There's another challenge that was actually pre-seen by James Irie a long time ago in 2009 when he wrote this hilarious brief, incomplete, and mostly wrong history of programming languages. So it goes through all the languages. If you haven't seen it yet, then do look it up. It's really very funny. So it ends with this one. It says, a drunken Martin Odersky sees a Reese's peanut butter cup and featuring somebody's peanut butter getting on somebody else's chocolate and has an idea. He creates Scala, a language that unifies constructs from both object-oriented and functional languages. This pisses off both groups and each promptly declared jihad. That was a joke then. It turned out to be actually very true. What happened over the last 10 years in Java, that in Scala, a lot of that happened. There was quite a bit of very bitter fights between people who were in the purely functional programming camp and people who were in the more object-oriented camp, which was denigrated as just a better Java. So the question is, what should Scala become in the future? Should it maybe cede its current space that's thoroughly industrialized and put the emphasis on pure FP instead? And some people think it should do that. They call it a Haskelator jokingly, or monadic Scala, purely functional Scala. But what they really mean by that is that the imperative part of programming, which is always there, should essentially be staged. I don't really like the name pure functional programming. I like to call it staged imperative programming, because it means the effects happen at a later stage in a monad through an effect system. So what people like is, what some people propose is that we should become essentially I don't know, a redder Haskell or something like that. So something close to Haskell. I am not one in this camp, because I believe that if you look at the benefits of functional programming by and large in industry, then there's a diminishing curve. So it's not what promoters claim, that the purer you are, the better. In some domains, definitely, but averaged over the whole industry, I have my doubts. I think there is definitely, it goes very far, but then there's a plateau and maybe even a diminishing returns. We see that in Scala land, where we have lots of very ambitious purely functional projects, and I have the impression that the failure rate in these projects is higher than in the projects that are more pragmatic and have more a mix. So I don't know, you have to tell me. So that's also where, in a sense, Scala is to say we try to hit this plateau where essentially functional plays its strengths and without losing effectiveness. But so in these mostly functional languages, it's not just Scala, it's also OCaml, for instance, or F#, or, as I said, a lot of the industry is moving into that spot. There's a dilemma. So the dilemma is that you have to choose between when to use variables or effects and when to be purely functional. And the problem is, how do you ensure that this happens? You can do code reviews or things like that, but it's very hard. You feel uneasy. A manager wants to have assurances what the code does. And if you have vars lying around and everybody could use them willy-nilly, then bad things could happen in the code base. We've seen that in our own code bases, that there was a single stupid thing that somebody put a var in a place where they shouldn't have put it, and it meant that large parts of the compiler were not parallelizable because there was just a race and we didn't see it, and the var was in such a stupid place that nobody found it. So it was really ridiculous. So how do you ensure this doesn't happen? That's essentially a problem, and that's why many people flock towards purely functional solutions, because then they don't have to decide this problem. So Scala programmers generally really like their guardrails, and that means there's an uneasy choice. You can be simple and performant, no monads, no monad transformers and this thing, but you're unsafe. There's always this bad feeling to say, well, maybe my code is really doing bad things, launch the rockets or something. Or you can be safe and relatively complex and slow. So the problem here is that I think languages should encourage good code. So we use a particular programming language or type system to guide us towards writing better programs. That's the whole point. So ideally, a program that looks simple on the surface should also be safe and predictable. That's sort of what we want. But with effects in these predominantly but not purely functional languages, that's not the case. If you can use an effect, let me just mutate that variable over here. It can make your program shorter, but it would also probably make your program harder to reason about. So the problem is what looks nice and short on the surface is not necessarily a program that you want to write and that you want to reason about. So the functional answer to that, of course, so far was a staged architecture for effects, where the first stage is a purely functional program that describes a usually monadic computation, and the second stage is you execute the effects in the chosen monads. So it looks a little bit like this. So you have, essentially, this is your program, and then outside is the thing that gets managed by libraries, whether it's a single monad like Zio in Scala, or a stack of monads like Cat's effect. So they handle all these things, but they're outside your program. Your program is a first stage, purely functional program that essentially uses these things in a monad. Okay, so that was a solution. It is a solution that is very widely adopted in industry, so much so that people tell me I shouldn't work on effects or capabilities because that's the industrial solution that they will say in Scala. That's the proven thing. The problem with that is that compared to direct style programs that just use the effects, there's a fairly high notational overhead, in particular because monads don't really compose very well. So one typically has to do either higher order acrobatics, such as monad transformers, MTL, finally tagless, and all the freer monads and all the other inventions, or the other solution is one puts everything in a single monad, which can lead to over-provisioning. And Scala has both. So it has essentially one part of the functional community does that and is essentially criticized for being very, very complex and very hard to learn. And the other one does that, essentially has a single monad with 3 type parameters for environment, effect, and result. And everybody has to fit into that. 3 type parameters should be good enough for everyone. So the industry experience so far with this, I would say, has been mixed. So people are using that in big projects, but there's also a lot of backlash to say this is too complicated, and there has been quite a lot of sort of walk out to say people walk away from Scala and do Go or Kotlin or other languages just because they don't want to do this kind of stuff. So there has been quite a bad reaction. So the alternative would be to look at it from a different point of view and have a new approach to effects. So what we see here is essentially there's this tension between what our model lambda calculus does, it's pure, it's abstract, and what actual computers do. So computers are full of effects and resources and everything. And languages reflect that. So there are the low-level languages like C or C++, where essentially everything is a mutation and everything is a resource. So essentially I don't have any value that can be arbitrarily used. And then we have higher-level languages like Haskell or Scala and so on. But there's another dimension, and that's to what degree do I track effects and capabilities? And there, I think the answer is, with our current languages, not so much. So the functional languages just say, we want to have no effects, or as little as possible effects, or all effects in a monad. Whereas down here, the languages typically say, well, effects are just a way of life, we don't track them. Except, of course, Rust has done a big progress here that they have very refined tracking of memory effects. But Rust is, at its heart, even though it has lots of nice functional trappings with traits and type classes and everything, at its heart, it's an imperative language. You have to write a lot. Yes, functional languages need a garbage collector. I think that's an axiom. So the question is, if you go up here to the essentially more lambda calculus-like thing, what happens there? And a lot of research happens there, and some of that has actually found its way into practice. There's linear Haskell, the projects like Singularity, Mezzo, there was alias types, algebraic effects are very hot. But the question is, there's nothing really widely deployed as widely, let's say, as Rust is used in the industry. This is all sort of still very fledgling. And what we have here is another entry in this space, which is called Caprese. Caprese is a acronym for Capabilities for Resources and Effects, and that's a project that we have started last year, and that's going to take 5 years. It's a large SNF project, which we're working on this one. So I'm going to talk a little bit about that. So Caprese is about capabilities for resources and effects. The claim is that capabilities provide safe typing for both resources and effects. For us, capabilities are simply implicitly talked values. Capabilities are a very broad term. There are many type systems that sort of have some capability components, but for us, capabilities are really capabilities in the object capability sense. They are values in your program that you pass around. And we have a type system that keeps track of these capabilities, in particular, which capabilities are retained in closures and objects. So for us, the view is more like this. So you still have your mostly purely functional program, but you have all these other things that you can also access, but they're all mitigated by a capability. You need to hold a capability to get to the network or to get to the state or things like that. And these capabilities, they can have limited lifetime and other restrictions, which makes them resources. So ideally, with a system like that, we would arrive at a system where encapsulated effects are very easy to declare, but global effects are hard. The idea is that you should be able to use, let's say, a local loop or something like that, or a local resource. As long as this thing is local, as long as the effect is encapsulated, that's okay. The rest of the program will still see a clean API. On the other hand, a global effect, like a side effect to something that's universally accessible, is really bad. And what we would like to have is a system where that's really hard to type. And with capabilities, indeed, there's a good promise for that, because well, capabilities would have to thread through the whole program. If you need that, then somebody has to give you the capability, and that's going to be very expensive. So the more local the effects are, the easier a system with capability becomes. So that means we can hopefully soon get to a state where shorter and clearer programs also tend to be safe, and we trust the type checker to guide us to produce good code.
Are capabilities linear? Meaning need to be flipped? Can they be forked?
That depends on the policy you apply. So in the base system, they can be forked. But you could impose a linearity restriction, and we are looking at that right now. Yeah. So the capabilities compared to effect systems, there's some difference. That capability at their core is just a mechanism. There's nothing yet that says they are even used for an effect. They could be used for other things like information flow and things like that. So what our system does is it simply tracks which capabilities are retained. We don't really have any restrictions like with ownership systems where you say there are certain policies where you can't do certain things. With capabilities, is essentially everything is completely free. We just say, well, we have a type system that finds out what capabilities go where. And then afterwards, we can add various policies to enforce lifetimes, prevent data races, and so on. And that's essentially the fundamental difference between, let's say, ownership type systems approaches, which start with the policy and say, okay, so here's a policy, your program has to adhere to that, and that's a restriction of your program. Okay, so that was my first part. I want to then switch to the second part, which is written in a different system. Apologize for that, for talking about what the approach to capture checking is and what the capture checker actually does. Let me just get, okay. Okay, so we're talking about capabilities for resources and effects, and the challenge that we have is to be actually adoptable in a language like Scala. The notation needs to be really, really simple and intuitive. So there should be next to no overhead for introducing these things. And so what we were mostly looking at is simplicity of notation and not so much extreme expressiveness or essentially we were looking more at what properties we can express simply rather than this full set of properties that we also want to express. So resources and effects are both expressed as capabilities, and the capabilities are tracked in types. So just a quick reminder, what are resources? Resources are values that are available only with certain restrictions, such as lifetime, sharing, quantity. So examples are regions of memories, file handles, channels, database, network connections, and so on. And for us, effects is any aspect of the computation beyond the shapes of inputs and outputs that we want to track in types. So for instance, accessing state, throwing exceptions, doing I/O, suspending a computation, or using a continuation for control operations, and so on. So the problem with effects is that they are transitive, and that makes them a little bit different from other things in type systems. So if you have a calling chain and the final member of Fn has an effect like I/O or assignment or throwing exceptions, then that's indirectly also an effect of F1. Other types don't behave that way. Other types are more local. And the problem is if that graph, function graph, is dynamic, as it usually is when you have virtual calls or higher order functions, then it's hard to describe what the effects of F1 are. So that's the so-called effect polymorphism problem, and it's a problem that has been with effect systems since the beginning 30 years ago. Okay, so our approach is that we model effects with capabilities. So the following two we treat as equivalent. We say, okay, if we have here t throws e, a function, then clearly that's an effect. The function returns type t, and it might throw exception e. What we model that as instead is we say the function takes a capability, let's call it can throw e, and returns a t. So it's a function that we say it returns a t, nothing else, but to do that it needs the capability to also throw an exception. From a point of view of information, it comes down to the same thing. I mean, in both cases, you know that an exception e might be thrown.
Think of that as an argument to f.
It is an argument to f, yeah.
And a value argument.
Exactly, yeah. The using here means it's an implicit argument. The compiler will synthesize it when it sees that the function needs that thing and that capability is available in the environment of the call. So, but otherwise, it's just a function parameter, yeah. The thing is actually closer than it just philosophically. So there's a way to get from one to the other in 4 steps in Scala. So if you write t throws e, what that actually is, it's an infix type, so it throws te. So it's a type that has two components, the type that gets the t and the e, the exception. So that alias throws is actually an alias for what we call a context function type. So these are types that, function types that get applied automatically to the result. So it's can throw e to t automatically applied. So the parameter is synthesized at the point where the function is used. So that's what f then is, and this context function type translates into exactly the same thing. It translates into a function that takes this thing as a parameter and returns that thing as a type. So why is that important? Well, it's important because it means that I can actually synthesize and type abstract these implicit capability passing. I don't need to repeat that at every function definition. There's a way to define it once and maybe name that as a type and then use the type everywhere. So these things have been explained in a POPL paper 5 years ago, Simplicity, Foundations of and Applications of Implicit Function Types, 6 years ago already. Okay, so why should I bother? Why does that matter to go from functions, from effects to capabilities? Well, it matters for effect polymorphism, and the standard example of effect polymorphism is the map function here. So map, we would write it like this in Scala, so it's defined on lists, it takes a function from A to B, returns a list of B. So if I would have a hypothetical extension of Scala with traditional effects, then somehow I would have to add an effect parameter. So I would say, well, map now takes an effect, E, and it takes a function that returns a B and has this effect, and then the effect of map is also the same effect, E. Which might look okay, but really isn't, because map is just the simplest example of something that is absolutely pervasive. We have everywhere calls to higher order functions or virtual method dispatches, so it would mean that essentially everything we do gets these additional parameters, which then accumulate. So you would just get a sea of these effect parameters, and nobody wants to do that. So if you go to capabilities, then interestingly enough, this thing has exactly the same signature it had before. So it's, we say map takes a function from A to B and returns a list of B. So how can that be? I mean, there's something, yes, there's something. So it can be because for us now, the type A double arrow B is a type of impure functions that can capture any capability as a free variable. So function, that's a closure. It closes over the environment. The environment can contain capabilities. That's the idea. I'm going to show some more examples. So we now introduce a new arrow, the single arrow, for pure functions. So A arrow B says that's a function. It doesn't contain any capabilities, but the double arrow is a function that retains capabilities. So serendipitously, Scala always had this, the double arrow is a type of function, so that was a big point of deviation from, let's say, Haskell, but you could say, well, we have just reserved this thing for the pure functions, and it's still available. Okay, so let's see how these things work, and I just pick exceptions. It's not the best domain for effects, I think, but it's one everybody knows. So here we have an application of map. So let's set up the scene. So we have an exception too large. We have a function that throws this too large exception, just as well if my number gets too large, I throw the exception, and then we have a list of integers. I map the function over the list, and I do the sum, and that function might throw too large. If it throws too large, I catch it here, and I return another value, right? So the too large thing is, as we've seen, a capability. So if we translate the thing to capabilities, that's what we get. So the function now takes a capability, can throw too large, and it returns an int, otherwise nothing has changed. And I have to generate that capability, and that's done here. So the compiler will actually pass this capability to the function, and that's a mechanism that's inherent in the try, because the try catches the capability, catches the exception. There's a capability available that the compiler can pass at this local point. So what you see here is that the function that gets passed to map, it's this function here, right? And that function has a free variable, which is this can throw capability. So it retains this thing in its free variable, and that's why map doesn't have to know about it. Map applies the function. Whatever the function can do, map can do. So it's a different point of view to regard these things. So for us, then map is actually a pure function, because we say map itself doesn't have any effects. The code of map is pure. But of course, if you pass it something impure, that will be impure. So it's a different take from, let's say, the monadic systems. Okay, you say, this is great. I don't need to change my signature. I get effect polymorphism. Where's the catch? Well, there is a catch, and that is that this capability here that I have passed has limited lifetime. So it's only available as long as the try is executing. When the try exits, then there's nobody that can handle this exception anymore. Okay, so here's a way to trick the system into doing something bad. Now, instead of just writing xs.mapf, I write xs.iterator.mapf. So an iterator is essentially a delayed computation. So nothing happens here. And then outside the try, I write iterator.next. So that's the point when the function f will be applied, when I force the next value of the iterator. And of course, at that point, there will be no longer a handler for this exception. And what I get is an unhandled exception. So that's the catch. So if I do these things with capabilities, I need to control I need to know about the lifetime of capabilities, and I need to reflect that in the type system.
It's
So
kind of like laziness.
it's kind of, so iterator and lazy would be the same. So I could also return a closure here. That's, yeah, yes.
The implicit arguments that you have for capabilities, are they always the last arguments, or do you have sometimes need to eta expand to show the application?
That's a good point. So let's see. So here we have an eta expansion, right? We have f, and now we eta expand. And what we do with implicit arguments, which is very important that it happens that way, is we pass all implicit arguments into the eta expansion. So implicit arguments get passed at the point where essentially I form the closure, not later on. Yeah. If you want to pass them later on, you have to make them explicit. Yes.
So can that interact with, higher order functions? I mean, imagine I want to call this with, one function f that can throw too large and another function f that throws a different exception. So how would that?
That is handled by the map polymorphism. Map would gladly take any closure that throws any exception and just apply it. The type system, it's not reflected in that thing. So that's the beauty of it, that map works that way. Yeah.
If you pass this function, this sort of pure this function f to map, which is pure.
Yeah.
Map, let's say it wasn't map, but a function that called f many times.
Yeah.
Then the order in which it called it, the compiler might move that around, but
Yeah.
depending on the effects, that might change the semantics radically.
Why would the compiler move it around?
Oh, just because it's optimizing the code for map.
Ah,
for
right.
Wombat.
Yeah.
Let's call it Wombat, right?
Yeah.
And it just optimizes the code for Wombat.
Yeah.
Previously it called f of 3 and then f of 4, now it calls f of 4, then
Yeah,
f of 3.
yeah.
That would completely change the semantics if it captured an I/O capability.
True. Yeah.
So Wombat is not really a pure function, or it's not being given a pure function. How do you control?
Right.
How do you control what optimizations the compiler can do in this allegedly pure?
Okay. So we're not quite there yet. So what we are here is we have the capability system. We can track them, and we can gradually have more and more effects that we capture with capabilities. If you would say we capture all effects that the compiler cares about, then the compiler could just look and say, well, what capabilities get captured? If it's pure, then we're good, and if not, then I can't do these optimizations.
But this is when you're compiling map or
Right.
Wombat
Yeah.
function. And you don't know the callers. They're in different libraries, in 10 years' time. So
Okay.
you don't know the effects that are going to come with the closures that you're being passed.
Right. So you have to specialize then for one or the other. We are looking at that for async. That's a typical one where you say map could be called with a closure that suspends or with a closure that doesn't suspend, and that means map itself can be a suspension point or not. And the idea is that we would specialize the code based on the capabilities that we see in the type system passed to the closure. Because at the application point, you know whether your closure has possibly an async capability or not. That's the idea.
So functions are no longer truly polymorphic. They have to be specialized for their call signs.
Yeah, they're truly polymorphic in the source, but not for the compiler. The poor compiler, it's not so easy for the compiler.
This is an implementation meeting.
Exactly. Exactly. Okay, so So what we want to do is we want to track in a type which capabilities can be captured by its instances. So I have another example here, which doesn't use any compiler intrinsics. So it's a simple try with resources pattern. I have a function using log file. It takes a file output stream, and the way it works is I create a new one. I run the operation on the file that I have created. I close the file, and I return the result of the operation. And that also suffers from the same problem. The operation here might return a closure that accesses the file when the closure is further applied later on. But at that point, the file would already be closed, and essentially that would be an error that would happen. So to rule out these problematic cases, all we have to do is this little hat behind the file output stream. So what that declares is that the operation takes a file output stream, which is a capability, which we want to track. So the hat says this is essentially an arbitrary capability that needs to be tracked. And that would rule out the use like this, where I say, well, the operation takes an iterator, so it's delayed, and I write, so I would get something like this. I would say local reference f leaks into the outer capture set of the type parameter t of method using log file. It could probably be improved, so we should work on the error messages, but you get the gist what it does. So the type parameter using log file, it says, well, essentially what happens is that this capability that we passed inside somehow gets returned as a part of type T. So it gets instantiated here, and the system doesn't like that. But on the other hand, if we just wrote map instead of iterator of map, then the compiler would be happy with that. So the compiler knows about one versus the other, about safe versus unsafe usages here. Okay, so how do we do that from a type system point of view? So we have these capturing types, which is a type and a capture set of capabilities. So you ask, what is a capability? Well, a capability is just a parameter or local variable. So that in that sense, it's object capabilities. But if it was any parameter or local variable, the system would be far too verbose, because the free variables of a lambda are something that is very implementation dependent and can change from one point to the next. So we don't want to put these things in the types. The types would get too large, and they would change too often. So what we say, a capability is defined by having as its type a capturing type. It's a meta-circular thing. You're a capability if your type needs another capability to exist. So that means that there must be some capability that is essentially from which all others are derived, and indeed there is. It's called cap. So every capability gets its capability-ness or authority from some other more sweeping capability, which it captures, and there's a root capability from which ultimately all others are derived. And I believe that's sort of the type systematic account of the object capability model. And object capability model, as far as I know, it didn't really have a type system so far. I would claim that's essentially a natural type system for that. Okay, so let's make this a bit more concrete. So here we have a mini language, simply typed lambda calculus. The only difference is, since we're talking about capabilities, which are objects, which we want to have in types, this calculus needs to be dependent. So we need to be able to talk about terms in types, but it needs to be only mildly dependent in the form Scala already is. So we just need variable dependencies or path dependencies. We don't need full terms in these types. We just need the references. Okay, so our language then is, so there are lambdas, applications, there are lets, because the other thing I should say, the whole thing is in monadic normal form. What we want to do is that in an application, it's variable to variable. So I assume there's this expansion to monadic normal form. The types are top or the dependent function type. So functions now can depend on their parameters. So these things are the pure types or the shape types. To go to the full types, I need a shape type or a shape type and a capture set. So the full type has a shape type and a capture set. And a capture set is just a set of references. So function type is variable dependent. Terms are in ANF, or rather monadic normal form, because the lets can be nested. And I have the abbreviation that a shape type and an empty capture set, I just write that as the shape type itself.
Martin, were arrows and, I don't know, lists or something in this?
Which one?
Arrows.
Oh, that's the one. Dependent function type. Yeah, that's my arrow.
And what about list of T? Or
Yeah, that thing is just yeah. So we also have type constructors and things like that. But in that mini formalization, we have just the functions. Okay. Everything is church encoded. So we can show that the Böhm church encoding of lists is actually typable in this system. So polymorphically typable. Okay, so we have a subtyping discipline over this, and subtyping is influenced by a subcapturing relation over capture sets. So there's a relation between capture sets, and this subtyping rule says that if two shape types are in the subtyping relation and the capture sets are in the subcapturing relation, then the full types are in the subtyping relation. So, and here smaller capture sets would give us subtypes. So essentially the type that can do anything is a supertype of the type that can do nothing, that is pure. And pure types with empty capture sets are subtypes of capturing types that capture anything. So the subcapturing thing is essentially subset plus one additional rule, which is very important. It's this one here. This one says if X is declared in the environment to be a shape type and a capture set, then the singleton set X is subcaptures that capture set. So this gives us specialization. I have this variable X, which essentially has its underlying capture set. It gives it the authority is C, and then we say X is better than C. So, for instance, you could say C is a file system, and X is a logger that needs a file system, so it captures the file system in its thing. So then we say the logger singleton capability is actually a true sub-capture of the file system. It gives you restricted access, but it, of course, in order to work, it needs the full access. But you, as a user, if you just hold on to X, you don't have the full access. Okay. So if we use this rule and we instantiated C to empty set, then it shows that, well, if X is a pure shape type, so if it's pure, then the capture set X is a subset of the empty capture set. So that means we can drop all things that are pure from our capture sets. All references that are pure don't show up in these things because of the instantiation of this rule. Okay, so that means we can greatly prune the set of variables that we track. So if we look then at the simple typing system, that's what it is. So it's simply type lambda calculus plus subtyping. And the new parts are in gray, so they're not that many. So I think probably the most important one is here right up at the var rule, where we say, well, if we have a variable that is this type, then a reference to this variable. So the variable is a capability because it has a capture set. I'm now assuming it's not empty. Then the capability of the reference itself is X. I say, well, the capability has the underlying set, so let's type it with X. If C is empty, then it would be again X, but then we know that the capture set X is a subset of the empty set, so it comes down to the same thing. Okay, so then the next rule is for the lambdas, where we say if we look here at a lambda, then we look at the free variables of the body T here, and we subtract X, and that's the capture set of the closure. Pruned with all variables that are pure, because we've already seen that we can drop them. So that gives us the true variables that the closure will hang on to.
T should be a variable in your system.
Sorry?
T was a variable in your system.
T is the body of the lambda. Yeah, sorry, yeah.
But when you say pruned, this doesn't say anything about pruning.
No, the pruning was on the slide before, that where I said, because, well, okay, so we have subsumption. If a type is a subtype of another type, then it has this other type. And by this rule here, we know that if something is like that, then the set X is a subset of the empty set. So that means we can safely drop it from the capture sets via subsumption. Yeah. Okay. Right. So that was, so conversely, the application rule says, well, if my function has a capture set, then that's now discarded. The function gets applied, nobody hangs on to this anymore. So here the capture set goes away. And finally, we have the standard let rule, dependent let rule. So that means that the variable x here can't appear in T2, which is usual because, well, of course, it's local here. But that would mean, well, the question is, well, what if it does? What if it does appear in the type? Then you have to work with subsumption to actually lift the type to a capture set that doesn't get mentioned locally. And that we do essentially with the subcapturing rule here. Where is it? Yeah, that one here. And we say, well, let's say x is the forbidden local variable. And we say, well, x is actually a subcapture of C, the set it's declared with. So hopefully C will not contain any local variables, so we can pick C instead. So that's essentially this avoidance step here. Okay, so that was the simply typed system, and it's really not very much to it. What we have further is we have extended that to a generic system, so it's essentially an extension of F sub. And there were some challenges in making it generic. So the full system is in our paper that's appeared at Toplas and was presented here. But the observation for how to get generic systems is worth a second look. So to add generics to the system, you have essentially two choices. You can say, well, either X, the type variables, are full types. So full types, the type X can range over types that capture things or don't capture things. Or you say X is just a pure type. Type variables have to be pure. And then you need some other way to essentially get a full type into that to essentially make it work so that X can range over things that also capture things. So what we do here is we have this box. We say boxes are things that encapsulate things that can capture things and make them pure. So that means type variables can be instantiated with box capturing types. And it turns out that this choice gives us much smaller capture sets and doesn't lose much in expressiveness. So we picked that for the capture calculus. So if we look at boxing, then boxing really, there's a well-known precedent that for boxing we know with type erasure. So when we have type erasure and we have primitive types and we pass them into a generic context, they need to be boxed. They need to be essentially turned into a generic representation. So that happens when primitive type is passed to a generic type variable. We need to box it, and when the generic type variable is instantiated to a primitive type, we unbox it. So we know that from generics. And in our capability system, that's very similar. So only that boxing doesn't create a box on the heap. It hides all captures, returning a pure type, and unboxing re-instantiates the captures in the environment. And what that leads to is a very nice property which I call capture tunneling. So with boxes, captures get masked on construction. So here we have a type constructor. It's simpler than list. It's just cell. So it takes an element, and it's generic. It has a type parameter T and an element of type T. Now we have a capability that essentially captures another capability C. And the question is, if I form cell of A, what happens? So what happens when I expand this? Well, I have to infer the type parameter of cell, so that would be A hat C, but it's not A hat C because I say, well, I go into a generic representation here, so I have to box it. So there's this type, what I wrote box in the syntax here, I just write it in ASCII with box. And the same happens in the actual argument that I pass. That argument was an A, but it gets passed to something which is now essentially a box, so I have to box that also. So here's a term level box where I box the type variable, and here is essentially box. Here means, you can say, generic representation, pure representation. What's important is where there's no capture set. So there's no capture set here on the outside, on cell. And that's very important because it means I can actually put these things into data structures and forget about them where they are. I don't need to track every capture that a data structure refers to. So that's the upside of it. On the other hand, when I access things, so let's say I have a function f and is a lambda, and it takes the b and it returns the element of the b. So what happens there is that the type of the element, which is box AC, has to be unboxed on access. It's this unboxed thing here. And what that leads to is that the function f has this type here. So it has type unit to A capturing C, but the function itself also captures C, because in the function I had to unbox, I had to access the capability. So now it's basically this environment that produces the closure that needed the capability because it needed the capability to access the box with the key. So what we see is essentially in a different system, we would expect the capability to see here on construction, where we drop it. But what we do is here on access, it pops out again. So that's this idea of capture tunneling, where we hide things on construction and reveal them on decomposition. Ralph?
So if I think of the capability as a value, does that mean that kind of the capability value is passed as another argument to f and then gets kind of reattached with the a when that is returned?
Yeah, you could see it that way, but of course that's not the mechanic. The mechanic, it's in the environment of the closure. So it's just that the accounting is as if this value sort of traveled.
Right, but it's in f, it's not in b.
It's
so b kind of loses the capability value, and then need to reprovide it when I access its field.
right, yeah, you can see it that way. Yeah. Okay, so captures tunnel through from construction to decomposition. So you could say, well, this looks all rather hairy. Fortunately, boxes can be inferred. What the program actually would look like with full types is like this. So there's no box unbox. It's essentially exactly the same as for primitive types and erasure. We know when we need to box and when we can unbox. So all these things happen under the covers. Of course, all these types can be inferred as well, but I just gave you the full types here without the boxes. So essentially, the rules are all type arguments are boxed. Expressions of capturing types passed to instances of type variables get boxed here, and expressions of boxed instances of type variables gets unboxed on access. So if B has this type, then B.lm would get unboxed. And what this unboxed means, it has no runtime semantics. It's essentially just an accounting thing, as we have seen here previously, that it means if you have an unbox here, then the environment, which is essentially the closure here, gets charged with that capability to say that environment now accesses that capability. So essentially that's where it pops out. That's the only effect, you could say, that boxing and unboxing has.
Could this whole slide be polymorphic in C?
Well,
here presumably your C is some fixed.
yeah.
But could it be polymorphic in C?
Yeah, sure.
So I just add a C parameter to cell.
Yeah, you could do that, yeah.
Cell square bracket C comma T.
Yeah.
And then everything.
Yeah. Oh, no, it's not a type parameter. It's a term parameter. These things are terms. But I can pass them around, and I have a term-dependent language. I can reason about it.
Cell of T, and then I have a C.
Yeah, exactly. Yeah.
But implicitly, using C.
You can. That's just the convenience. You can pass it explicitly or implicitly. There's no difference from the type system point of view. Okay, so that brings me to the capture checker. I see I'm actually quite advanced in time already, so I'm going to speed up a little bit. So the task of the capture checker is to recheck a Scala program in a type system where capabilities are tracked and compute all these capture sets. If a capture set is explicitly typed given, then we say that's what it is. But for all the inferred types, we have to produce the capture set component. And the capture checking is, in a sense, similar to borrow checking in Rust. The two are implemented as additional compiler passes for us and also for the borrow checker. So if we look at the Scala compiler in the large, so there's a front end, there's a middle end with 85 mini phases, but they're all very small and they're fused into about 13 phases, about 15,000 lines of code, and somewhere in this pipeline there's a capture checker that happens, that does these things. And the capture checking is a separate phase. The reason why is, well, it's currently optional, so you can turn it on or off. So you have an import, a special import language experimental capture checking. If you have that in your source, it will be capture checked, otherwise not. It takes time, so it's about as fast as the typer. So that means it's significant for things. So if you don't need it, you don't want to run it. And also, of course, there's a separation of concerns. They're both complex pieces of code, typer and capture checker. And the inference algorithms are different. For the typer, we use local type inference, whereas for the capture checker, it's a form of global global inference that we use here. Okay, so in fact, the compiler pipeline, in the compiler pipeline, the capture checker is split into two phases, which we call setup and check captures. So setup prepares types of all definitions for capture checking, and check captures does the actual checks. So before and after checking these capture checking types, if you write them, they're treated as annotated types. So this is an annotation, these are arguments, and the Scala compiler generally, it just ignores annotated types. So whatever happens, that's just information that gets ignored. So it means before and after capture checking, nobody knows about these capturing types. It's only during capture checking that they get instantiated. So what the setup phase does is it takes these types, if it finds a type with retains annotation, which is explicitly given, then it converts it to a capturing type, and the capturing type has the underlying type parent, it has a capture set, and it knows whether it's boxed or not. So it has this boxing information. It adds box status to capturing types, also explicitly given if they appear in arguments, so they get a box. And for all the inferred types, it decorates them with capture set variables. So let's say you have a type previously, let's say a type argument that was inferred to be list of C. Then what the setup phase would do is it would say, well, yeah, that's actually boxed because it's a type argument, so let's add a box. And then it would say, well, the C here, that's a C capturing something that because the type was inferred and I haven't looked at the capture set so far. So let's add a type variable here. And then the whole thing, the list, let's say it doesn't know that lists are pure, that could also capture something, so let's add a type variable here. So on every level of the type, we add fresh capture set variables. Sorry, not type variables, capture set variables, of course. Okay, so then what we do is we essentially run another type checker, but the type checkers are slightly different. So the first type checker, of course, does a lot of type inference stuff, type inference, implicit search, overloading resolution, adaptation to the expected type, and so on. So that's our main typing function. It takes an untyped tree, an expected type, a context, and it returns a type tree. So that's what the front-end typer does. The capture checker is slightly different. It takes now a type tree, that's the type that was previously typed, an expected type as before, a context, and it just returns a type because capture checking doesn't transform the trees. It's just a check. The trees remain the same. It doesn't have a runtime significance here. Okay, and what it needs to do, it needs to infer these capture sets, and it needs to essentially simulate the box-unbox operations because they influence the capture sets in the environment. Okay, just for a quick thing, these are the kind of trees that we see. There are more trees than Haskell, but not terrible. It's still manageable. It's about 25 trees or something like that. So ident selects this, super, type apply, literal. So you see the sort of the type of shape. It's essentially a simple language that has objects and functions and the basics. And then the other thing which is important for the type checker are the map. So basically what the type checker does is it has subtype checks, of course, and it has a bunch of maps that it applies to types. And these maps are basically all homomorphisms that sort of get overridden selectively at some points. And they're all type maps with this definition. So there's a type map, it's a trait, has an apply method, goes from type to types, and there's essentially a pre-configured thing where for every case there's the standard case where we just go homomorphically into the arguments, and you can override that if you want. So some important type maps are substitutions. We need to deal with those. as seen from, which is specific for objects. We need to compute the types of a class member as seen from a prefix. And then the last one is avoidance, which I have shown you already with the let, that we need to sometimes compute types that don't refer to certain variables. We need to find the least supertype of these things. Okay, and furthermore, the application points. Yeah, I'm gonna quickly go. Okay, let's see what we can do. Yeah, so I have to skip that. So essentially, okay, let me just go to the conclusion. Yeah, that's all right. Okay, so summaries. I'm sorry I couldn't get to this part. Ask me afterwards. I can maybe fill in some of the things. So what the capture set that does is it decorates inferred types with capture set variables. It rechecks the program with the usual typing rules, which generates subcapturing constraints on the capture sets. It solves the constraints incrementally using propagation. So for any set, essentially it knows which references are known to be in the set at that point and what the supersets are. And the most tricky aspect is to handle these type maps, because type maps are essentially unidirectional, and we have to know that what happens. So let me just give you to give you a taste. So the hard part is, so we know B is f of A and f is a type map, and then we also know that B has a new element B. So the question is, what does that mean for the element A? So we get a subtyping constraint, and we have to find an assignment of elements to all these capture sets that makes that true. So we have to find some things in A so that this that this relation can hold. So if f of B is B, that has a simple solution. It's just B. But if it doesn't, then there's a problem. So what we do in this case is we say, well, we don't know what we can put into the A to make this true. So let's make the C bigger. Let's look at the underlying type of the B and try again. And in the end, that will terminate, because at the end, everybody ends up at the universal capability, and all maps map to that. But it's not complete. But in practice, it seems to work fine. Okay, so that was the type maps, and we have to infer the box-unbox operations. So far, we have checked some parts of the Dotty compiler itself with the goal of arena allocation. We have capture-checked most of the standard library, including the collections, frameworks, and futures. And we are working on a new stack of direct style continuation-based concurrency and I/O, which is capture-checked on top of that. So in practice, the annotation overhead is very reasonable. That's the goal we set out to. So to show you how reasonable, I have here the lists in the collection library with a selection of typical operations. And the only thing that I have had to add is these two little hats here, which say for flat map and concat, this iterable once thing here, that it could actually have an effect. I can append something to a list that as I traverse it has an effect, and that's okay. So I added these two arrows here to say they can have an effect. But if we go to something which is lazy, like iterator, then it's slightly different. So now map returns an iterator, and that iterator retains two capabilities. One is the iterator itself that we have here, because map is lazy, and the other is the impure function f that is also part of the iterator. My point is, this is precisely the information that you want to know. It's not annoying. It's things that if I see an iterator, I really would like to know, yeah, what can it do when I call next? And that's precisely what it tells you. So in that sense, it's really nice. Okay, so to conclude, I think capture check capabilities have the potential to solve some long-standing problems, including effect polymorphisms, mixing sync and async code, combining manual allocation and GC, fearless concurrency, excluding data races, and they're particularly good in situations where we want to track only a few capabilities. So I wouldn't recommend them for something with Rust, because in Rust it's sort of universal for memories. But if I say most of my programs are purely functional and I have a garbage collector and I don't care about these values, but at some points I do want to essentially do arena allocation or something like that, or I want to care about effects, then these things are good because these things is essentially you only pay for what you use. So as long as it's purely functional, there's no overhead whatsoever. And otherwise, essentially, the wider you spread your capabilities, the more the annotation overhead increases. So here are some references to find out more. There's a paper. If you Google Scala 3 capture checking, it gives you the details in a doc page. And if you go to this directory repo, it's, you find the source code. Thank you, and I'm already out of time.
Thanks very much, Martin. Maybe we can have one quick question while the next speaker sets up. Is Andre here for the next talk?
Yes.
Okay. Ralph.
So I was wondering, there was a question earlier about linear capabilities. So if I understood correctly, that would also need retype checking all the other code, right? Because now if we have a closure with a double arrow which captures linear capability, you can no longer just duplicate that closure because you would be duplicating linear capability. Like that seems like a non-trivial extension, so even given that they have all
No, it's exactly non-trivial.
Okay.
So we have a system that's provisionally accepted as an on separation. That's going to fit okay. It's like a control of interference, but not yet linear.
Here. Press go. Okay. All right. Hello, everyone. Thanks for having me. I'm Andre. I am officially unaffiliated because you know the tiny text box when you register that says what you are? You can be tempted to put anything in there. Actually, you can't put anything in there. Someone just goes through a list and removes it if it's too outrageous. So I put unemployed here, and that's too obscene for POPL. And it's just a joke because PhD students are not technically employed by the universities in the UK. If you can't change this, please help your students. But I'm at Strathclyde with Bob Atke, who's right here, and I want to talk to you about syntax. And that is actually not true. This is a trick to make you come here because everyone loves to hate syntax. What I really want to convince you of is to think about syntax as a means to an end. At the end is programming language user experience. So whenever you're designing a programming language and you're talking about syntax, you might be tempted, or you might notice that in the discourse, you see people doing things like this, where they have an idea of what syntax means or what syntax is, and they're like, oh, I think syntax is too rigid, or sometimes it needs to be rigid, and those languages are good or bad because they do those things. And you could summarize them by putting features, then assign them a place in the spectrum. And then if you really want to go full Fillmore, you can say, well, everything this side is actually legible and everything this side is actually rubbish. The other way to see this is like the bike shedding argument, right? Where you just keep piling on colors until you end up with a complete incoherent mess that nobody can actually tell what is going on or why this argument for this specific part of the language is useful or isn't. So instead, what I want to have in mind in this discussion, and there's a mistake, but that's fine, is let's think about what is a compiler. I see a compiler as this infrastructure where we have an interface, we have something that users put things in, we have an internal state that is the thing that we usually work the most on, which is also the most important, and we have an output, which is what the compiler produces. In general, this is very binary, or this is either yes or no. And if it's no, sometimes there's a bit of information about why, but it's not always necessary. In reality, what I want to convince you of is that there are three pillars of design that I think we should keep in mind when we're talking about programming language design. And the first one that actually doesn't need to convince anyone is trust. I'm saying this because we're at WITS and we're writing compilers with dependent types, which probably means we like writing programs and we like writing proofs about those programs. And a big part of this is to be able to trust that the internal state of the compiler or that the types do what we think they do. And what I identify in this previous picture is that
trust is about this interaction between what we've put in and what we get out. So if we put in types, if they're correct, or if our program is correct, then we get a good response. And if we get a good response, we can believe it, right? This is another way of saying we want, in general, it's a good idea to have a sound type system. Like we can believe it, we can trust it, and it's going to do something that we expect. But there is another aspect of trusting a programming language or trusting a system like this that has an input and output. And for this, I'm going to take an example that's been in the news recently. Can you trust the output of a frozen UI? So this is a quote from one of the articles. A post office operator would see the screen freeze, and then they would keep entering enter, and then the computer would do something, but it would not be reflected in the user interface. This is something that thankfully doesn't happen with compilers, but it does happen a little bit with things like text editors or like IDEs, where you're doing something, it's not quite working, so you just do a clean build, and then it's working. And what is the difference? Who knows? Cached files, you know, internal state, mutable state. Those things happen, and they do erode this concept of, can we trust the system? Another way of seeing this that's in the literature is the concept of Polak inconsistency, that can you believe, or can the compiler believe itself when it generates output? So if you give it a file, it parses it, compiles it, and then gives you some output. Does this output actually match what you've given it, or is it even valid syntax? And if it is it even looking like something that it's advertising? So you can have something that looks like a proof of false, or something that doesn't look like a proof of false, and actually is or isn't. So that's the first pillar of design that I want to keep in mind. The second one is diagnostics. And this one is a little bit harder to convince people that it's important, and it's a property of purely the output. So when you have a compiler, again, you have some input, some output, and whenever you get a result, if it's yes, you need to trust it, but if it's no, you also need to know what you're supposed to do in order to turn it into a yes. Again, I'm sure we've all written proofs and programs, and we ended up with a situation like this, where you get a type, and you give a goal, and you put your goal in your result, and it says, oh, my goal is A, and I have a function that returns A, and I just put it in, and it's not A, because there's some hidden state, there's some hidden parameters. It could be anything, right? That's an example of the outputs or the diagnostic being unsuitable for the usage of making actionable feedback. Another one that's very memed upon is C++ templates, where you just get a barrage of data of this is what's supposed to happen with this internal state, but we actually have no clue what we're supposed to look at. Where is the one function call that actually makes this internal state erroneous? So there is a spectrum. What I mean with those two examples, there is a spectrum between too much information that's unactionable and too little information it's also unactionable. You need to find a compiler diagnostic that makes errors actionable. And the third pillar of programming language design, I've called it self-evidence, but I don't think there's a very good word for this, but it's a property of the interface itself, like files you put in, text you enter, or maybe diagrams you draw. A very successful instance of this idea that you probably have heard of this is the Zen of Python, which is a very preachy text, but does, I think, succeed in saying that we need to care about this part of the experience. And the idea is basically that things that ought to look like they should work, and things that probably shouldn't be there, probably shouldn't be there. This is very tautological, and it's the hardest one to convince people to care about because, of course, we can't measure those things. Those are purely internal fuzzy feelings about text and syntax. There are other things, if you go to industry, that people with big words like to say. So we want to optimize review speed. We want the smallest diff possible. People who do Haskell love small diffs, for example. We had a very fast iteration time. If you're using Go, this is a big one. Developers are big into I don't want interruptions. I want to keep my flow state as long as possible. Those are, again, very hard things to describe and things to optimize for and to share. But if you go into other industry, the one that I found quite funny had a very good way of explaining this that was quite understood by lots of people is this idea of game feel and game development, that when you are prototyping something and you're testing it, it must feel good to everyone doing it, or you must at least not feel terrible, or identify things where it doesn't feel bad, and then either accept that those things are going to be bad, and or maybe think about a way of solving it. So that's the context in which I want to bring up the topic of syntax in programming languages, and specifically dependent types. And that is because I've encountered a problem, and I want to fix it. But not in the way that will reach a discussion that is exactly like a bike-shedding discussion where just people want to throw their preference and then not really think about those 3 pillars of design, which is experience, feedback, and surface syntax. So the problem that I want to solve, that I've encountered too many times, is also that probably lots of compiler engineers here have this problem where they only fix it whenever it happens to them, and then like, we need this to happen. This is a problem, well, this is a type that occurs in dependent types very often. You have a first argument that is the type of the thing that you're dealing with. You have a second one that's indexed over the first, and then it gives you an output. Could be anything. Could be a type, could be a constructor, etc. A very common example of this is sigmas, right? Give it a type, give it an index, and then that gives you a type. Here another one, pi. We're not breaking any grounds, right? This is normal everyday dependent programming life. Those happen all the time. The one that actually killed me when I was dealing with this is the type constructor, the data constructor for containers. It is exactly the same shape. It gives you a container. You don't have to know what's a container. You just need to know that those 3 things are in our everyday life, and we have no real way of dealing with them. That's not true. We have syntax. We have special syntax for pi. We have special syntax for sigmas. But we don't have special syntax for containers. And I don't think we should. But I also don't think we should deal with the problems I've encountered. So here's a very simple example. This is very basic Agda, where I'm writing a sigma here, and we have a program here that says that's the index over this type, and I mean, it's a legit program with the lambda and the return type. The problem is whenever you start nesting them, you completely lose the symmetry between what's on the left of the sigma, what's on the right of the sigma. And you have all those lambdas that, what are they doing in types? This is terrible. I showed you C++ templates before, but as dependently typed programmers, we are not immune from this problem. Our types are programs, and whenever we get a diagnostic from type A doesn't match type B could be a very big program, and we actually have the same problem as C++ in this context. Here's what I was going through in my life, which made me reconsider my choices, which is a operator on containers. And there are actually 3 terms in there, but they're all indexed, and they all have lambdas in them, and it's unreadable. So what is the solution? As I said, there already are solutions for pi and sigma. Turns out people have thought about this before me, and we have a solution in both Idris and Agda, which are the 2 languages I usually use. And those are arbitrary syntax blocks. They work the same way. Also, this is Idris 1, I want to say. Idris 2 does not have arbitrary syntax blocks, and I think it's a good thing, and we'll see why very soon. What they allow you to do is to say, whenever you encounter this piece of syntax, actually means that. Whenever you encounter this piece of syntax, actually means that. But whatever, you understand it. It means you can write sigmas this way, which is a lot more natural if you are used to mathematical notation. It also means that you don't need to put parentheses on the right side. You don't need to put, you don't need to add lambdas. The programs you're writing look a little bit more like you would expect from your everyday life of programming or looking at types or type systems. If you look at the complex example, you have, it's a little bit more complicated, but it's only complicated up to the point that the program itself is complicated. So you do actually recover this this symmetry between left and right, and inside here there's another left and right, and it's much easier to see what's going on. But remember the first part? The idea is not to only think about one of those pillars of design, but all 3 of them. And this solution only fixes the front-end part. We are not explaining how this makes the code more trustworthy, or not explaining how this makes compiler diagnostic better. You could argue, I think this is why I'm not going to talk about it right now, but you could argue that this makes code more trustworthy because it's easier to see, or rather it conforms to our social expectation of what a sigma type looks like, and this social conformance makes it a little bit more easy to convince other people that the two things that we're looking at are doing what we expect. So there is another problem, and that's diagnostics. If you don't import the right thing, or if you import or use the wrong syntax slightly incorrectly, you get errors that do not tell you what you're supposed to do. So in this case, for Agda, it just tells you the thing is not in scope. It's just not the right, not written the right way. Sorry, it's just not importing the right module. And this one is the same thing. It says I was hoping for a type signature. You did not give me a type signature, but it is in fact a type signature. So what is the solution I came up with? And that is something that is I've called a customizable binder syntax. And if you use the Camel, you're probably screeching right now because there's lots of binder things in Camel. I want to specify that this is specifically specifically inspired from this dependently typed structure of we have one type, another index, and then a return. Now, if you talk to people in the community and you say, I want a customizable binder syntax, the discussion usually goes like this. It's like this meme of this kid that goes to grocery shopping with their mother and that says, Mom, can we have customized binder syntax? And they're like, but we already have customized binder syntax. What are you talking about? And what customizable binder syntax is at home, it's do notation. Please do not do this. This is actual valid syntax. It does work. Do not. And I see Simon is, this is Idris code. You can do this in Idris. So what I've reached is this solution. Again, it's complicated, but my argument is it's only complicated as much as the program itself is complicated. So we have an operator here that works a bit like a pi type. So it has a binder on the left, and it has a program on the right. And here we have a sigma type that works, exactly like a binder, right? So you have a left bit here, and a right bit here. And you have another sigma type, you have a left bit here, and a right bit here. And then you can start deciphering what's going on. Sideways. This is a sigma type that works as a pair, right? So we're pattern matching on the left bit and the right bit, which puts X and F in the scope. And then we're using X and F in the right pipe of this binder, which is the data constructor for containers.
So this is not active,
this is
some proposed extension.
So this is my implementation of it in Idris.
Oh, so this is Idris code?
This actually working.
Okay.
But it's not in the compiler right now because people are, discussing about it. So the way it works is very simple, thankfully, because there is a very well-known desugaring that you can do to implement lit binders, and that is to write them as Lambda application. There's one more thing that we need to understand in order to implement this feature is that you can see this as applying the application function, flipping it to those two arguments. And this is exactly what I've implemented. So given an identifier, parentheses, a pattern, colon, an expression, and then another expression, you desugar this by applying the function from this identifier to those things. And the thing that's a little bit special is that the type of the lambda is informed by the type of the first argument, which I found quite neat. Does respect exactly what you would imagine doing. It works the same way for operators. So if you have on the left a pattern, a colon, an expression, an operator, and then another expression, this does desugar as applying the operator in its normal application, or in its application, its left to right application form, and then the lambda as an expression. I'm not saying like I am a genius and this is incredible. I'm just surprised that this does not exist yet, and all the solutions that we come up with are worse in the specific way that if you write this and you write it wrong like that, you get an actual good error message. You don't get, oh, this thing is not in scope, or I don't know what you meant. You get something that tells you what it is that you try to do, what it is that you should be doing, and what is their possible mistakes. So and specifically, it tells you this is the correct syntax. If this is not what you meant, you probably mean to fix the way you have defined the operator. And if this is not what you meant, you probably need to import the correct thing. And by the way, the things are in those files. And there is also explanation about how to use this. And the reason we're doing this, or the reason we're able to do this, is that unlike arbitrary syntax blocks, we're dealing with a fixed grammar in this language. Even though we have this feature of binders, we know what the file looks like every time. We don't have to guess or try to import other files to see what things are supposed to do. So now, of course, I would not do this if it was just for me, right? If it was just for my small use case of containers. So there are actually a lot of other use cases. The first one I think everyone will be excited about in this specific room is that for loops are back. This is a slight variant where the types are not dependent, but this is basically applicative for written in this syntax, which makes code look imperative. Well, imperative looking code look actually imperative, which is quite nice. Something that is very going to be also popular or unpopular, depends on who you are, is math syntax is there to stay. So you can write things like exist x of type p such that f, or for all x, blah, blah, blah. Or you can write the infix form for sigmas. Something that is specific to Idris 2 is that we have linearity, and we have an operator for linear functions, but it is not dependent because it is not built in. It is user-defined. Is there a way we can write a user-defined linear dependent arrow? And we can. And this is what I've come up with. So the dash at is the linear arrow, and the equal at is the dependent linear arrow. And then there are arguments about if you can allow overloads, et cetera, et cetera, et cetera. We're not there yet. The point is that we can do this, and that's a neat, useful feature. And if you're curious, this is the type signature for the function that replicates one element in a vector of n things. So it takes a linear natural number. It also takes n copies of x, and that it puts all those n copies inside a vector of like n, which is, yes. Sorry. Finally, something that is very common in non-dependently typed is DSLs. So I was working in this other dependently typed programming language, and I was writing the elementator for Sigma. And it's atrocious to write if you don't have a better syntax for this. So this is what you can do. And once the floodgates are open, you can do anything. I don't recommend you do this, but this is a data structure that I came up with recently. And it was writing lots of lambdas for the second case. And I realized, wait, I can't just use the feature, just read it. It's just easier. So to summarize, this is how we just usually build compilers, or we build any product. We find a problem, we identify the tools, and we test it, and then we're done, and then we start over. Again, when we talk about syntax, I feel like we skip a lot of those steps. Usually the problem is not really identified properly. We just say, I don't like the way it looks, which is not really useful whenever you have a big compiler with dependent types that's supposed to be correct. And that's supposed to be believable within a community of proving theorems. This feature, I mean, it's a desugaring step. It's nothing magical, but I think the best way to present it to this audience is to, given there are a lot of people who deal with compilers, think about the procedure in which they implement new features in their programming language and take more seriously this idea of both diagnostics and trust in the system. WITS are extending it because we're never done with work, so this is purely syntactic, but it would be nice if we had first-class access to binders. Let's say I have an X and Y. Can I just know actually how many binders I have? Can I move them around? Can I rebind things when I notice something is wrong? Can I use this to give even better feedback? I've done this for Idris. I don't know how I would do this for Agda. I don't know how you would mix this with syntax blocks. Please, if you know, tell me, or if you're interested, tell me. And in general, I'm also interested in finding out the way we're doing, or the way I've implemented this idea of can we trust the compiler, is that when you resugar code, you also have to take into account the fact that you have done one step of desugaring before, which means you need to redo it once you show it to the user. Is there a better way to deal with this rather than having ad hoc code every time? Is there a bigger theory of let's have the internal state be rendered in a way that is consistent with the way it's been given to us? That's the end. Thank you for your attention.
We have a few minutes for questions.
Thank you for saying that diagnoses are important. Yeah, I'm going to give a talk on that. But this is something about keep bothering me. In the diagram, the arrow to the output
Yes.
are bidirectional.
I said it's a mistake at the beginning. I was referring to this. I said there's a mistake here, and skip. Yeah, it's a double arrow. It should be a single arrow, but yeah.
So I might be missing something obvious about maybe the context or the way you're doing this, that this isn't an issue, but ordinarily when we're encoding things like syntax with binders in some kind of meta level, we don't want to use like the meta level function space, right? We don't want to use like functions because then we get, we can't faithfully represent the things that we're encoding. You can, if you can case analyze on your input, then that's not,
Right.
Correct. So do you have a similar concern here, or is that somehow not an issue?
It is an issue. This is why Edwin is working on the new core with case analysis inside lambdas. I'm just not dealing with this. That's my solution. But it is a identified problem, yes. Okay. But thankfully, it's unrelated to this, right? This problem existed before I've implemented that.
All right. Thank you.
Well, thanks very much, Andre. And we have a break now until 11 o'clock, so we'll see you back here then.
Yes.
Okay, before we get started, we're still sorting out some AV problems. But before we get started, I want to let you all know our second talk of the session is canceled. And to keep synchronized with all the parallel sessions, we're just going to have an extra break at 11:30 and come back here at what? How long are the? At noon. At noon for the third talk of the session. Okay? Okay. Just give us 1 second while we finish sorting out AV.
Sure.
Okay, I'm pleased to present second session of WITS. Artem will tell us about retrofitting null safety into Java. Please take it away.
And can I use the mic? Oh. Hello, hello. Just, yeah. 1, 2, 1, 2. All right. Hi all, my name is Artem. I work as a software engineer at Meta. And in this talk, I will tell you a bit about the work that we did to turn millions of lines of production unsafe Java code into beautiful null safe Java code. So I guess before I start, I would like to thank the program committee for the opportunity to speak here alongside such an amazing group of people. And when I did this talk internally a couple of weeks ago, I received a somewhat puzzling advice from my colleagues who are more familiar with the POPL audience. And they said, cut the technical details and just add industrial context. And I was like, all right, let's see how it goes. So let's get started. So when it comes to null pointers, there are kind of two perspectives. So perspective one is the runtime perspective, which is basically when you want to dereference a non-primitive value, you check it, whether it's null. If it's not great, you invoke a method or something. But if it is null, you get a null pointer exception. Your backend service crashes, your applications crash, and users are unhappy, with this experience. But from the developer's point of view, things are more complicated. So as a developer, you get all these questions like, can I get null here? Do I want to accept null, or maybe check for null, or assert that it's not null, stuff like that. And this is a lot of decision making just for kind of one dereference. And so if you multiply it by 1,000,000 times, that's just a lot of overhead. So basically, it's not having this implicit nullness is not very efficient, and it's not safe. So naturally, there's this question, there has to be a better way, right? And that's what we did internally. So basically, over the course of, let's say, 3 years, give or take, we migrated millions of lines of our production Java code to null-safe Java. We developed tools, deployed them at meta scale. We iterated on the analysis and got some really nice benefits. This is a work of many people, including my close collaborators, Ilya and Dmitry, but also of the extended null-safe team, which is hundreds of developers that actually drove the adoption of null safety within their teams and orgs. All right. So when it comes to the structure of this talk, there are 3 parts: inception, scaling, and hardening. And this is, it kind of reflects our own journey. And so I guess for me personally, hardening is the most interesting. That's where we had to teach our system to understand generics, to work with generics, to add contracts, to figure out how to produce comprehensible diagnostics, and so on and so forth. But let's start with inception. I'll have to skip a lot of context here, but 2 main pieces were that at that time it was known that null pointers are a problem, right? We also knew that something like an optional type, as you see Camel or Java or Rust, is really not a solution in Java because of this picture and some other problems with the optional. And lastly, Meta had a history of turning dynamically typed languages into statically typed languages. So after thinking for a little while, I came up with this project idea, which I very ambitiously called 0NP. I was very naive at the time. And so the idea was to take this unsafe default Java, like the code base, from this state into a state where it's all beautiful, null safe. And I mean, of course, when you talk about these massive code transformations, it's important to have some process in place. And so this process looks something like this. So we just, we fix a class, we make sure it is compliant with the checker, has 0 issues. We slap a null safe annotation on top of it. And then we enforce at, like CI time, that you cannot introduce any more errors in an already clean class, otherwise we will break your build. And so like you repeat this multiple times, and you get to something like 90%, right? And so like this had 2 very nice properties in a sense that it was like, we had a very clear progress metric. And we also had, the progress was monotonic. As soon as something is null safe, it stays null safe, right? And this plan may seem a little bit like this meme, but nevertheless, like this idea, I pitched it, it landed well, and like with a few collaborators, we started working on it. So to kind of do this, we had to change the vocabulary of types. So string now means non-nullable string, and nullable string means the default Java's nullable string. We also had non-null and unknown, but I will get to them later. We also really needed flow-sensitive typing, because all the code in Java is written with the, using these explicit control structures. So whatever type checker we come up with had to understand control flow very well. And flow-sensitive typing is not very common. There are few languages, relatively few, that actually do this. So it was not super obvious at the beginning, but luckily, this, as many other problems, can be solved with AI. And that's actually what we did. Of course, here I'm referring to the proper kind of AI. And so the idea was that, we just take the code, we turn it into a CFG where the control flow is explicit, we run our AI analysis on top of it, and this kind of gives us this flow sensitivity sort of for free. And also, as Kuzo showed in '97, types are just abstract interpretations, so this all kind of made total sense. So to the scaling part, here I will front load some of the industrial context that I mentioned before. So first of all, we had these constraints about scale. So right, it's a multi-million line code base, and that's just first-party code. When you had third-party, it's just mind-boggling. We had thousands of developers that are submitting changes every day. So, this is a blessing and a curse at the same time, because, in this code base, you can probably find all possible combinations of Java feature usage. So it really gave us a lot to work with. Then there was this constraint about timing and impact. We couldn't really disappear for 2 years to come up with this grand unified theory of nullness in Java. We really had to deliver the value incrementally and ship changes to production code from the get-go. And finally, we had to smoothly integrate into developers' workflow. And I would like to elaborate on the last point a little bit. So from the developer's perspective, they like to solve business problems, ship impact, and write good code, probably in this particular order. What they don't like is when things slow them down without a very clear benefit. So friction is a very important consideration for all of this. So what we actually had to do, we had to increase developers' velocity while allowing them to ship safer code. And so the type checker itself is a very important component. It's central in this whole thing, but it's not the whole thing. There are also many other components that had to be implemented, like CI integrations, CLI tools, ID integrations, tools to work with the user-defined models, and so on and so forth. And in particular, something like cloud build integrations took a little while to get it up and running, but in the end, we could kind of retype check the whole code base in something like 10 minutes, which was extremely helpful to iterate on the analysis and understand kind of the impact of our changes that we were when we were experimenting with type checker. So our starting point was Infer, which is a platform for static analysis. It does compositional, interprocedural, summary-based analysis. It has support for many languages, including Java. So at the time, there was this checker called Eradicate, which did a simple nullness analysis. And it was also intra-procedural, and so we wanted to stick with this just for the scaling and understandability point of view. And so the good thing about AI is that you can really dial in the complexity by choosing the right abstract domain. So like you can start with something as simple as this, where it's just either non-null or nullable. And that's what we actually started with. Kind of quickly, we had to extend it further with these other elements of the lattice, like null, bottom, and unknown, so that we can reason about feasible and infeasible paths and deal with legacy code. And so we actually learned a lot during the scaling phase, especially about how to run this giant code transformation so that you can actually start this transformation from anywhere in the code base, but also so that at each step the system is consistent. But this had not much to do with the actual kind of type system things. So I tried to sample 2 learnings that had to do something with the type systems. So the first one is about soundness. Very important. No questions about that. Before I see pitchforks, yes, very important for a type system to have soundness. But also, it adds a lot of friction if you just go to the extreme. So like in this example, let's say you null check the field, then you call a method on this field, but there is this method call in between. So if you want to be sound in Java, you would just reset whatever refinements you did at this program point. Because this method could reassign the value to a field. So this is bad, and this adds a lot of friction, and we couldn't really afford this. So what we did instead, we assumed that all Java methods are pure, which may be appealing to the Haskell programmers here, but it was also appealing to our developers because they didn't have the the kind of friction that they would have otherwise. And then there was this paper by people from Nullaway where they corroborated our own experience with this soundness and unsoundness, or how to strategically add unsoundness to the system so that it's still fine in the end.
I love the idea of a targeted unsound assumption.
Yes.
Great phrase.
Thank you. So the second thing I would like to mention is, so when you see this piece of code, and you see this null check, and bar here means non-nullable bar, you probably think, all right, so that's infeasible path. And the first instinct of compiler engineers when they see infeasible paths is assume that this is dead code. So let's just remove the dead code, which may actually be a pretty bad idea because there may be a bunch of callers that actually call this code with null value, and that's because the whole code base is in a flux, right? So this code may actually be undead. I guess like the more constructive way to deal with these situations is to instead, just change the signature if the rest of the method actually allows it, so that you turn this infeasible path into a feasible path, but also type check all these calls so they don't produce an error. So now I would like to switch to the hardening phase, which is basically where we started working with like hundreds of developers, like very closely with library authors and framework authors, so that they can improve the UX and safety of their frameworks. So at that point, about half of the code base was in this null safe state, half was still in flux. And also developers started writing more generic Java code, more sophisticated code. They wanted better guarantees. And we also started getting more Kotlin code with nullable generics. So at that point, it became clear that we kind of need to support the full extent of Java language features, including generics. And this way, null-safe was born. So we could not extend, it was difficult to extend infer to support the full generic Java type system. So we actually re-implemented this thing from scratch as a Java compiler plugin. Null-safe has a bunch of things, including a complementary object initialization analysis, but I will focus only on the type checking bits. So Java is actually a very large language. It has a lot of features and also intersections between features. So when you add, this explicit nullness, there are many details that you need to get right. And so here I would like to mention this project called JSpecify, which was kicked off in 2019 by Google and JetBrains, and then more companies joined in, including Meta. And it kind of, gets these details right. But just, from the implementer's point of view, that's how we extended our type system, from the simple nullness lattice to the full generic system where we just basically attach this nullness lattice to type components. So we have a new type system, like a type lattice in our generic null safe. And this allows us to actually properly type check generic Java. It works well, but there is one complication, and that's error messages can be really hard to follow. So you have this complex type system, you have flow sensitive typing. So when you have something like this, nullable string cannot be converted to a string, like even in this small snippet of code, it may take a while to figure out why exactly it happened to be, this particular error message, right? And if you show this error message to a busy developer, that's probably going to be their reaction. So we couldn't really do this. We had to do much better than this. And so we had to extend our abstract domain to this sort of type trees, where the structure of the tree sort of reflects the provenance of the type. So, for instance, when you have this getObject method call, you'd get a terminal type with a reference to this method call. When you have a instance of check, you would get a refined type that points to the underlying terminal type. And when the control flow joins here, you would get a joined type that points to its components. And so this allowed us to kind of produce nice error messages with a trace that points to the right place where things went wrong. And like in this small snippet, this is, again, probably not, the trace is just one line, and it's really easy to understand. But in a real production method of 300 lines, these traces can get longer, but also much more helpful than in this case. Now, when you go from this simple nullness to generic nullness, method calls become much more complicated, like handling method calls. So in here, I would like to talk about the constraint solving and contracts. So when it comes to constraint solving, that's your usual stuff. So you have generic method, you have your arguments, you generate constraints, you simplify them, and then you have a solution, and you instantiate your inference variables. So that's your regular stuff, nothing interesting here so far. But when it comes to, this particular snippet of code, with forward analysis, you would first infer the type of the right-hand side, and then you would see what the left-hand side is and whether they are compatible or not. So this means that we would generate this set of constraint, right? We would infer that T here is just equal to a bird. And this means that the right-hand side would be a list of birds, and a list of birds is not a subtype of a list of nullable bird, because Java generics are invariant. So this means we would reject this code, which is actually pretty terrible. So we had to do better than this. And this is actually a kind of a known technique. I think Pierce described it in '98 in one of his papers. But the idea is that we look at the assignment context, and we add some additional constraints here about the desired type that we want this whole thing to be. And so this way, when we solve the constraints, we get that T is a nullable bird, everything type checks. So previously, we would just solve these constraints a bit too early, and this way, we get the full context and a nice solution. Now I would like to switch to contracts. And contracts are funny because they are usually these helper methods that developers use a lot. And without understanding what these helper methods do, you can't really accept correct code. So with contracts, you accept more correct code, which means you have less friction for developers. And so examples of contracts would be something like getODefault, where if the default is not null, the result is also going to be not null. Here, you can probably rewrite this method as a generic method. But developers don't want to do this. They want to see this simple signature with a kind of this implicit contract attached to it. Another example, this checkState method that throws if the argument is false. And an example usage may look something like this, where this Boolean value is just a bunch of null checks. So after this succeeds, at the next program point, A, B, and C should be refined as non-nullable. So what we do here is, again, probably not surprising, we do set solving for contracts, we translate contracts into formulas, refinements are obtained from formulas fixed assignments, also known as backbone or frozen variables. And this worked both for the result and the arguments of these methods. So when it comes to fixed assignments, there are many ways to calculate fixed assignments. That's probably the easiest one, and that's what we started with. You just check that some formula is unset, which, again, like there are more efficient ways, but this also works, and it's very easy to implement. So just reflecting on the contracts and set solving in type inference, there are pros and cons, of course. So the pros are that this is a principled solution, and you can actually extend it. You can also apply the same set solving to, let's say, to reason about feasible and unfeasible paths with these type trees. So there are lots of applications. But like even for contracts, we had zero problems with it. It just worked, and even a baby set solver was performant enough. Yep, thank you. Because the formulas turned out to be rather small, at least in production. And so the initial version actually took just around a week to implement. So that was all very nice. The con is that when you first talk about it, it may sound like a crazy enterprise, but it actually turned out rather well. So now I would like to conclude with some discussion around reliability and productivity impact of these changes. And so here I have the numbers for our Instagram Android app. And so like when you see these columns for the alpha channel, beta channel, and production. So alpha channel is this pre-release version that is just enabled for a small fraction of users. Production is the current release that is enabled for billions of users. All right, so when we look at the alpha channel numbers, we see this like, significant drop, like 3 times less null pointer exceptions in the alpha channel. So this basically means that developers started making much less silly null pointer exceptions, like NPE mistakes, and spend less time fixing NPE mistakes that happen in production. So this is direct reflection of improved developer productivity. Now, when it comes to production, as I learned over the years, real-world reliability is a lot more complex than just the type safety of, let's say, the client code. So when we were working with teams, particular teams, on improving null safety of their parts of the code base, they reported numbers ranging from 35 to 80% reduction in the volume of NPEs. But like for the whole app, on average, we measured it at minus 27%, which actually is very substantial. If you slash a third of NPEs, you get many, many more users that are happy with the app and spend more time there. So overall, we were very happy with the results. But again, the real-world reliability is complex. You have also like all these sorts of interactions between systems. You have things like reflection, JNI, and whatnot. So that's, I would say, a different story. And I would like to conclude with an inspirational quote of mine. And that's the quote. We couldn't imagine how much work we would have to do to, reach our goal that we stated initially. But still, it was very rewarding. So, I'm very happy about what we achieved. So, thank you very much for your attention.
All right, we have time for questions.
I'm curious how this works with constructing new objects. Like Java objects are all born full of nulls, and the constructor has to try and fill in some or all of the fields with nulls. So how do you track what's null and what's not null, especially when there's methods being called from inside a constructor when the object is half built?
Yeah, so we have this initialization analysis that I mentioned before that is complementary. It's an interprocedural analysis, so we look into these methods that are called inside a constructor to see what they actually initialize. And I mean, of course, there are again like false positives in this analysis. Like there's a sound approach, I think, called freedom before commitment, which is type-based, but it adds a lot of annotations, and we couldn't do this. So we had to build our own kind of custom thing, which again, like for our use case, worked well, but you can construct like like, these examples where you either leak this or do something funny where it would break. But like overall, yeah, that's how we do it.
Hello. Very interesting talk.
Thank you.
I'd like to know, so null pointer exceptions have been a problem since forever, basically. I'm really interested to what do you think made this possible? Like, was it a change in Java or in your company? What do you think was the kind of the cause that you finally have to do this?
Right. I mean, that's a very good question, in a sense that no one actually asked for this, but everyone wanted it. So what we had to do is just to come up with a reasonable project that you could, again, like pitch and that the leadership would understand, and then just, burn down this chart of non-null safe things. But I would say it's mostly about the organizational aspects rather than the technology in particular.
Thank you.
When you're talking about undead code, right? That's that slide. I love the zombie illustration. So I could imagine that a function in existing code that tests for null might have two cases. It might be a situation in which null is really a perfectly legitimate argument and you're testing for it, or it might be that really null is very bad, but the programmer was programming defensively, right? So then you still have to leave that defensive test there, is because of there might be part of the code base you haven't converted, or because some of your targeted unsound assumptions were actually wrong in a particular case. Okay, so you want to leave it there. But nevertheless, the question is, when you're looking at the code with the if in it, does your system say, oh, you meant this to be non-nullable, I better check that? Or does it say, oh, you've got a test there, so null is just fine? Which of the two? Or do you rely on a human being to tell?
So we definitely rely on human beings to some extent, but also if there's an explicit null check, so let's say you have if A equals to null, even though the input type was not nullable, we would assume that inside this branch, it is null. So we trust the actual sort of behavior that it would be exhibited at runtime. It actually, it's make the whole thing a bit more complex, because when the control flow joins, if you just do it in a simple way, before you had a non-null A, then you refine it to null inside the branch, then control flow joins, you join non-null and null, you get a nullable. So the rest of the method gets poisoned by this decision, so we had to kind of, have some workarounds for this. But overall, yes, we tried really hard to, like when we see an explicit null check, we refine it as it would be at runtime.
James Noble, creative stuff. I was just going to say, but I guess the point here is you're actually working in a closed system.
Yes.
So really, you're just working on the Android app. So.
Or apps.
Or apps. Right, but all from the same company. So in the future, you expect all the code you're handling is going to pass not just the Java type checker, but also the non-null checker. So you won't have people, for example, who are writing against a public API, where you can't be sure that they are writing a null checker, and so even if you annotate your method argument with non-null, that will be observed by the client, but you don't have that case.
Yeah, I mean that's an important consideration for sure. So like on one hand, we when we consume this external third-party code, we enforce that developers should provide an explicit signature. So that's kind of this thing about user-defined models. When it comes to other people consuming our open source libraries, I mean, this is complicated, right? So they are annotated with, as we think, clear semantics. Whether they would like to respect it in their own apps, I mean, we're not really responsible for this. But there is definitely this, the JSpecify thing. It is this attempt to produce this kind of standard semantics for nulls in Java, so that open source libraries from Google can have these consistent annotations from Meta, from other kind of major players. I guess like one thing to mention here is that we implemented this solution because we could do it at the time. It was viable. Java itself would probably implement a different solution. It seems that they're, maybe like in 5-10 years, it probably will be something different, but time will tell.
Okay, because we're at 11:30 and a bunch of people have entered, I want to remind everyone that and inform everyone, the second talk of the session has been canceled. We had to cancel it. Sorry if you're here for that talk. But since we have a lot more questions, I'm going to keep going. And I'll remind you that the next talk of the session starts at noon. Simon still has to work on his slides. I've seen him.
So I really liked the description of error messages because when you have any sort of flow-sensitive typing or subtyping in particular, you soon stop being able to get away with pretending errors of a single location. You need at least, here's where the null came from, and here's where it went that wasn't allowed to go. And I'm wondering, do you have any idea how much value your users are getting out of the bit in the middle? Would they be happy with just the here's where it came from and here's where it went? Or are you producing the full trace of, and then it was assigned to this variable and then it went to here and to here and to here? And if so, is that bit in the middle very useful?
I think it is very useful. It's like going from very bad experience to okay experience. So like even having this would be, it would be great. But obviously, like as you have more things like, contracts and stuff like that do these refinements in a very weird way, having a more complex, like complete trace is kind of this next step to get from good to great experience.
Very cool.
Thank you.
You briefly mentioned JNI, and I see that your null safety system kind of reminds me of a refinement type system where you can say X such that X is not null. Is there some appetite or is there some plan to tackle interacting with native code? I see that this is right. I'll let you keep going on with that.
It's been floating for quite a few years. Maybe you should better ask my colleague Jules about this. Because that's something that we could potentially tackle with Infer because it's multilingual, right? So we can analyze both the Java and the C++ side of things and see whether, the contracts on the boundary holds. But we didn't get to it yet.
Hi, thanks for a very nice talk. And
thank you.
I have a question about the Instagram app, like the diagram. What's 100%? Maybe you said it. I'm sorry, I missed it. So what's the total thing? Is that the number of the total report or the number of?
So this is a relative percent of NPE crashes. So we take all the crashes and we see like what portion is caused by null pointer exceptions. So this is just percent. I cannot show the absolute numbers.
Okay.
So piggybacking off Simon's question about defensive programming versus, cases where null is legitimate.
Yeah.
It sort of seems like a gradual typing problem. Like I want to sort of specify that part of this is nullable, and then, like that change sort of flows through my program. And so maybe I just missed it, but in your description, so when I'm writing a function, as the developer, am I responsible for going and checking all of the call sites before I can delete my null handling branch, or sort of how does the change propagate through the code base?
Very good question. Yes. So if you want to make a breaking change, so let's say previously your return type was not null and now it's nullable, you will not be able to land your change unless you fix the callers. So that's like one of the benefits of this closed world ecosystem, where we can actually automate this to a large extent. Again, like it's not something that you would probably do manually, but you can either do it like in multiple steps or with the use of automation. But that's, again, people understand these sort of considerations. So if some API is used very frequently, again, like very conscious about the blast radius, so to say. And I briefly mentioned the what we learned about like how to make sure that the system is consistent, although you can start now saving from everywhere. So before we actually released it to the wild, what we did the analysis of the most used APIs, right? And then we made sure that these APIs were properly annotated. And this way we can try to mitigate the problem where at some point your system evolves in two different branches, where one thinks that it's not null, the other thinks it's nullable, and you cannot quite reconcile it.
Thanks. What with the whole tracing that you added to the type system and the set solving that you also added, what is the performance impact on type checking or on compilation?
Very good question. Very dependent on like how pathological your case is. Like usually the impact is not large, but I mean if you have like a generated piece of code with 2,000 lines of switches, may be problematic, yes. So we saw something like 10x worse than what you would, your Java would give you. But again,
any more questions? Okay, then let's thank our speaker one more time.
Thank you.
And we'll resume at noon, at 12 o'clock. Okay, let's get started. So, for the second and last talk of the session, I'd like to introduce Simon Peyton-Jones, who will tell us about typing application spines.
Okay, good. I need a microphone, but then I won't do that. Because otherwise people online won't hear. Okay, so I'm giving 2 talks today, and both are trying to distill folklore out of the literature, and particularly out of implementations, into a sort of digestible form that you can make use of in your type checkers. But we're a kind of sad collection of people who thinks that type checking and type inference is really cool, right? But we're all in a room together, so let's share the love. And so this would be nice if we asked questions and made comments as we went along. We will fit in 30 minutes somehow. But so in a sense, I'm not going to tell you anything new, but I'm going to try to extract lessons that I've gotten from 30 years of trying to write type inference algorithms for GHC in the hope that they may have some resonance for you. Okay, so this talk is about applications, type checking applications. What's more fundamental to functional programming than this? So here's the lovely typing rule that we all know and love, right? And it deals with binary applications. Just apply a function to an argument. And it's sort of simple and beautiful and elegant, and it deals nicely with currying, and it doesn't have any dots in it, all very nice, right? So, so I'm going to focus on this, this problem. I'm going to show you a few, whenever I show sort of typeset rules, they're coming mainly from this paper, readily available on my homepage, which kind of both has lots of typing rules, but also it has an implementation, executable implementation right there in the paper. So it's good, it's very concrete. So the first thing I want to cover is, because it's sort of a precursor for everything that goes on, is a bit about bidirectional type checking and higher rank types. Many of you will know this well. In fact, bidirectional type checking is such a piece of folklore and such a well-known idea that nobody is prepared to admit that they invented it. Neil was just telling me, he asked Thierry Coquin and Benjamin Pierce and John Reynolds. None of them would admit to inventing it, but terribly useful. So what's the problem? Well, if you look at this application here, what are we going to do when we type the application? The obvious thing to do is to say, find the type of the function and find the type of the argument to check they're compatible, right? Infer both. But that doesn't work very well when you've got a higher rank function like this. So here's f, which takes an argument that itself is a function type, whose argument itself is a polymorphic function. A little bit strange, but Haskell programmers are very strange people. They do this all the time. So in a call of f, right, I'm going to call f on a lambda, right? So this arrow type is going to be the type of f's argument, and I'm calling g at type int and type bool. So g had better be polymorphic, and we have enough clues to work that out, because we know that f is, we know the type of s argument. We can push that into the lambda, and so determine that g has this polytype for all a to a and core. Okay? Simple. I mean, everyone can do this in their heads, right? If it's obvious to us, it should be obvious to a type checker. So the very good, well-known idea is to use bidirectional type checking, which we tend to notate by saying, well, in some environment, this term t has type row, and this little delta can either be up arrow for inference or down arrow for checking. The idea is, which direction is the type flowing? Down arrow means that row is an input, right? I'm pushing it down into the term, and up arrow means that I should think of row as an output, that is, I infer the type of the term. So far, so good? Okay? Now, let's see, and that leads us to, like in this practical type inference paper, we actually have two type checking algorithms, one for inference and one for checking. And the inference one says, give me a term and I'll give you a type. So this TC is the type checking monad. I'll say a bit more about that later. And the checking one takes a term and a type and produces a, well, it just produces a, we just type check it in this monad. Okay? So how's it good? Easy enough. What are these row types? Well, so we'll have to be a bit careful with where the quantifiers are when we're playing this kind of game with higher rank types. So sigma types and phi types are going to be ones with quantifiers at the top. So here are the for-alls, right? So we can have an arbitrary number of for-alls, and then we end up in a row. And what happens when we get a row? Well, we can have arrows and lists and so forth. We can have monotypes that are just no quantifiers anywhere in a tau. So tau you should think of as being some arbitrary type but with no for-alls in it. Or it can be a type variable, a tau, or, yeah, okay, we good? You can ignore the kappa for now. Okay, so that's what rows are. So now we can answer this question about, how does bidirectional type checking play into this? Well, when we are looking at lambdas, we split into two rules, one for inference and one for checking. So for inference, what happens? We say, well, we don't know what type X has, so we're going to give it a monotype, right? Because we can infer monotypes. That's standard Hindley-Milner kind of type inference. So we'll just, out of thin air, this isn't an algorithm yet, we make up out of thin air tau, but we're allowed to make up taus, right? I'm not going to explain very much about that, because I think most of you will know. Out of thin air, we make up a tau. That will be, in implementation terms, a unification variable. But when we're checking, well, we know when we're pushing down a type, we've got the type of the argument, and moreover, it can be a sigma type with quantifiers at the top. So we can push that down into the term T with an auxiliary judgment that is going to end up scholemizing this sigma type. I haven't written that out explicitly. Okay? So the important thing is that some rules are sort of polymorphic in the direction, but lambda is definitely not. And that's the key to making these higher rank type play out. It's just one way in which bidirectional type checking is a win. Okay. Now, so instead of, let's see. So now in implementation terms, I said we split into these two, and that's a bit of a pity. All right, because it looks as if you write two whole algorithms, right? That wouldn't be terrible. And expr, the expressions of the language, that might be a large type. So we don't really want to duplicate all that. So a standard enough idea is to say, well, maybe we could save a lot of work when we are inferring, right? Maybe instead we could just make up a fresh type variable, a unification variable, and check that the term has that type. Okay, let me just say it once again to make sure you got it. When we want to infer the type of an expression, maybe we could cons up a fresh unification variable and check that the term has that type. And I've written out the code here. Make up alpha, a fresh unification variable, and call check. Easy enough, right? And so now TC infer is just a little wrapper around TC check who does all the heavy lifting. Okay. Now what's the problem with this? The problem with this is that these unification variables they are variables, I call them meta-type variables often because they are a variable that stands for a type that we don't yet know. So I'm getting a bit more algorithmic here. But key point, the type that we don't yet know must be a monotype. These types that we develop incrementally by unification are always monotypes. That's the rock to which I cling. Maybe you can do better, but that's a fundamental principle of GHC's thing. So here, therefore, I'd be checking that E has some monotype, so I couldn't possibly infer a polytype. I could never get this term, for example. I'm being a bit informal here. If I called infer on a term that had an explicitly annotated lambda, I'm jolly well expecting to get, as a result, that the type of that term is, for all AA to A2, bool, in this case. But I could never get that because that isn't the monotype, okay? So, problem, easy solution. And so here, this is a takeaway idea. I'm sure everybody implements this, right? But GHC certainly does and has done for 20 years. But it's a very good idea and it's a simple one. Just make your main type checker take not a type, but one of these expected things. And an expected thing is either I'm checking that you are that thing, or else I'm inferring, and now I'm going to have something that's very like a unification variable. Just a reference cell that I'm going to fill in. The idea is that TC, when he's given an infer, is going to fill in that reference with the inferred type. Simple enough. So it's very like a unification variable, but this guy can be filled in with a polytype. And that's not immediately obvious from what I've shown you so far, but it works out very smoothly and very fine. Okay, so it's just an idea that I suggest you take away. Very, very simple, easy to implement, works really well. Okay? Nobody is, oh yes, Garrett, thank you.
So is a TCRF different from a unification variable in that it's sort of, you're only matching, you're never unifying, you sort of how it flows?
No, how is this different from a unification variable? Principally that you could infer it with a polytype, right? But it's not a first-class thing. The only place this goes is in expected. It can be pushed down. It never lands up in the middle of a type or anything like that. No, no. It's just, think of it, it's like a var parameter to a Pascal procedure, right? It just says, by the way, when TC of infer blah has finished, blah should be filled in. That's the invariant, okay? So it's everybody must make sure that's the case. Now, there is a bit of fancy footwork when you come to things like case expressions. So here again, I'm being a bit informal. Supposing I call TC, the type checker, on a case expression, well, I'm going to end up checking that E1 has type R. Oh, I should have put infer R here, sorry. I'm going to check that T1, I need to infer the type of E1, and I need to infer the type of E2. So can they both update this funny reference thing with perhaps different sigma types? Oh. But in fact, this is easy to get around. We just, at the cost of making the type system less expressive, but that's fine, right? It's a type system we're defining. If there's a multi-branch case, we just insist that the result is a monotype, right? So operationally, the moment you try to update this thing, you find it already has a value, you say, okay, let's make it a monotype, which means unify it with a unification variable. It's easy. So there's a little bit of footwork there that I just don't want you to think it's trivial. You have to be a little careful here, but it all works out. Yeah, Richard.
I thought we did that ahead of time.
No, we don't do it ahead of time. In fact, as it turns out nowadays, it's sort of on the fly, for what it's worth. Maybe it'd be better to do it ahead of time. Now, okay, so where are we? Good. Okay, we're 10 minutes in, and so we have 20 minutes for the title of the talk. The title of the talk was about type checking application spines, right? So the first thing I want to do is to say, what is not good enough? So now we sort of got to the boundary of the practical type inference paper. In fact, I don't think this idea was in the practical type inference paper, so we got a little bit beyond there. But we still haven't got, no cigar yet. Why no cigar? So I'm going to show you 4 sort of inadequacies for what we got so far. One is error messages. Right? So if you've got something like this and you pass a Boolean as the second argument to F, really you'd like an error message to say, oh, you would like it to say that the second argument to F should be rather than the third, but otherwise you'd like an error message like this. But the danger is that if you don't pay some attention, you may just say, oh, I can't unify int with bool, go figure. Right? But to say, in the second argument or the third argument, we've got to have a notion of that there is an F at the head of this application and that we're in the second argument, right? So we used to have some ad hoc stuff for that, but this talk is about making it a bit more systematic. So that's number one. Number two is this. GHC these days has something called visible type application, which many languages have, right? And what's many, let's say, sort of statically typed sophisticated languages have. So what does that mean? Well, if I've got this function, polymorphic function reverse, I can call it just passing it, some list argument, but I can also explicitly give the type that instantiates the polymorphic variable A here. So this says, in this call of reverse, please instantiate A with int. So x's had better be an int. Now, what's the problem with that? Well, if you think about the binary application thing, when I infer the type of the function, what do I get? Let's look back. Where's my inference judgment? I infer the type of the function and I get a row. And does a row have quantifiers at the top? No. So how can I instantiate them? Right? And it's very reasonable because if I've got a function with some quantifiers and then some arguments, it might be we somehow need to get a sigma type back here. And one possibility is you could say, oh, well, fine. Look, if I have one of these at things, I'll just generalize the type. I know how to do that. But then you think, but it might be quantified over several type variables. And then in which order do you generalize them? So now you start tearing your hair out. GHC's story, in papers, I think it was your paper that first described this visible type application game, is just to say, no, we'll only do this when there is a visible function at the top, at the front, so we know its type. It was declared by the programmer, and we know the order of the quantifiers. So something about knowing the function at the front is going to play a role here. Okay? That was number two. Number three. Impredicative types. So here's a little cottage industry of papers about trying to figure out how we could instantiate reverse, a polymorphic function, at, but instantiating A, not with int, but with the type for all B, B arrow B. Whoa. Okay, because now, this argument here is a list of polymorphic functions, so I must instantiate A with this polytype. Okay? So how are we to do that? That's called impredicative instantiation. So Q, long sequences of many papers that try to do this, including, embarrassing to say, I think at least 3, which included me as a co-author, all of which turned out to be bad ideas. But finally, this one turns out to be a good idea. Now, how is it a good idea? Well, the idea is the way that quick look works is it takes a look at, if you look at this thing, you think, well, reverse applied to Wise. Wise has type, lister for all B, B arrow B. Guys, it's so obvious. So obvious. The only thing we can instantiate A with is this, right? If it's obvious to us, it ought to be obvious to a compiler. And the idea of this whole paper is to to formalize what it means to be obvious, right, to catch the obvious cases. So you could go read that paper. But that was the third reason. But it required us to know this sort of known type reverse at the front to figure out the instantiation. Yes, Didier.
To ask question during, or do you want to wait for the end?
So,
is it
ask question now.
When you say it's so obvious, you could instantiate YS as well. So I think you cheat when you say.
Wait. I'm saying that Wise, we know its type for some reason.
Yeah, but it can be. Oh, it's in the list.
It's somehow Wise is a term variable that happens to be in the environment, right? Maybe it has a declared type.
Okay, I missed the list because I read in Camel when I would just say.
Sorry about that. Okay, anyone else? This, by the way, is point 3. Joachim.
Right, so this row type, so suppose I'm checking like an if statement.
Go louder.
Yeah. So suppose I'm checking an if statement.
Yes.
And I pass in a variable that has this row type. So I get out of the then branch, I get that it should be an int, and then out of the else branch, I get that it should be a bool, right? But it's sort of while I'm checking the else branch, it's I try to update this reference, right? I find out it's a bool, so I throw an error message, and the error message says this variable should be an integer, right? When really what I meant was this if statement is not typable.
Right, so you're saying that in an example like this, you're backing up to an earlier slide, right? So in an example like this, well, I'm trying to, if E1 and E2 have different types, I don't really want to complain about E2 or about E1. I want to somehow complain about the whole thing. Yes. That's absolutely true, and I think so I've not put a lot of effort into trying to improve that error message. But I think this setup might make it more feasible, but I don't think we do a very good job there. I think today we'll just we'll complain about E2 for what it's worth. Sorry. We should do better.
So a few slides ago, you were telling us that it's a bad idea to try to pretend that the two cases of bidirectional type checking and inference are the same thing, because we can't encode type checking, this failure, we can't encode it as checking against a fresh variable.
Yes.
Because of this thing that the meta variables stand for monotypes.
Yes.
But now you're introducing a predicative instantiation, so.
Yes.
Does this idea start working again?
So the whole point of the quick look paper is to say we can get this behavior without having unification variables standing for polytypes. I'll give you a quick clue in a second about how that works, but that is the key payload of this paper.
Okay.
Yeah.
So
because the unification variables that flow around and live in the middle of the types and have a long lifetime and get solved incrementally, those are still monotypes. Making them be polytypes is something that people have tried really hard to do but never found a good way to do. Okay. What else? Good. This is good. Right. Into the bowels of type inference. Okay. Let's see. So, what was the last thing? Fourth point. Right? Fourth sort of trickiness about just dealing with binary applications only is when we come to a function like this. So, and this is, remember, Haskell is gradually pushing in the direction of, we have Agda envy and we have Idris envy. Right? We're driven by Richard and Stephanie. We're creeping towards dependently typed programming. And one of the things we want to creep towards is to say, well, in a function like this, for all a, this is a type class constraint, size they double arrow int. Well, since there is no a to the right-hand side of the double arrow, really every call of sizeof must specify the type at which we're instantiating sizeof, right? So every call of sizeof would have to go sizeof at blah, right? And it would be quite nice to make that explicitly. So we'd like to give sizeof the type for all a, and in Haskell now we're notating this for all a arrow rather than for all a dot. And the for all a arrow means that every call must look like sizeof, and then you just give a type, no @ sign, and it's compulsory to give a type, right? It's not optional. Because if you leave this out, the complaint would be obscure, be something about ambiguous sized a constraint. It's all very obscure. As this, it's compulsory. Yeah? But now you've got functions with different shaped quantifiers, right? And so that's going to make this binary instantiation, the binary application game, fall apart as well, for what it's worth. So it's 4 things. So 4 little straws in the wind. So the very simple solution. So finally, the payload of the talk is something that which is very easy to understand and intuitive, but just we fought against for ages because binary application just seems like, so simple, so elegant. But once you do this one thing, everything else becomes easy. And then you're, okay, so what's the one thing? Well, it's simply to treat applications as a whole. So what do we mean? An expression is, well, it can be a lambda. I've left out let and case and all the other many case. Or it can be an application. And what do I mean by an application? Some head h applied to 1 or more arguments. Well, actually 0 or more arguments. N is just bigger. So even variables show up in this production. And what's a head h? A head h can either be just a simple variable, that is the function at the head, or it can be an expression with a type signature, an explicit user-supplied type signature, or it can be, well, an arbitrary expression, but preferably not itself, that this guy should not really be an application, because otherwise you could have had a longer h here. So you could make the syntax a bit more complicated to formalize this, but I've just put not an application here, right? So this E is not going to be one of these h guys. Okay? They're pretty simple. That's the syntax of expressions. And once you've got that syntax of expressions, now we can say, well, in the common case, very commonly, in like 99% of all applications, the h thing turns out to be just a variable. There's a function at the head of most application chains. And when it is a variable, we know its polytype. It's in the type environment. Because remember, gamma has bindings of variables to their polytypes with all their quantifiers, gloriously decorating them, right? This, expression with sigma, that's just a kind of, what's the word? It's not common to see expression : type applied to things, but it's kind of simple and uniform to put it there because, again, this expression, we know the polytype of its type, right? Namely, sigma itself. That's easy. But then we can bail out. If the h is some arbitrary other expression, say a case expression, then we could just give up and say, fine, we'll just do what we did before, but we won't get fancy polytypes out of it. We'll just get a row. Okay? But this is not very common, and I don't think many programmers, nobody's ever complained that they don't get some fancy polytype out of this that can then be impredicatively instantiated, right? It's just not what people are worrying about. Okay? So far so good? It's very simple, really. So now, once you've got that idea, how can we, beg your pardon?
No, I want to ask a question.
Oh,
Not as a session chair, as an audience
member.
member.
7 minutes.
No, sorry. Sorry, I was just looking at this case expression, and you just mentioned how in GHC you're moving more and more towards dependent types. Mm-hmm. And I'm thinking that actually this pattern is very common in dependent types, where the dependent type of the case is quite different than the types of the branches.
Oh, okay. So if you want,
I wonder if you thought of that.
No, if you want the dependent, so if you really want to write this, and you want it to have some, sophisticated type that gets informed, then you will have to put a type signature after it, right? Or give it a name and give that a type signature, one or the other. But what you won't get out of the system that I'm describing, at least, is it'll just sort of magically combine the strange polytypes out of here and no. So, sorry. Okay. Yeah. But there's an escape hatch that doesn't seem too unreasonable. Okay, anyone else? Okay, so then, but I want to stress this is not just an implementation technique. This affects what programs are typable, right? So we've got to write typing judgments for it. So this is the typing judgment for applications. So let me just walk through it, because this is this does have a little bit of technical content and is worth grappling with a bit. But once you sort of internalize the way application works, everything else becomes easy. It's so good. So how do we type check? And this is going to work for any delta, right? Up and down, checking and inference. An application applied to 0 or more arguments. Well, the first thing we're going to do is to infer the type of the head thing. Now, H. How do we do that? Well, here it is. Very simple judgment, actually. Because, notice it returns a sigma. Ooh, the power of saying sigma rather than rho. Right? As, you know, tell this to an ordinary room of people and they say, yeah, whatever, right? But to you guys, you think, oh, yes. Okay, so why does it? Well, remember, there are only 3 forms of H. If it's a variable, just look it up in the environment, and we got a sigma there, because gamma contains bindings of variables to their polytypes. If it's an expression with a type signature, we got the sigma right there in the term. The user wrote it. And if it's anything else, well, just bail out into ordinary old inference for E, and then you only get a row back. But every row is a sigma, just with no quantifiers. Okay? So H is very simple. Now what else happens? Oh, so now we know the type of the function. Now we have to instantiate that type, because it's got some fools floating about, and we instantiate it. So this is a complicated judgment. It says you should think of input is the sigma type of the function, and the list of arguments pi, and I'm going to get out the instantiated argument types phi, and the final result row at the end of, in the corner, right? So this guy is just saying, take sigma and strip off his fools and take his arrows apart, as many arrows as are necessary to satisfy the pi, and give me back 1 phi for each of the pi's and a result, okay? Now then, now we come back to your question about unification variables and so forth. So this says instantiate the function with fresh instantiation variables. So instantiation variables have a very short life, right? Instantiation variables are born here, right? And then at this point, this is a funny line. What does this say? It says take the free instantiation variables of phi and rho, and take the free instantiation variables here, and for each of them choose a monotype. Now, why is there this fancy footwork with instantiation variables? It's because the quick look algorithm for impredicative instantiation is actually going to figure out polymorphic instantiations for some of these instantiation variables. But so while you're not thinking about quick look, you can just imagine inventing taus here, but there's just a little intermediate step. So this rule is built to scale to quick look. Right, and once we got that, now we can check, down arrow, that each of the arguments pi, oh dear, E is the value arguments. Each of the argument has the type that you expected, that you got out of here. And finally, you have to check that the result type row here matches up with row R. Easy, right? So then all of the fancy footwork occurs in the instantiation judgment. What does it do? Well, it takes this type and these arguments, and it gives you the argument types phi and the result type rho, and it takes care of all these required arguments and visible. There's quite a lot of moving parts in this guy, but all of the things that I told you were tricky are all embodied in this instantiation judgment that I'm not going to work out. I'm just showing you this slide to say, look, it fits on one page, all right? And if I just take one example, what's this? This is a visible type application. So we got a fool, and the first argument is an explicit sigma. I could have written at sigma there. It's an explicit user-supplied type argument. Well, then what do? Well, of course, I just instantiate that A with this sigma. That was what the visible type application said. Easy, right? Boom. So you can read the paper. This is all in the quick look paper. But it scales nicely, that's the point. So what I want to say by way of finishing then, that treating function applications as a whole is a piece of folklore that many of us in this room will have found our way to implementing it. But it's very, very valuable. It exploits the wildly common case of having a function at the head. It degrades nicely in other cases. And moreover, as I discovered 5 minutes before giving the talk, by appeal to higher authority, it is in fact not just a random hack for a poor, sad compiler writer, but actually a deeply principled process. So I appeal to Neil now to explain what I mean by that.
Okay, when you look at polarized type theories and give them a syntax, then you discover first that n-array functions are actually very natural, which is why we have these top-level clausal definitions, and sort of dually to that, like. When you have a negative type or a function type, you naturally want to supply it with a whole list of arguments at once, and the semantics of this works out very nicely with call by push value as well. So a good paper to look at this is Arnaud Spivak's A Dissection of L.
Okay, thank you. You may say that, I couldn't possibly comment, but I'm very glad to hear that this egregious hack actually has a deep logical foundations. But really the conclusion is, the takeaway is, look, you should just do this, right? It's a straight win on every dimension. And anybody who's writing a type checker should have a good reason for not doing this, I think. Good, thank you.
No, thank you. Thank you, speaker. Okay, we're about out of time, so I'll ask for maybe one or two short, quick questions.
Yeah, so you didn't talk about how to implement the error reporting when we have a type error. I assume it's easy. Is it as easy as I think it is?
Yeah, the error behavior is pretty much as easy as you think it is, because like in this vector down arrow thing, we're making n calls to TC check, if you like. But we know for each of the n's, we know what n is. So you can sort of say, I'm now in the nth argument. That's really all. There's nothing more sophisticated than that.
So this was supposed to be the last question, but actually I have two. One is that the multi-application, if you let bound only some of the arguments, then now you have to do the application in 2 steps. So you're not stable by a transformation that let bound some arguments. This is more.
Oh, you mean if you picked out the prefix of the application and let bound that, you're completely not stable under that. That's true. Yeah.
And the other remark is that you said that unification variable should not be substituted by should only be substituted by monotypes. You said this like a key rule, and that's not the point. They can be substituted by polytypes, but those polytypes should not be used unless you know that they really have those polytypes.
Oh, so you're talking about MLF, really, aren't you?
Just Camel does that. So MLF does that as well, but Camel also does that.
Okay, so I need to understand that better. So I think, Didier, you're saying that I said the rock to which I cling is that unification variables are instantiated only by monotypes, right? And you're saying, actually, you can relax that under some circumstances.
Yes, this is what I'm saying.
I should understand that a bit better. Thank you.
Okay, let's continue the questions at lunch, and thank our speaker.
Lunch. Good.
which perhaps I will. Oh, I probably have to press. Do I have to press that button? Which I'll possibly ignore.
Right. And so our first talk is from James Noble, who'll be talking about heaps of type systems.
Something like that. I was having a discussion with my colleague Sophia, who said she wasn't happy with my talks because I make too many jokes, and it wasn't clear what the takeaways should be. So I thought I'd start this slide with the takeaways. And the takeaways here are from KFC, this idea of a heap model, which I'll talk about, which is going to sit between, what sits between the operational semantics and the memory models. I'm going to give a bit of advantages of doing that in Daphne. I'm going to reflect a little bit on Dala and Rust and the overall experience I've had with doing this. It very much is a work in progress talk, obviously, because the slides aren't finished. So, any ideas, any Rust programmers willing to admit they're Rust programmers in the house? Okay, fine. So what's the lifetime of that borrow? Precisely. But does this, in fact, even compile? Should that compile? I mean, let's just, we declare mutx and there's some box of some size, and then we're initializing it in here, and we're calling new inside, you can't see, we're calling new inside that first block, which in Rust will allocate a memory scope, and then we'll allocate the thing inside the memory scope, yeah? And then it goes away at the first closed bracket. I'll gurn at the camera. Should it compile? I mean, I think you've got two different types because you've got two different memory things there, but of course it's Rust, so it does compile. Which raises for me the question, well, why? And how should we know? How should we know that that's what it's doing? Another example, I guess, somewhat related, this is the famous doubly linked list in Rust, except, of course, what's Rust famous for? Oops. What's Rust famous for? Rust is famous for the language in which you can't write, or sorry, safe Rust is the language in which you can't write doubly linked lists. Because doubly linked lists are bad. And if you talk to enough Rust programmers, they will tell you that you shouldn't want to have doubly linked lists, that wanting to have doubly linked lists means that you're morally impure. And that's my shitty thing playing up. It has worked. Sorry? Well, we're right. We had that. Or not wanting to have currying as the foundational basis of your language. Precisely, well, whatever, all these things are bad, and then at some point I say, yeah, well, I just think of a doubly linked list as a, sorry, you're approaching because you need to fiddle with stuff, or as a, we're good, right, sorry, as a proxy for data structures that people actually use, like B trees, which are kind of important if you want a database, a structure you can access with indexes and also traverse, or the kind of butterfly lists and edge structures you might have in computer graphics, where you do want these nested things. And how do you do it in Rust? Oh, well, we go back to using integer indices into arrays, which is kind of like Fortran, but slower, because, as there was a good talk in the capability workshop, the big issue in the English Rust community in particular is whether we should push all those array bounds checks into hardware and do it every single time, or whether we can somehow negotiate and actually optimize some of them away. Cheers. Right, this is really not the kind of talk you should give for those of you graduate students in the room. Don't do this. That's what Sophia would want me to say anyway. Or maybe you'll remember them the talk, I don't know. This is a classic Rust error message. You tried to have a doubly linked list, you're not allowed to. I had a workshop paper that put this code in, which is kind of drawing on other work that I did 25 years ago, which says, look, you could actually have a version of Rust where maybe you have something called local ownership, where stuff can't leave a thread, but and in fact, the things in this list have to be in the list, but it's almost as if those things, if you could have, and you could set it up with unsafe Rust, a linked list, you could have it if you had multiple immutable borrows, as they're called in Rust, yeah, multiple immutable borrows. You can make a doubly linked list with that topology in unsafe Rust. You can port it into safe Rust. You just can't work with it in safe Rust because of the Rust constraints. And then I guess as a researcher, my question was, okay, well, how do I convince someone who's now effectively working solo and trying to get contracts, if someone has a day or so a week that they want to rent my brain, it's available, come and talk to me afterwards. Luckily in New Zealand I was able to extract a research contract when I left my university, so that's sort of keeping me fed and in plane fares. What would I have to do to convince people that they should go into Rust? Oh, well, obviously what I ought to do is hack the Rust compiler. Hack the Rust borrow checker. Ellen in the front row. How long have you been doing that for? You've not been doing it. That's all right, you're right. A man has been doing it. Years. Okay, or I could learn cock or lean. Cheers. Model the entire complexity of the Rust programming language. So, the first, again, one of the takeaways there is this idea of a heap model. That often, I think, when we talk about our formal models, and this is obviously done in graphics, but for those of you who prefer LaTeX, can imagine this has been typeset in LaTeX. We have an operational semantics for our programming language on one side, and we're all quite familiar with that. And then the sort of semiconductors on the border there to represent the very low-level memory models that, again, if you worked on concurrent Java or concurrent Rust or anything, or even the Cherry stuff, you're all familiar with the rules about what happens when you have multiple CPUs accessing memory chips and all this question. Is it a weak memory model? Is it a strong memory model? Is it, you know, logically consistent or whatever? About threads and about hardware. And, you know, ASTs are often about types. Well, dynamic languages don't really have types, and sequential languages shouldn't really trigger these kind of low-level memory bugs. And, well, I was going to say extensible languages don't have syntax, but that's just being mean. But I think there is, for languages like Rust and a whole family of languages, I think we want something in the middle. And that something in the middle is what I'm calling the heap model. And so it's not the AST or the type system. On one side, it's not the detailed memory model about how you're actually interacting with the hardware, but it's the description of the kind of constraints I've been talking about in Rust. That's actually a picture from a dynamic or sort of dynamic/gradually typed language, a postdoc working with Tobias and I did a few years ago called Dala. We'll talk a bit about that. Effectively, it has three different kinds of objects. Local objects, which are the ones I've talked about with Rust that can't really leave a thread. It has immutable objects, the red ones, which are the things you're all familiar with from Haskell. And then it has ISOs, which are mutable objects, which can traverse threads under the sort of Rust-like condition that there is only ever one pointer into them. Okay? And the heap model is about describing that and talking about it. Let's see. Why Daphne? Well, the short answer is because I had experience with Daphne. In my the last course that I developed and taught was a third-year formal methods course. I've got other papers, and I'm happy to have discussions if people are doing that about my experience there, which was, well, Daphne was probably better than any of the other ways we'd tried it, but you need a lot of support. And, well, again, this is one of my favorite Daphne slides where I've written an if statement, and it's complaining about that I can't assign a sequence, a set of strings to a string variable. Anyone know why? Daphne, sorry. The brackets, that's right, yes, because Daphne is really two languages. It's really the expression language of Haskell bolted onto the imperative language of C#, and in C#, brackets mean grouping like they do in Rust, but in the Haskell language, the brackets form sets. So if you want to do a refactoring between imperative code and functional code, you have to remove or reinsert the brackets. But even better, you have to remove or reinsert the then keyword. I keep saying this, I'm glad people laugh, because I do think there is hard-won experience, as an aside, sorry, Sophia, that I do think there's hard-won experience in programming language design that we have gathered over the last 50 years. And would people using languages that they expect people to use please learn about it and actually apply it, or contract me to tell them what they're doing wrong at the very least? Well, in this case, the hard-won lesson is don't overload brackets. Don't have syntax where brackets interpretation is so different. And in one language, and in the name of Niklaus Wirth, do not have one if statement that has a then and one if statement that doesn't. I mean, let me just say that again. In the name of Niklaus Wirth, do not have one if statement that does not have a then and one if statement that does. Sorry, one of them is an expression. One of them is an expression. Sorry, Sophia. It's like the Dijkstra quote, but I think Sophia is now hiding in the camera. You know, there's a great quote about Dijkstra, which, when you do something dodgy, I want to imagine you're looking over the shoulder and thinking of Dijkstra. So this stuff is hard enough to understand, to pull it back to kind of the actual topic of the talk. This stuff is hard enough to understand, and this is just syntax. This is just syntactic, a lot of this shit. But this question we've seen in Rust about why can't I have a doubly linked list is more than just syntactic. It's to do with, well, it's what I call the heap model, or the effectively the semantics, not just of the code that I write, but of the heap structures, which I have to think about it that way, that my program may or may not build. I'm within friends. Can I do something daft at this point? I have a dream. This is a workshop, isn't it? Great, so you're not going to reject my papers just because I give bad talks, or, you know, my workshop, the workshop demonstration collapses or something. So let's try this. I have a dream. And having used Daphne, here is basically a bit of my dream. Sorry. It's a beautiful, it's dream for me. I paid a lot of money to get Apple's user interface designers to dream that dream for me. And yeah, you know, it's like, it's beautiful, and can I even turn off mirroring or turn on mirroring, which will then break something else, won't it? Can you see a menu bar? Alt F1. I don't have an Alt key. Okay, I'm not sure that helped. Thank you. Sorry. I have a dream, and the dream is that I will be able to get a description of these things that the dream is that I'll be able to get a description of these kind of things that I understand, these heap models, that if I'm a programmer, I'll be able to read and understand the actual descriptions. I mean, when I was growing up and I couldn't compile my Pascal or even my Smalltalk programs, I could actually go and look. Kind of, yeah, but I just forgotten how to work my computer. But it's all right because people tried to help. And screen mirroring, mirror or extend to Paulina's MacBook Pro. Can I see? I don't know. I can just not do the demo. It's probably the right thing to do. Great. Okay, I have a dream. The dream is that my laptop will actually project properly on the screen. Okay, sorry. Yeah, apparently people editing the videos for SIGPAN like my talks. Just saying, you can edit them down to about 5 minutes by leaving out all the comments. But anyway, great, this is my dream. We have this kind of thing where, you know, you can look at this sort of stuff. Here's, well, for Dala, this is in fact the heap model for Dala. Here's the important bit. Can some object f, the from object, have a pointer to the to object? And well, basically what it says is anything, if the to object is immutable, anything's allowed to point to it. If the from object is mutable, well, those mutables, because there's a hierarchy, are allowed to point to anything, but isolates can only point to other isolates and immutable objects. Is this the whole story? No. If people are looking puzzled, I'm happy to take questions, given how random it is, and you're all asleep after lunch anyway. For some reason, I always get scheduled after lunch. That's not true. Sometimes it's after morning tea. I do. I do. Everyone was pulling a face, but anyway. Okay, right. Yes. So Dala is the language that Kiko Fernandez-Reyes did, and there's a paper in Onward a few years ago about it, which is probably why somebody damned my European grant with the line, James Noble, he publishes in B-grade conferences. Yeah, that's right, because we had a graduate student do a prototype. Anyway, so you can find that if you look up Onward and me or Kiko Reyes. What I'm hoping to work towards is something that I used to call an object-oriented framework, but I probably have to think of some more Latinate phrase, like a conceptual ontology or something, for modeling these sort of heaps. Am I there yet? No, because I'm getting there. I might talk about that if I have a few more minutes. So Dala is the language I'm modeling. Technically, the name of the library or the framework, it's not really a library that I'm hoping to build, is Dahlia. Is this a joke about Iris? Yes. I'm not saying I don't think Iris is great. I think it is. I'm not sure I'm clever enough to use it, and I'm really certain that I won't be able to find programmers in the real world who want to understand Rust will be able to do it by looking at the kind of equations you need in something like Coq and Iris. I'm hoping, again, that possibly stuff like that is getting simple enough that people would be able to understand. Shall I go on? Yes. Mutable objects can have, that's a very good question. Actually, let's answer it. We can answer it. So let's look for, well, oh dear. Is this working? Can anyone see a find box? Well, we can answer it, and this is something I'm hoping that it could actually happen by saying, let's try and find, okay, all immutables are immutable. Okay, so there are basically a couple of predicates here that control how, what evolutions a heap is able to go through, and this is one of them. It's valid 2. This is basically the heap transition predicate, and it's saying one of the things there is all immutables are immutable, and if we keep on going, there's the definition of this. And what this says is for an immutable object, its field must always be the same. It can't change between each heap instant, each heap state. Okay? Mutable objects do not have that constraint. Can I find any other differences? Okay, initializing, we can't assign to immutable. Yeah, sorry. Right. Mutable and ISO. Okay, well, in that case, I should be searching for the wrong thing. But I can probably still answer by doing this. ISOs, blah, blah, blah. Well, that just tells us, gets all the ISOs. I knew I should have renamed this thing whole enchilada. Sorry, I haven't released it. If you're doing the artifact evaluation for eCube, I promise that I will rename, actually, fuck it. No, I promise I will rename this by next week. What this says is for ISOs, just the ISOs takes a list of edges. I haven't talked about the structure of the model. At this point, it's basically 3 layers of black. And this says, get me all the ISOs, and then the constraint here is that the reference count for every isolated object is less than or equal to 1. Okay? You can have one pointer from a heap to an ISO. That's basically it. And I would hope that with sufficient English text and shit around it, I'm not in America, not in the Midwest. Right, with sufficient English text and understanding around it. I mean, in some sense, we're seeing this in that the WASM specification, how legible it is, I don't know, is actually now part of, the formal specification of WASM is now actually part of the language definition. But I would hope that stuff expressed as simply as this could also be there. Can I really try and make a fool of myself now? What's the other part of my dream? My other part of my dream is that it's like, I was reading this obscure, well, it's not an obscure paper, but it's a paper that's probably POPL obscure, from Uppsala in, I think, 1991 about, this is terrible, bridges and encapsulation by John Hogue. What's the islands, of course. No object is an island. It's a great paper, and if you come from POPL and you haven't read it, you probably should, because I think we would have made more progress if POPL people had also read Uppsala papers. And islands is in some ways also one of these kinds of systems. Basically, the idea is we'll consider an object an island if it is separated from the rest of the program, pretty much in a separation logic sense, such that you can treat it as a black box. You can give horse specifications for its interface, and that those will actually be maintained by the program. And it effectively says it has 3 kinds of objects, well, 3 annotations, read, which I'm not going to touch, something called unique, which is pretty much the same as my ISO, and then it also has something else called free. And, okay, I can say, right, we're now also going to have objects that are free. What's the deal with a free object? Well, they're a bit like ISOs, except the idea, these are things, Could be an iterator, there could be the result of some long computation. The idea of a free object is you have an encapsulated object that creates this thing and returns it. So the deal of a free object is it's, why won't this verify? Can someone make this verify? If I do that, what's it doing? Yeah, okay. A free object is an object that has no incoming pointers. So my dream is that down here somewhere, I'm actually going to cheat and, where is it? Whole enchilada, isn't it? Oh, actually I could do it here. If nothing can point to it, then if we have a free object, if the to object is free, then nothing should be able to point to it, yeah? So I think if I do something like this, and I should probably say, yeah. Okay, I would like to do that, and now press the button. Don't you just love? And okay, that's actually validated it. And in fact, somewhere here I have a main method, and which effectively is testing a bunch of stuff, and I can say, okay, go back and re-verify that in Daphne. All right, and it dies. Great. Why does it die? I have an idea why it dies. Ha! Great. Who was it I said I was about to screw up the definition, but it wasn't going to end my career? Anyway, okay, it's because there was an example there. That is actually attempting to create 2 pointers into an ISO is what it was doing. Take that out. This thing should verify. Well, who knows if it'll verify. Whee, no problems. Okay, I'm going to take that as read. That has actually verified with the extra definition in. If we wanted to, we could now, well, in fact, because it's free, you can't actually add a field of an object and then assign it. Well, we could try that, and we could make a free object and then see again. Were we to do that, how do we do it? Var f4 is a new object, and it's free, and I'm just going to give it the same fields as any other object because I may as well. And now I can heap. So heap is a Daphne object that actually represents the reified heap. F-add object, F4, there we go. We've added in a free object, and hopefully that should be okay. But if we, a few minutes, I have had already some questions. If we try and add in an assignment to it or something like that, as we've seen here, that would break. And if we change this and said, okay, look, let's assign that free object somewhere, in fact, this could break in several different ways. Why do that? It will fail to verify. If I point at it, it will actually tell me there is a precondition. The precondition is actually that it needs to be free. I didn't rehearse this very hard. If you saw me preparing the slides, I actually first did a dry run of this example just once at about 11 o'clock this morning. So that seems a lot less work than you would need with Lean or with other approaches to this. That's what I hope. What's the downside? Well, as one of the slides that I haven't talked to is, it's still Daphne. There was a great comment this morning in one of the talks. We didn't do this because it was hard. We did it because we thought it was easy. And that applies. And I have negotiated a fairly carefully chosen path through the simplest model that I've built. It's about 500 lines, non-commented lines of Daphne. And there was another talk earlier about using Daphne to do the type system for the CEDAR security policy language. And when someone said, what lesson would you learn? The answer was, well, don't do it in Daphne. Go to the main talk, and we've got a description of the formalization of this, what we did in Lean. And that was much easier than trying to fight with Daphne because What I haven't shown you is when it works, and when it doesn't work, well, it just doesn't work. And yeah, psychologically, the notion of an intermittent reward, which is you keep doing something and randomly you get a reward, is exploited by the gambling industry, by the computer games industry, effectively by drug dealers. Highly addictive. Social media works on that precise basis. You send a tweet saying that SPJ has just recanted on currying, and you get no retweets, and then you've got to give a bloody talk about Daphne. So Daphne, I think, also works on that sort of basis, that sometimes it will all go through like this, and then sometimes it won't. And if it doesn't, you have much less information about the reasons why it doesn't than you might like. That said, I'm really delighted in what this has done, in that I didn't actually have this error message and actually coming back and saying, we tried to do something with a free object, and the absolutely standard Daphne error message is we couldn't prove it wasn't free. That's pretty damn good. Yeah, I do have time for questions, I hope. A couple.
Yeah, let's thank James, and then we'll take a couple of questions.
If I understand correctly, one point in the talk is that we can implement static policies as code in Daphne or some other similar tool.
Yep.
And then programmer would be able to play with them, understand them better, because they can see the code and they can reason about it in the usual way. It's running statically, but that's fine. Okay. But then my question is, when we use this sort of static discipline for memory ownership or any static discipline, pretty soon we need to add annotations on stuff that says, oh, this actually assumes this or provides this and so on. And it's very important in practice for the static checking to scale to modular programs. How does it work in your system? Can you just add post-condition and precondition that talk about your policies as you implement them? And would the users know how to do that?
The short answer is, of course, yes, maybe, and no. So because of the way these models work, although they're being checked statically by Daphne, they can be purely operational. If you don't, a dialer, because it's a gradual system, has a sort of mode of use where there are no static constraints. But we still want to know, okay, we're only allowed one pointer into an ISO, and it'll be enforced with dynamic checks. If you want more static assurance, then yes, you have to do annotations on your code. The way currently I'm doing it is you have annotations on effectively either your stack frames or the objects, and we statically check against those. So the preconditions for doing, say, that initialize operation is that we're sure there isn't a field there. The third question is, I think that in future we could finish the whole, well, at least do the left half of the picture, where this could go in underneath a traditional operational semantics or some kind of semantics of language model, a type system, and then you would prove that keeping this type system preserves the invariance that you want in the heap. But I haven't got all that connected up yet.
All right, let's thank James again. All right, and now our second epic talk of the day. Simon Peyton-Jones will tell us about type inference using constraints.
Okay, great. Thank you very much. Yes, good. Okay, so same rubric as before. Please make comments and ask questions as we go, and we'll have a lot of fun together. We will finish in exactly 30 minutes' time, regardless, somehow. Okay, so here is the plan for a fairly conventional, type inference or algorithm. What happens is you have some source program, and you write some more or less difficult type inference algorithm again, and it rejects the program with some error messages if it's bad, and otherwise it accepts the program, in which case it produces, no output at all. It just says good program. Okay. So, I want to keep this is an implementation workshop, so I'm going to put up type signatures as we go. This is what a type checking function might look like. It takes an expression, and we talked about this morning, the expected type that it has, right? And in some monad, it produces no result. That's the unit at the end. But what does the monad do? Well, it does at least 3 things. It's got to keep the type environment, which keeps track of what variables are in scope and what their polytypes are. That's the gamma part in our types thing. That's a kind of reader monad kind of thing. It's got to be a place to emit error messages. That's a kind of writer monad style thing. And then it also has to deal with unification, which you might think of as being a sort of state monad, but it's growing a substitution from unification variables to types. Or if you're going to do it imperatively, it's actually done a side effect on a mutable variable, which of course is what we really do. But if you're thinking more kosherly, it's just a substitution that you're building up as you go. Okay, so that's the monad. We're going to have an ambient monad all the time. Right, now, so the second thing we're going to do as we go is we're going to elaborate the program. What does that mean? That the type checker, as well as rejecting the program if it's bad, will also produce a new elaborated program as its result. So what does the elaborated program do? It makes explicit the type instantiations and applications that go on. So GHC is a little unusual here. In GHC, we take a Haskell program, we produce an elaborated program, which then gets converted into System F, which is statically typable, right? So right the way through the compiler, from the front end right through to the back, we've got a statically type checkable program in System F. That means that we need to know where the big lambdas are and where the type applications are. So here's an example. I've got foo here, which calls sort of reverse of x's. Sort and reverse are both polymorphic functions. So in the elaborated program, I need to be explicit that I'm calling reverse at type int, and that I'm calling sort at type int, and moreover, sort is overloaded. It's got this OR day constraint, so it takes an ORed int dictionary. I'm not going to dive too deep here, but it's an actual runtime value that is passed as an extra implicit argument to sort. So this is the elaborated program. This is the original source program, and it's part of the business of the type checker to cough up this guy, given this guy. So far, so good? Right, and the elaboration also has to do, we dealt with applications, the elaboration also has to do with abstractions, right? So here, if I've got foo, my foo here was not polymorphic. It was just list of int to list of int. Now here, this foo, same code, but now he's polymorphic for all a, or day, list of A to list of A. So what does he do? So foo has to start with, he's got a for all type, he must start with a big lambda. And he's got an OR day constraint. He must have a lambda for some dictionary for OR day. And then he has his value argument x's here, and it's explicitly typed with type A, or is it list of A? Oh dear, sorry, that should be list of A. And then we sort, so then the application bit as before. Is it what? Concrete syntax. Is what concrete syntax? The light blue box. The light blue box is the elaborated program. So you can imagine it as being written in a slightly larger language with explicit dictionary abstractions and dictionary abstractions, type applications, and dictionary applications. Just a bit of a larger source language. You don't have that language. We have some of that language. In a Haskell, in fact, we have extended the language with explicit type applications like these guys, but not with explicit dictionary applications, because that might be incoherent. Yeah. Yes, that's true. If the signature was not here, and we just gave this, we will infer this signature and cough up exactly the same elaboration. Thank you. Yes, carry on. Yeah. Okay? So, long story short, type inference takes a syntax tree and produces a new elaborated syntax tree, which is basically the same one with type decorations, including these abstractions and applications, and also every binder in the source program, which didn't have types on it, like this X is no type. In the elaborated program, the binders do have types on them. So does that make sense? So it's a very helpful thing for the type checker to do. And that means that the type checker has a type that looks more like expression, and then here's the expected type. And now it's a TC monad returning an expression. So simple enough idea. but very useful in practice, I think, which we found pursuing this consistently is good. Okay, so now enough preliminaries. I want to get to the main bit of this talk, which is about constraints, right, and generating typing constraints. So this is what I call the French approach to type inference, because I learnt it from Didier Rémy and François Patier in their wonderful paper, The Essence of ML Type Inference, which is long and quite technical, but brilliantly written. It took me about 7 goes to understand this paper, but it was worth it, right? This is, if you're going to read one paper, it's just the basics. So go read it. So all I'm going to tell you is I'm just the sort of like the shill to interpret Poitier and Rémy for your benefit, if you don't already know. So their idea is this. You take the source program, and first thing you do is you walk over the syntax tree generating constraints. So when you finish that, you have an elaborated program. The generation process produces an elaborated program, and you have a whole bunch of constraints, as yet perhaps unsolved. Then you solve the constraints, and that generates a substitution that you're going to apply to this elaborated program. I'll show you a little bit about that happening to get you the final elaborated program. But also solving the constraints may lead you with some unsolved residual constraints that you can report as type errors, right? This is the architecture of a type checker, and I want you to, that's different to this, in which all of, it's broken this arrow into several distinct chunks. Why is it helpful to break that big arrow into constraint generation and constraint solving? Why is that good? So here are 5 reasons why it's good. Number 1, constraint generation has a lot of cases, right? Haskell is an enormous language. So the number of syntactic constructs is, 50 or 100 or something, right? So there's lots of cases here, but constraint generation, pretty simple, right? So there's a lot of cases, each of which has pretty simple code. But the constraint solver is really tricky. Oh, man, if I had £1 for every hour I'd spent on the constraint solver, I'd be a rich person, right? So constraint solving is difficult, but constraints are written in a small language, which I'll show you very shortly. So it only has a small number of cases, but each of those cases is very subtle. Does that make sense? So what you don't want to do is to have a lot of cases, each of which is subtle, right? Many cases, easy code. Few cases, really tricky code. Much better way to factor your problem. Thank you, Didier. So another important thing is that the results are independent of the order in which the constraint generator traverses the program, right? In many type checkers, if you write a pair E1, E2, it'll type check. If you switch it round and it's E2, E1, no longer type checks, right? But there's some left to rightness in the type inference algorithm. There's no left to rightness here because the constraint generator just walks over the program, spitting out those constraints. The constraint solver kind of sees them all at once in some more, it has a more global view. It's much more it's much easier to make it order independent. It's not easy to make it completely, but it's much, much easier. I think this is a big win myself, but it's tiresome if your program changes. If minor syntactic changes to your program change radically its typing behavior. Apart from that, apart from anything else, it's hard to specify, right? What's the spec of the type system? Okay, elaborated. Generating the elaborated program is relatively easy. The act of constraint solving is more or less filling in the holes of the thing, as I'll show you. And error messages are generated. Error messages are really hard to generate. Spreading the error message generation code all over the constraint generator is pretty hard. In fact, I'll show you. Here is a sort of breakdown of lines of code in GHC stuff, right? So constraint generator, 11,000 lines of code, and not quite as many lines of comments. Constraint solver, 6,000 lines of code, and rather more lines of comments than code because it's tricky, right? Error message generation, 9,000, a monstrous amount of code is just to deal with trying to generate good error messages. Splitting that out into the bit that is right here, right, looking at a constraint and spitting out error messages is much easier than spreading it out all over here. So in practice, I found this to be a really big win. That's really what my sales pitch to you today is, chaps, this is the way to write type inference algorithms. And your life will be happier if you adopt this in a wholesale way. Okay, of course, Didier and François, they don't do this in OCaml. Is this the way it happens? Not at all. But we have adopted your... in the future. But we have wholeheartedly bought into your plan. Okay, so let me just say a little bit more about each of these steps. Right, so constraint generation. how do constraints get generated? What does it really look like? So I'm going to show you. Well, here's my type checker. Remember, we're familiar with this type signature, right? It's in some monad. And we're going to provide some primitive that lets us emit a constraint. We'll have to see what a constraint is, but emit is just going to stick it into what does it need to stick it into the monad? Imagine that the monad is carrying a bucket of constraints, and we're just collecting them all. And then finally, collect constraints takes a computation that generates constraints, and gathers up all the constraints generated by this computation and will return them as a paired up. So collect constraints of some computation thing, will run thing, gather the constraints and return a pair of the constraints with the value returned by thing. But this guy here emits no constraints of its own, right? Because they're all the ones that came from inside here appear here. Does that make sense? So it's just a standard monadic approach towards sort of gathering constraints in a state. Good. So the monad here has a sort of writer monad here that just gathers constraints up. We don't need to read. It's just a writer monad. Okay? Simple enough. Monad was already there. We're already paid for. Whenever anybody says something is for free, what they mean is you've already paid for it. Right? And this is true here. Good. Okay. So what are these constraints? Well, there are not very many of them, actually. A constraint is either empty, or it's a pair of constraints, or it's a class constraint, like show A or ord B or something, or it's an equality constraint. We'll see those in a second. Or it's an implication constraint, which I will tell you about in about 5 minutes' time. But when I said the constraint language is small, this is what I meant, right? Because really, these first two are barely worth talking about. They're just like a collection of constraints. So really, there's only 3 forms. That's not very many, right? It's amazing how hard it is to deal with those 3, though. Right, so here's what the constraint generator might look like for an application. What do we do? Well, so it's not exactly like this, but it's kind of close. Let me see. This is binary application. So forget this morning and vector, right? I'm just taking the simplest case, a binary application. I'm going to infer the type of E1. Remember, infer is just a little wrapper around that TC function. Remember that from this morning? So I get the function type. Then I'm going to make, the function type ought to be an arrow, shouldn't it, right? But it might not be an arrow yet. So what I'm going to do is I'm going to make up fresh unification variables for the argument and result. And then I'm going to unify the function type with this arrow type, right? Because they should be equal. And then I can check that E2, the argument has this argument type thing. Now, this isn't exactly what happens in GHC because of the stuff to do with higher rank that I was describing, but it's I wanted to make something simple enough. I could show it on one slide for constraint generation for application. But the thing I want to point you to here is this call to unify. Now, this doesn't mean actually unify the function type and the arrow. It means emit a constraint for that equality. That's all, right? But there is an opportunity that sometimes you can, on the fly, say, he's trying to unify list of A with list of B. Well, I could do that. I can do the list part easily, and I'll just emit the constraint A equals B. Right, so this guy can do a little bit of on-the-fly unification really quickly because it's a bit more efficient than emitting the constraint. But the idea is it's exactly as if you just emitted the equality constraint. Garrett?
But is it important that you didn't also unify A and B?
Is it important that I did? Where was A and B?
Well, you said list of A and list of B. So
Oh. Oh, no, sorry. Is it important? So when I said you could quickly look ahead when you're trying to unify list of A and list of B, could I unify A and B? If A and B were, say, unification variables, alpha and beta, then you could unify them. But supposing there were scolums from something, but there was maybe an equality constraint in scope, which mumble. So yes, there are lots of times when you can do a quick fix, including actually performing unification. But if there's any doubt, if anything tricky happens, you just say, I'll emit the constraint anyway, and send it off to the constraint solver, who is very clever, right? You do the stupid things right away. The clever things you leave for that wonderful constraint solver. Okay? Yeah, Capra. Say again?
You say this is for speed.
Yes, for speed. I don't actually know how much difference. It would be easy to find out, but I don't actually know. Probably not that much, but a bit. Okay, so that's how constraints get generated. Yes?
So there's also a missing piece here, right? Presumably you have to be tracking source.
Oh, you're talking about how can I generate good error messages if I don't know source information? So when I say unify here, I emit an equality constraint, but I also attach to that constraint provenance information that says, where did the constraint arise? Where does that provenance information come from? It, of course, is in the monad, right? And so when I come across a node here, the first thing I'm actually going to do, right before that do, is to extend the monad with something, say, I'm in this application, or something like that. Yes, thank you. So every constraint does have its provenance with it as well. Yep, Joachim.
If I have a list of constraints and I don't have the microphone.
I'll give you my microphone. Go. Yeah.
So suppose I have a list of constraints and they are just equality constraints, right? And I solve them by either they are equal, so I throw the constraint away, or they are not equal, so I substitute one for the other in the remaining constraints, and I risk quadratic runtime for solving the constraints.
Oh, I'm going to show you the constraint solver next. Funnily enough, that's the next thing.
All right.
So we're talking about constraint solving. So now we've generated these constraints. So in principle, we've walked over the whole program and done no solving. Now we have the constraints and we're going to solve them, right? So how does that work? Well, here's a bunch of equality constraints, Joachim, right? A couple of, here's just two. So what do? So the idea is I repeatedly pick a constraint and try to solve it, and if I can, I make it simpler, and if not, I move on to the next one. So here, the first one I pick is list of beta equals list of gamma. Fine, I can solve that by decomposing, but I have a new constraint, beta equals gamma, to solve. How can I solve that? Oh, perhaps by unifying beta to b gamma by side effect. So then I solve that. Now I've dropped down. Now I've got this. Right, and now I've got to solve this one. So I decompose that, and then delta equals int, and I unify that, and that leaves me with ord delta, but now it's being unified to b int, so that's just ord int, and I can solve that. Did that answer your question? That's what the constraint solver does.
Okay, so the question is sort of, in the talk this morning, you had this bidirectional type checking, whereby you sort of find the inconsistency immediately, whereas with this type checking algorithm, do I pay with a slower runtime complexity?
No, so the question is, how does this relate to bidirectional stuff? All the bidirectional stuff is here, interestingly, right? The bidirectional, all that up-down stuff we saw this morning, that occurs over here. By the time we generate constraints, bidirectional stuff completely dealt with. Bidirectional stuff deals with the quantifiers, right? And these constraints are mostly monotypes. Yeah. Okay, so let's see. So that's roughly how constraint solving kind of goes. You can see that. So all we're doing, this step at a time thing that I'm showing you here, that's just Robinson's unification algorithm, isn't it? Right? Nothing new there. It's just expressed as a kind of rewrite system. But there are some other things going on. There's these class constraints, and also, as we'll see shortly, we have some given constraints. So it gets complicated at the end. Right. Next step, how does solving affect the source program? Well, what I'm actually going to do, what actually happens is that the elaborated program is full of unification variables. You might say lambda x with type alpha, where alpha is a meta type variable, unification variable not yet filled in. When the constraint solver fills it in, which it did here, right, that, as it were, affects by side effect. Ooh, this is an imperative program. In the heart of GHC's type checker is an imperative program. But so we fill in all the holes in the elaborated program. That's how the two are connected. It's funny, this generates quite a big data structure that's completely separate as this data structure, but these constraints all have, as it were, pointers into the elaborated program. But it works very, very nicely and very simply and robustly. That was another idea from here. Okay. All right. Last thing I want to tell you about is, yes, we have 9 minutes. In fact, actually 10, maybe. Level numbers. Right. So also, I learned all about this from your paper about level numbers. Actually, I think it was a tech report. I don't know whether it's shown up in the paper. Maybe it has. It's another folklore thing. And you probably learned it from somebody else. You're probably going to deny inventing it. Right? But I'm going to tell you anyway. Right. So, oh, beg your pardon, wrong direction. Now, what happens when I am type checking something like this? So here's just focus your attention on this lambda here. And this double colon is a Haskell source level type signature for all A to A. So it's a claim that lambda y dot x has type for all A to A. Does it? Of course not, because it's got this free variable x, which is bound outside this for all, right? So something is wrong here. But look what happens if we sort of naively generate constraints. We might say, well, you know, the F2 must be a beta to gamma, so X will get type beta, and then in the body here, I'm going to get, dear, what am I going to get? I'm going to, have I got this completely wrong? I think maybe no, that's right. Then gamma, this result type here, that's kind of going to get connected up with X's type. So, but the A here comes from the signature. So am I allowed to unify the result type of the whole function, F2 lambda X dot something, that's something, gamma, am I allowed to make that equal to, by sort of unification, with this for all A thing? Obviously not. That's wrong, right? It's just wrong. So what to do? I can't tell you for how long I sort of scurried around with sort of half-baked implementations, and then I learned from Paris, and now we just have level numbers. So what do? Is just say, well, look, when we walk inside this for all, we're going to, first of all, every type variable is going to have a level number attached to it. It's just permanently part of that, including both meta-type variables, these Greek things, unification variables, they have level numbers, but also scholars like the for all of a universally quantified type. So here then I'm going to, when I walk inside the for all, I'm going to say, inside a for all, I've got this thing A in scope, but it has level number 2, right, because I'm walked inside something. And then I've got gamma from level 1, that's from the outer thing. It's got to be equal to this A from level 2. And then we're going to have the rule that says I cannot unify a unification variable from an outer scope with a scolum from an inner scope. And so it's a pretty simple rule. You just look at the free variables of the type you're unifying with and decline to unify. And that leaves you with a residual constraint that you can then report. So it's sort of super simple, but it needs this implication constraint thing, right? What is this? This is one of those constraints. Do you remember? Have I repeated the syntax of constraints? Bother, I haven't. But the syntax of constraints, do you remember, included for all a W, double arrow W, and here it is here. And this, incidentally, is totally part of Didier and François's paper. Just took me a while to understand what they were doing. And these implication constraints, super good. Right? So the idea is pretty simple in the end. The type checker monad carries around yet another thing, which is the ambient level of the type. Whenever you make a fresh meta-type variable, you just take the ambient level. And at something like a type signature, when you walk inside the type checker, we scholamize it, scholomizing to the, you bump the level, scholamize the type variables to the new level, and then check the, in this case, the expression inside with the body type, with the A, the bound variable substituted by this level numbered scolum, and away you go, right? And then you build the implication constraint. And the implication constraint is just emitted into the monad to be solved later. Right, so you get a big tree of constraints. I'm going to skip, am I going to skip promotion? Yeah, I've got 2 minutes. I'm going to skip promotion, yes. So I just want to say this idea of level numbers and implication constraints scales nicely to handle lots of different things. And I just want to quickly enumerate the different things. Number 1, when you're inferring types, when you've got something without a type signature, this is Gabrielle's point, right? We need to say, I want to quantify over all the type variables that are not free in the environment, right? What do you mean, free in the environment? That's just a level number question. Very easily solved, right? So no walking over the environment to find its free variables. Pattern matching with existentials and dictionaries. Here's a data type in Haskell. This is a type with no parameters, but inside this data constructor has this funny polymorphic type, result type T, of course, but it binds an existential variable A and a sort of dictionary, show A. That works very nice. I'm now going to have to go quickly. You end up, again, with implication constraints. That handles that very beautifully in the same way. There's a trickiness with GADTs right back in the original GADT paper. It says if I've got a function like this, what does this say? T1 is a function that takes an int and returns a T int. So when I pattern match on T1, I know that this A here is an int. Sorry, this is a different T than the previous slide. So if I say this function Tx arrow x, now this x is an int, but perhaps the function has type Ta to A, because inside this right-hand side, A and int are the same. So there is no principal type for this f. So in the original paper, we talked about, oh, so for these kind of functions, we want to reject the program on the grounds there is no principal type. But then you have to say, by what mechanism are we going to reject it? And it turns out that this whole implication constraint infrastructure gives you just enough leverage to do that nicely. Elaboration, this is number 4, the things that it scales to handle nicely. When we got these funny data types that bind dictionaries, like this guy, right, then we might have some constraints inside that we must solve using the constraints bound by the implication. So we're going to generate some runtime bindings. And so, in fact, this program elaborates to have a let binding. And this let binding here, is like a unification variable, really, in that it's just the name for a mutable reference. And right there in the implication constraint, we say, oh, this is a pointer into this part of the tree. And when we solve a constraint using this guy, we should add a binding to that. So it scales nicely to handle the solving dictionary constraints with involved values. Lastly, quantified constraints. This is a fairly recent, like only 5 years ago, innovation to GHC, where you've got functions which don't just say ord a double arrow blah or show a double arrow blah, blah. They have something on the left of the double arrow which itself is quantified, hence a quantified constraint. I do not have time to pause here. I just want to say the very same mechanism makes this easy to handle. So, big picture. This is essentially what, let's see. Let me just stop here, right? So, I think that this game of generate and solve, with the glory of implication constraints, is just sort of on all axes a better way to write type for inference engines. And again, you should have a sort of reason not to do it. And I repeat my grateful thanks to Parisians for telling me about this. This is the way GHC's type checker is. And I think that more should be like this. It's great. Thank you.
We have time for 1 or 2 questions.
I'm curious about how you generate coercions for GADTs, because there may be many qualities in the context that justify why A would be equal to B or int, and then you have to generate a coercion term. What's the strategy there?
So you're quite right that you're talking about coercions, right? Because your point is that when GADTs are involved, the pattern match actually binds a coercion, and we're going to elaborate. And when we have a unification constraint, like where was my syntax my syntax of constraints here? This guy G, the evidence for inequality is a coercion. So it works by exactly the same mechanism as type classes. We just generate coercion bindings in effect. And it doesn't really matter which equality you use to solve it, so long as there's one available that's in scope. So I don't think we've had trouble with saying which of the many possible ways to prove it. Any proof will do.
I have a possible reason not to do things like this, then I'd really like to be told it is
yes,
that works anyway.
Good.
But also, it's not one that applies to GHC. So languages which aren't Haskell often do some amount of type-directed disambiguation of names, type-directed lookup of fields. And that means that by the time you're doing scope checking of like a record field access, you need to know some stuff about the types already. So compilers that I'm familiar with that do this do it because they don't work in this style. They solve some of the constraints as they're going and use those partial solutions to decide what next. Have you thought about doing that kind of type-directed stuff in this style?
So, in a way, the setup I've described also does something like that, in that when I said that this part, the constraint generator, deals with pushing types down, it really deals with all the placement of quantifiers, right? It knows where the for-alls are. When I said it generates the elaborated programming, all the for-alls are placed in the right place. So there's some amount of type pushing up and down that's happening here, right? But it's very statically defined what that is. It's not sort of, you solve all these random constraints. It's very programmatic. Now, it's possible that the type-based name disambiguation that you're describing, it's possible it could be expressed and specified here. If it required some complicated constraint solving to discover which of the many X's you meant, that would be a bit of a worry. But so then I agree that it would become a lot more complicated, right? But maybe you could do it over here. And there is precedent for that in that we're already doing that for quantifiers, effectively. All the quick look stuff, for example, is right over here. Quick look entirely over here. All that stuff this morning, all over here. Yeah. Well, here, I should say. Yeah.
So record.syntax essentially does it with constraints.
So another plan for multiple fields is to encode record accesses, using a sort of type class constraints, which is what Haskell's new sort of has field constraint is all about. And that does let you postpone it off to here, but by expressing the things you need to know in the language of constraints, in effect. But a more ad hoc, that's when it's not a more ad hoc sort of overloading, you might want to handle over here. Yeah. Capra? Yeah?
And I guess that is made easier by the lack of, it's made easier because you gave up on local generalization. Otherwise, you can have interaction between generalization inside the term and this
yes,
constraint.
as ever, very insightful question. So now, what happens if I have a local let, right? If I've got a local let and I want to generalize, I've got some constraints arising over the body that have not yet been simplified, not yet been solved, right? So I could just abstract over all of those constraints and get some kind of giant type, like for all 100 constraints, double arrow, blah. That would not be very cool, right? So what we do in GHC is either we say, don't generalize local lets at all. Good plan, by the way. Let should not be generalized. Little paper about that. But if we want to generalize, and many people do, I regret to say, then we just say, damn the torpedoes. We'll solve the constraints. We will call the solver during constraint generation and just do the best we can. So now you probably could cook up an order-dependent problem, right? Yes, I mean, I think so there you're kind of a little bit outside the envelope of what I think is truly principled. But hey, it just works fine in practice, I'm embarrassed to say. I almost wish it failed more brutally. Yeah, Didier.
So actually, in this case, you only need to solve a fresh part of a constraint. This is what we did in the essence of ML type inference.
You mean the bit that's concerned with that function?
With using the levels. So you want to solve it up to the level to which you want to generalize. You don't need to solve all the constraints.
Yes, so if you've got constraints, when you're solving the constraints for a local let, if you've got constraints that involve only variables, bound at an outer level, you can just not solve them and leave them on one side. No need to solve them, yeah. It's just the ones that are local. And even the ones that are local, if you can't solve them, you can always abstract over them, right? Because after all, you'll expect... Then you're going to duplicate the solving, right? So it's kind of optimization thing. Yeah, that's exactly it.
All right, let's thank Simon again.
Yeah, good. Thanks.
Thank you. That was a very helpful introduction to what I'm going to talk about.
Oh, good. You can pay me later.
Indeed. Well, I'm going to back you up on your 2 talks, so you can pay me. Is this going to be on? Oh, that's not what I wanted, but we can make it what I wanted. One of these is screen mirroring. Which one is it? That's my other screen, which I don't want. That's what I want. Great.
All right, and our final talk of the session will be given by Edwin Brady from Standrews about a new core for Idris 2.
One of these buttons, if I look like, are you okay to hear this? Everyone good? If I look a little bit confused about the way I'm presenting things, it's because usually I don't use slides. And I've prepared a few slides for this one, unusually. I don't have any live demos. So I'm very confused with what I'm doing. Anyway, because I've prepared lots of slides and I never know how long slides take, I've put a spoiler alert on the first slide so you get the takeaway. I'm going to talk about essentially where we are with the new implementation of Idris 2. That was the point of giving this talk. I've been implementing a new version of Idris for the last, goodness knows how long, about 5 years. I've started a new core implementation over the last couple of years. I realize I've never actually talked about it. I've talked about the language, but I've not really talked about how things work internally. So I thought this would be a good opportunity to tell you that, essentially a brain dump of the one most interesting idea and how it all fits together. And it's right here on the first slide. Takeaway: term and value representations are indexed by names in scope. If you're in the business of implementing a dependently typed language and you've decided to do it in a dependently typed language, the thing you have to do up front is decide to what extent can you use the type system to help you. There's a lot of choices you could make. Like, do you do nothing at all and just implement it conventionally and do a couple of proofs? Do you put types, the types of terms in the term representation themselves? Do you go somewhere in the middle? Well, the takeaway is there is a sweet spot, and it's indexing terms by the names in scope, and we'll get there. We'll see what that looks like, and I'll talk a little bit about the trade-offs. This new implementation is called YAFL. If you are British and at least as old as I am, then you may recognize Professor YAFL from Bagpuss. Professor YAFL is a bookend who comes to life when Bagpuss, the cloth cat, wakes up, and he is an actual know-all. So I thought it would be a good name for my functional language core, because the core knows everything about the language. Okay, so I'll give you a brief overview of how the Idris implementation works. And this is just going to be sketchy. Pleasingly, a lot of the details of elaboration, a lot of the core representation, a lot of how that elaborator works has already been covered in Simon's 2 talks. So entirely accidentally, Simon has given me an introduction. So I'm totally going to back up what Simon said in those last 2 talks. I was actually also interested in Stephen's question about type-directed disambiguation of names and how it fits into this system of generate constraints and then solve them, because we pretty much do that in Idris. And the way we resolve it, I could maybe have done this on Simon's time rather than mine, but the way we resolve it is we generate the constraints, and if we get a point where we are not able to disambiguate, we just say, oh, let's solve the constraints we have and see if that helps us make progress. Anyway, so all of the things I don't say refer to Simon's talk. That's how it works in Idris, pretty much. It's implemented in Idris 2. This was partly a challenge to myself. So we had an implementation of Idris 1 that was working, and I thought, well, it's about time I tried implementing a system in Idris, like something interesting in Idris, and I realized the only thing I know how to write is a dependently typed language. So I thought, okay, well, now is the time to try implementing Idris in Idris. So we got something working, an implementation of Idris 2 and Idris 1. There's some small changes between Idris 2 and Idris 1 syntactically, small but significant. The biggest being Idris 2 is based on quantitative type theory. So it was a little bit of a pain when deciding to switch from implementing in Idris 1 to Idris 2 because we had to deal with those changes. But I did it in April 2020, and I had nothing better to do. So, it was fine. There's a silver lining to everything, I suppose. So it compiles via Shea scheme, and this is another thing I would highly recommend you all do. If you happen to be implementing an experimental programming language, which quite possibly most of you are, because that's the sort of thing we do here, I can highly recommend Shea scheme as a target. I did this as a quick hack in 2018. 2018, yeah, about then. Fully intending to move on to a proper implementation, and it still compiles via Shea scheme. And I've been really impressed with it. So Shea scheme is fantastic as a back end. We do turn off all of the runtime checks, or as many as we possibly can, because it's basically, I've done the type checking. I don't need Shea to do the runtime checks for me. And the performance, worth mentioning, it's very hard to put a kind of real figure on how a language performs. I'm going to assert usably fast, whatever that even means. Essentially, it means that if I ask it to do something, it will typically reply in a reasonable amount of time, like a second or so. And a lot of this, I don't know where, I think he's in the room somewhere. Andras Kovac, yeah, there he is. Thank you. Taken a lot of the ideas from Small TT, and a lot of ideas I should have taken but haven't yet from other things. And it's been marvelous for getting a system that actually runs in a responsive way. It's at least an order of magnitude faster than Idris 1, which, to be honest, is not hard. But there is a but here, and this is, I don't know if it's OHAD's fault or OHAD's responsibility, or OHAD being extremely helpful. OHAD has worked Idris 2 very hard indeed with some of his research into Frex, and has found if there is a spot where Idris 2 is slow, I think OHAD's found it, almost all of them. And we got to a point where it was just there's no way of dealing with these issues without really going back to the core and essentially doing the things that we should have done right in the first place. Because, I mean, that's what you do, isn't it? You think, oh, why didn't I do it like this in the first place? Well, because I didn't know in the first place.
Do you know now?
But I know now, and I'll tell you when we get to the end what the idea is. Type checking. Well, type checking and compiling. And I suppose I could claim that in terms of generated code, that means it's fast because it's self-hosted. So, but I mean, these things are very hard to measure, and I'm not really the one to be the judge of it, quite honestly, because, you know, if you come along and use my language and you think it's slow, then I guess it's slow. So all of this is very hand-wavy, and this is all work in progress anyway. My feeling, and I see OHAD nodding, so OHAD feels that it's... I know when OHAD doesn't think Idris is fast enough because he comes and tells me. Sorry, question?
Yes. How long does it take to recompile Idris with Idris?
It's about 3 minutes, I think. So... it doesn't do a lot of. It doesn't do all the same stuff as you know, Haskell and Agda and so on. But yeah, it's something like that, 3 or 4 minutes. That's I can't. I mean, that is just an order of magnitude. It's not including. Or is it including libraries? It might be. I haven't timed it for a while. I think the last time I typed make bootstrap, which is where it takes the scheme code and then builds the library so that it can build itself and then build itself. I think that whole process is about 5 minutes. So I'll time it afterwards, just to... yeah, so I just wanted to say a little bit about the structure, because I think it's worth knowing about, and it kind of tells you a bit about what my future plans are. So there is Idris high-level syntax, which it's just syntactic sugar for a language that doesn't really have a name, but I call it TT-imp. So it's type theory with some implicit stuff. So it's a core type theory with local definitions. It's got case blocks, so a dependent case structure, rewrite rules. We do a lot of interactive, like if you've ever done any Idris or Agda programming or proving in Coq, you know that programs spend most of their time in an incomplete state, so it's a lot of the time is working with incomplete programs. So there's interactive editing support. All of that happens at the TT-imp level, and then we kind of re-sugar back to Idris 2. Now, part of the reason I think Idris compiles a lot quicker than, say, Haskell is I think Haskell does all of that with the high-level syntax, and that's, you know, it gives you better error message. Yeah, exactly, yeah. Which has the big advantage is that we can experiment a lot with high-level features. Big disadvantage is the error messages we have to, and displaying things, we have to work quite hard to get back to where the programmer started, and we don't necessarily get it right. So, you know, trade-off there. And that elaborates to QTT, which is a core type theory with quantities. So essentially that means that every variable is annotated with the number of times it can be used, which is either 0, that is it's compile time only, 1, meaning that it's linear, or unrestricted, which is, so Idris 1 would be Idris 2, but everything has the unrestricted quantity. Okay, so I'll show you, this isn't the whole of the core, this is the interesting bit of the core. or as far as this talk is concerned, the interesting bit of the core. So we've got variables and binders. Binders can be either lambdas or functions. I just find it convenient to treat lambda bindings and pi bindings the same in terms of the syntax. You don't necessarily have to do that. We've got application. So application in the core language is just a function applied to a single argument. That's in the core. When we elaborate it, we do what Simon said earlier, because it works really nicely that way. We've got the type of types. Now, Idris 2 does have type in type, so please don't shoot me. We do have plans to add universe levels. It's just that nobody's shouted at me that they really want them yet, so I haven't got around to it. You know, we have there's a big constraint problem generated. There are several things in the system that say generate a universe constraint here. We just don't do anything with that information. So one day I'll get around to it. And the other thing that is new in this new representation is that we have case expressions in the core language. So what we used to do, we'd have top-level definitions that were just pattern matching definitions, left-hand side, right-hand side, and then core expressions. The right-hand side could only be, well, everything here other than case. Now that is a really nice, simple way to implement things for a while. Works very nicely. And then you try writing a linearity checker, then you try writing a totality checker, and it's a nightmare because you have to. If you give people case expressions, they will use case expressions. They're a very convenient way to program. You get destructuring lets. It's if you've written a Haskell program, you do pattern matching lets in your do blocks. We write Idris programs the same way. So. To make the rest of the system easier to work with, like to make the linearity checking, totality checking, compilation easier to work with, we've now put case expressions in the core. So, not let or let rec. No, they're at the moment. They get lifted out to the top level, which your face tells me what I'm thinking as well. Oh, we don't. A let is not a let rec like in Haskell. So they're essentially like where blocks. So we have where blocks that are lifted out to the top level. You can't have mutually recursive lets. So it's
so they just turn into applications.
So lets here just turn into they're sort of but not quite lambdas that are immediately applied to something. So I think that. I mean, I think that is an oversimplification, and that's my next step that after this current thing to deal with. Neil, you have a question?
Yeah, do you have to have a motive for your case statements?
No, you don't. What will happen, I'm not sure I want to go into these details of elaboration, partly because they're complicated and partly because they're a little bit embarrassing sometimes. We've got type-directed elaboration. So in fact, it's what Simon was talking about earlier with the, you've got the infer a thing and you know that you're inferring a thing that is a meta variable that you will solve later. Sometimes you know what that type is, and when we come to a case expression, sometimes we know what that type is and sometimes we don't. If we don't, what we can do in the elaborator is say, pause, come back to this. So elaborate the next argument, say. And one of the things we have in our giant monad, because we have a giant monad too, one of the things we have in our giant monad is a list of the things we haven't dealt with yet. And so we might have to come back to it if we haven't worked it out. And the type checker might just have to give up, in which case it will tell you, I need you to give me a type here. I'm talking about the elaborator here. So here, everything in this core language is checked. So I'm really just talking about the core representation here, because that's the takeaway of the talk. Well, I kind of want to say that everything about elaboration is unsurprising. It's the stuff you would do in any language with a fancy type system. Okay, so let's talk. I don't have very long for this now. So I knew I'd have too many slides. Let's talk a little bit about the core representation, because that is really the key thing I want to get across. Is that core is QTT. So you've got a lot of possibilities. Do we just do things the way we're used to and have de Brown indexes, de Brown indexed variables? Do we do something a bit fancier and have terms indexed by their types? And I spent a while playing around with different possibilities here. So I was thinking, oh, well, we've got a very sophisticated type system. We can prove large amounts of our implementation correct. And I very quickly realized, no, life is too short. What I want here is to be more productive. So I want the type checker to help me with the things that I always get wrong and not get in my way on the things that are at least, I'm not going to say always get right, because I don't, but the things that are more easily testable. And where we've ended up, I won't go through these details because you've seen this sort of thing before. I'm just going to skip to where we ended up. So this particular structure, or this particular predicate, I'm going to say that pretty much everything in the entire implementation of IDRIS 2 is influenced by this little data type. Now, what we're looking for when we're writing a dependently typed application, I claim, is finding the place where states can be illegal and make those states unrepresentable. So, you know, this is the typed programmer's mantra: make illegal states unrepresentable. So what I'm trying to do here is make it impossible to get de Bruijn indices wrong. Now, if you've ever written a program that manipulates a term with de Bruijn indices, you've probably gone home crying at some point and thrown your computer out the window multiple times. You've probably looked for libraries and tools to help you. And I think, let's say you're working in Haskell or OCaml. I know there's libraries out there that help you deal with names, right? So and probably half of you have written those libraries, and the other half of you have used those libraries. I don't use any of those libraries. I use the type checker. And it's all this structure. So this structure is a representation, or it's a predicate that says that a de Bruijn index is correct in the current scope. So we've got the variable name, we've got its index. So this nat is. It's more complicated than that. It's not actually represented as a name at runtime. This name is really just for display purposes. But it's a complicated string. So it's a namespaced string. And then we've got a SNOC list of names. So these are the names in scope. The reason it's a SNOC list, by the way, is because when you write down the typing rules, you'll stick the variable on the right. This was a list for a very long time until my former postdoc, Guillaume Allais, got really annoyed and switched all of them to SNOC lists. And he was right. So, yeah. So the zeroth variable is, n is the zeroth variable in the scope that ends with n. And if n is in scope at position I in the variable's ends, then it's at scope at position I plus 1 in an extended scope. Okay. So hopefully not controversial. Nope.
It reads as if your answer to the question of should I use names or indices is to say both.
Correct, yes. And then I have a type checker that tells me, makes sure that the two things are consistent. So here's the other thing. If I were to represent this in the way it worked in IDRIS 1, which was written in Haskell, local variables had an index, and it was just a nat. That was or it was just an integer at runtime. So nat at runtime, it's essentially it's an integer. And then we have this proof that this index is correct in this scope. And oh. Okay. Well, that was a good moment for it to vanish because this 0. This is a bit of quantitative type theory magic. That 0 means that if I accidentally have to use that proof at runtime, I get a compile time error. So what that means is I've proved that the name is in the correct place in scope, but I only have the nat at runtime. So QTT, thanks Bob, thanks Connor, is lovely for this sort of thing because it means I did a whole PhD on this and it didn't quite work out. I mean, it kind of worked okay, but we've now got to a point where we know which things are going to be there at runtime and which aren't because the quantity says so. So these are just two very little ideas I'm showing you here. QTT is useful for erasure, and indexing terms by names in scope is unreasonably helpful, and then everything works out very nicely. So what follows from that is you have to write a bit of machinery. So this is all the machinery that you have to write for term manipulation anyway. It's just that, you know, if I, let's look at weaken. So weaken is an interface is what we call type classes, and we call them, yeah, I won't go into the details of why. This is where we say, oh, a term in one scope is also a term in some bigger scope. Or in order to do that, I might have to weaken the scope with some variables in the middle. Here's a fun one. Challenge to you. Take your de Bruijn index representation, write a function that swaps the position of the top two variables in scope. Good luck. Type checker told me how to do it. So rather the interactive editing told me how to do it. And I know this works because it type checks. And that I don't know, I just find that pleasing. I should have grown out of how pleasing I find that by now, but I haven't. I mean, obviously it's frustrating trying to write the program in the first place, but you know that when it works, you're not going to have any surprises. Now, I promised one more thing, and I'm nearly out of time. And 5 minutes, okay. If I've got 5 minutes, then I guess I can do this almost properly. The other thing, this is the key thing that OHAD found, is about evaluation or unification. So a crucial part of the elaboration process is taking a term and evaluating it as far as we can, given the program we've got. So there might be symbols that we don't know about. So that happens during unification. And that might mean that we have to evaluate some fairly big terms. Now, what Idris, the first implementation of, well, what Idris 1 does is it just evaluates it to normal form, because I was experimenting and I wanted a thing to work. What Idris 2 does is something a little bit cleverer, only a little bit cleverer, in that it has heard of closures. And it's, you know, you get a weak-head normal form. But even then, sometimes it evaluates too much. So there might be something you might have a function application which it can evaluate but shouldn't. And what we don't know in advance is whether we should evaluate or not. So a really simple example of this. Imagine I'm unifying 1 million plus 1 million with itself using nats. Now, if I say the unification works by evaluating to head normal form and just keep going as we find out more about the term, that's going to take ages. But I already know it's just 1 million plus 1 million, so I shouldn't need to go any deeper into the expression to do that. So we don't necessarily know in advance which of these strategies is going to be the right thing to take. So again, thanks to Thierry Cocon, possibly. So this is a glued evaluation. Again, I learned this from Andras. I should have known it already, but again, you made it clear to me, so thank you.
I borrowed the glued term, I think, from Connor.
Yeah, and so I think it's in the Epigram Reloaded paper, possibly. And I don't know where Connor and James learnt it from. I think it goes back to the 90s anyway. For some reason, even though it's one of those things that even though we've known it's the right thing to do, nobody's done it in any.
What is it?
Oh, yes, sorry. I got so distracted by that interaction that I forgot I haven't even told you what it was.
Everybody denies inventing it, but what is it?
Well, if I tell you, then okay. So glued representation. What's happening is when you've got an application node. In your value, you keep the application node and what it evaluates to. That way, if the application node without evaluation is enough, it's right there, you've got it. This is good news, firstly, because it makes lots of things quicker. You can do like an approximate conversion check. But it also means that when you print out the error message, you get the thing that the programmer wrote and not the thing that you happen to have evaluated it to. So it looks a bit like this in values. So, oh look, here's an application to a spine. We've seen that today. So we've got an application node after we've evaluated it will be the function name. There's actually a bit more going on here. I've simplified this a little bit, but it's the name applied to its arguments. That's its original form. And then if it's possible to evaluate it further, which it may or may not be, because we have to deal with the fact that programs could be partially written. We have programs that might be type declarations, but not the definition. So we have to deal with the fact that it might be stuck. But if it does evaluate, if it turns out we need to go further, we can go further. This core, by the way, is the giant monad. I put monad in quotes because for technical reasons, it's not quite. But think of it as a monad, it contains all of the state, all of the meta variables. In fact, all of the things that Simon mentioned. Thank you so much for explaining my talk in your talk. So all of these parts of the type checking monad, they're all inside core. And if it turns out we need to go further, we can. But it turns out a lot of the time we don't need to. Now, initial experiments, I haven't been brave enough to try OHAD's Frex yet because we're not quite there. But initial experiments are showing that this is, in the general case, very slightly slower, but in the kind of unhelpful case or the difficult cases, it's significantly faster and is removing the bottleneck.
Do you put a pair of the unreduced thing and its weak-head normal form?
It's an unreduced thing and a thunk that will give you the
A thunk that will give you
the weak-head normal form. Yeah.
Okay.
So
you get all the way to weak-head normal form,
yeah.
not just one step.
So this is actually I kind of skipped this, but a value is indexed by whether it's the unevaluated or it's definitely evaluated. So this actually I've done this to make it easier to port from the existing IDRIS code. But the values are indexed by whether we know that they're a normal form or not. So we can look at the type and say, oh, I need to do more work on this. Or we can look at the type and say, I've definitely got the normal form here. Or I've definitely got the head normal form here. So I shouldn't say normal. That's really weak head normal form. Right. I'm just going to give you the lessons learned because I am out of time. That indexing names by scope. I look at it now and I think, wow, that's simple. But it is unreasonably helpful. I think it's saved us so much debugging time. It's increased the amount of frustration when writing the program in the first place, but we don't have to keep going back to the program and debugging it because we know it works. Quantity 0, wonderful idea. So we're based on QTT, so we've got 0, 1, and unrestricted. I think 1 is, academically, the 1 quantity is probably the most interesting, but 0 is so useful. I could just have QTT with 0 and unrestricted, and I would be happy. And yeah, promising feedback from early adopters. And finally, I'm just going to say we are almost compatible with IDRIS 2. 95% done, so I think there's about 95% to go. And so probably what we're going to do is just take the best bits of this new representation, YAFL, and move it to the upstream IDRIS representation. Essentially, that's the gluing. And then I'm going to go and have some fun with YAFL because I've been wanting to play with some more ideas of surface languages for a long time, and I'm expected to work on IDRIS. So I'm going to take YAFL and have some fun with it. And yeah, you can help me have fun too if you like. Yeah, thanks. I'll stop there.
So we are eating into the break, but if people are interested in asking questions, maybe we can have 1 or 2 questions while the people.
Yeah, I don't want to keep you from your coffee, so.
I have a short question.
Sure.
What if you have add million plus 1, million minus 1? Is that fast, slow, or don't care?
Good question. I'll have to try that. So what I would hope is that it depends how you've written them. If it reaches a point where the two. Yeah, if one step would get to the same thing, depends how you've written it though. So, I mean, I think my advice would be don't write a program like that if it's taking a long time to type check. But don't doctor it hurts one eye. Don't do that then. Yeah, easier said than done. Sorry. Yes.
So a question is, one difficulty with the small TT work is that his benchmarks are sort of synthetic and ugly, most of them. So is it a problem that you can help improve on with YAFL? Because now we have real-world programs that people care about that you can use to play with these ideas.
Oh, maybe. I mean, this is something I've noticed looking at small TT is that I'm trying to get the same performance as small TT because small TT is really fast. And I think, well, part of the reason that IDRIS isn't quite that quick is because it's got a lot of other stuff to deal with. But also, we're not necessarily dealing with all of that other stuff well. So, we need to. There are things that we need to revisit. But yeah, having a full size system that is using those ideas is probably a good place to play. Yeah.
Hi, I'm kind of curious. So when I see these scope index things, I feel that for very simple, simply typed lambda calculus, you only extend the scope one variable at a time in a very boring way. So I kind of trust that this is a reasonable thing to do.
Kind of like
but I feel that for more real life languages, you need operations like list concatenation or these kind of fancier things. And so I wonder, like in your experience, what kind of list operations do you? Okay, so these are really the things. You need inserting something in the middle is the only, and swapping is the only crazy things you do.
I've carefully chosen these to be the most complicated things we have to do.
Okay.
There's a lot of list associativity proofs.
Yeah.
And once you've done it once or twice, every one of them has the same pattern. To the extent that I would like to know how to abstract it. I guess OHAD's on the case for that as well, to be honest. That's part of the point
I
of
think
Frex.
on this thing, I don't know if you've seen it, there was a talk by Jesper Cox at Types this year that was basically trying exactly this, trying to find like a fanciest representation you can do for like scopes, so that you would support all these kind of operations natively. And I think his conclusion was kind of a negative one, that he actually didn't, like he ended up with a data type that was so complicated that he ended up in some sort of weird impossibility corner.
Interesting.
So yeah, you might want to
I
look at that.
Because at the beginning, yes, it was a challenge.
Okay.
But once I'd got over the initial challenges, it's like, oh, it's all the same now. It's no problem.
Thank you. It's very enthusiastic that you can get away with this kind of things. Yeah. Thanks.
All right, so I think we should probably wrap up at this point. Let's thank Edwin again and all the speakers this session.
Thank you.
We'll resume here in slightly
ignore everything.
Okay, much easier.
Asahi?
Okay, hello everyone. Welcome back to the last session of WITS. So our first speaker will be Favonia. So take it away.
Hi, hello everyone. So I'm going to introduce a OCaml library called Asahi, which is for compiler diagnostics. And I appreciate all the many speakers before me because they basically introduced how important compiler diagnosis are. So I don't have to repeat that. I only have to just show out what we have done under that assumption. So you might wonder why we have this name. Unfortunately, I measured the time. I do have like at least 10 jokes that hidden inside of this name, but I'm not able to do it. But so anyway, so we're going to move on. So think about a typical implementation day. So you are exhausted after listening to all the POPL talks, and you feel like you have absolutely no energy whatsoever to implement error handling until you see this. Okay, this is a typical OCaml thing if you are just using some minimum way of the kind of raising the exception. And you're going to have this, and with all these lines which are not helpful at all. Okay, then you talk to yourself, okay, I have to implement something even to myself to understand what's going on. So then when you are trying to implement compiler diagnostics, and then you have to worry about many things. And in particular, in our case, we are trying to build a general library which should be, usable in many cases. So we have to think very hard about what constitutes a good compiler diagnostic. So the first thing, like a mechanism should provide is to determine whether a program should terminate now. Whether it's something that you cannot recover and you should just give up, or there's just some message that you want the user to know and then you should move on. That's something that you have to decide. And the other thing is, how serious should the user take it? Is it an error, is it a warning, or just some info or some kind of tip that the user can safely ignore? So there are several classifications. And I'm listing this as 2 items because they are different. An error doesn't mean that the program should terminate. The warning doesn't mean that you should move on. They are just orthogonal to each other, okay? And then there are still several things that you might want to include in a compiler diagnostic. For example, a Googleable code, because why? Well, when the user sees an error message, what they're going to do is to copy the part that they think that is the most important from the screen, and then put it into Google, and maybe after some clicking, then focusing on the Stack Overflow website or whatever that is there. Maybe in near future there will be some website powered by the ChatGPT or something like that. Okay, but anyway, they're going to have some keywords. So if you can put in some very unique ID that is recognized as one single word by Google or whatever search engine, it will be very helpful for the user to identify, to locate the documents. And this has been used by Rust and many other languages. And I think that is actually a very good convention to keep. The other thing is then a user perceived stack backtrace, the traces, like why this error has happened. And I want to make another clarification here. It's not a code backtrace. Because the user doesn't care how it's really implemented in your code. You might have like 10 different helper functions in order to implement one thing, the one conceptual idea, but the user doesn't want to know that, in order to infer the type, I called a another function to infer just for pi type, and then infer whatever, right? So you don't want to understand the detailed backtraces of the thing, because to the user, it's not very helpful to really understand how your code works internally. Okay, they want the conceptual reasoning about why the error happens, and they are different. Yes?
So it's a backtrace into what? Into like ideal implementation of the compiler?
So that's an interesting thing. So it's more like you have to describe at a higher level, like what you're doing. For example, you might say that I'm trying to infer the type of this term, but not in terms of I'm calling this function for this argument and then calling then another function with that argument, because the user couldn't understand like what you're doing. So this is really a backtrace, but at a higher level, trying to describe what you're trying to do at a higher level, and which might not match the code stack. Yeah. Okay. And the final thing is to allow multiple spans. Now, by a span, I mean a part of the source code. Why does it matter? So that's so many instances. So I was actually surprised when I think I got a question about this. But anyway, so for example, if you have a pattern matching and you want to say that the type of the branches don't match, you might not want to just pick the first branch or the last branch. You should just highlight all the branches, right? And then say they don't have the same type, for example. So that's one instance. And you can probably come up with many more usage of the multiple spans. But the gist of it is that it's in particular for a general library, we should be able to support multiple spans as our representation of a diagnostic. Okay, so we think these are really crucial parts for a good diagnostic. And then there's many other designs. So this talk will really just be our own ranting of like how other people might have been doing wrong. Okay, so for example, like, okay, actually this, I don't have a standard answer for this, maybe later slides. The other thing that you have to consider about the compiler diagnostics is whether your message is structured or not. So let me show you what we mean by that. So 100% structured is that, for example, in a language such as Haskell or Camel, you can have an inductive data type give you a very rich representation. And you can very well just define a type representing all the possible errors in a very structured way. Like everything has come with its own constructor and so on. So that's, I'm going to call it like 100% structured. And the 0% structure is like just a string or something like that. And you might want to stand in the middle, which means that, for example, in this case, there's a type error, okay? But I'm not going to specify, like, I'm not going to give a unique constructor for every kind of type error. I'm going to have a type error, but then all the remaining additional information as string or something like that. So this, I'm going to say that it's somewhere in between. And it's not an easy decision to make, like what should be just a totally unstructured strings and what should be a dedicated, unique constructor. But I'm going to just provide some of our thoughts. We do believe that some structuredness does help the user. In particular, the code that I was talking about that user can Google, that is part of the structuredness. So some classification should help the user identify, or by identify I mean Google, okay? Nowadays, identify means Google. So they can Google the pages they want to look at. However, if you go all the way with full structuredness, I think in practice you are going to encounter difficulties in many cases. And one of the significant cases, in my opinion, is the parsing. Because there are so many different possible errors due to parsing. Maybe unmatched symbol or something missing or something expected, and you're going to do that, or some lecture looking for something in the end of the string and it's not going to find it. For example, that you can come up with so many different kinds of errors, and I think it's very annoying if you're trying to define a very precise data type with a unique constructor for every single case. So maybe this is a case where you just want to have a parsing error and have all the rest as a string or something like that. So it's something you can think about. So which one? Well, we support both the fully structured and the 50% style in our library. So we actually design our library very carefully so that it actually makes sense in both usage. It's not an easy design. We have to sometimes argue with our intended user to say, no, I think this doesn't make sense. The user said, yeah, I want it. And then anyway, we came up with some design that I hope that is reasonable. Okay, now I think I'm going into the territory where I'm going to have more and more rants and maybe jokes. So the first thing is compositionality. This is something we want to really uphold in our library design. So the typical thing that you might be thinking about is that your main program is using the library. And if we manage to convince all of you to use our library, in near future, we are going to have libraries that are also using this RSI as error reporting. So it's important that to be able to use a library that is using this library and then somehow combine all the error handling together very nicely. Okay, at least that's what we believe that should be important. And it's not just using one library. How about using another library? And what if there's a library that is using another library? So we have been, I don't want to show you the API now, but we have been taking lots of time making sure that this is easily doable, like almost trivially. Okay, so, all right. Let's see, I think I'm going to really have a first big rant. Okay, I need to get ready. Okay, the first thing, Unicode. So this is, by Unicode I mean typically non-ASCII things, but actually everything just Unicode. So here I have some characters on the screen. So ABC, and then there's a Zhongwen here, which is in Mandarin, but it doesn't really matter. It can be any script. And then there's an emoji in the end. So in the past, people have some ideas about column numbers. Column numbers means, well, with the position on the screen there, right? But how about this, right? Is that 4? Like, how about this? Is it 5? Or 1, 2, 3, 4, 5, because this is wider, right? So already the introduction of all these fancy characters is going to screw you up. And it's not just like that. You might think, okay, maybe I can come up with a heuristics kind of a database to say that, okay, this is wider and this is thinner and et cetera, maybe I can get along with this. I'm going to show you that. Good luck. Okay, so the next thing that I want to show you is that there's something called Scala value, and this unfortunately is a terminology that even I think the people in the Unicode committee might have trouble with. So I'm not calling it just Unicode character. It's not an official term, but I think it's better understood. Okay, and there's one Unicode character for this little a and little b and little c, and this entire thing is one Unicode character. But this emoji that I handpicked actually consists of 3 Unicode characters. I just want to show you how horrible the situation is so that you can give up, okay? It's not, the details are not important. So if at this point you feel like, okay, too much, please stop. Yes, that is exactly the message I want to give you. And if you haven't given up yet, please follow me so that you can really give up. So what is this 3 in this pirate flag? It actually consists of a black flag with a 0 width joiner, which is a spatial Unicode, which consists to like 0 width, and then with a skull. And this is kind of joining these 2 things to form the pirate flag. Why am I showing you this? Because the database approach will give you this some kind of wider thing and this, right? And then if you are naively thinking that, well, I can just add up all the widths of individual characters, good luck. Okay, if this is still not convincing enough, please talk to me offline. I think we need a conversation. Okay, but the point is that there's no easy way to predict how wide anything it will be actually on your screen. It depends on your font, the font. Depends on the terminal. It sometimes depends on the locale. It's very complicated, and I really don't want to go into the details. And then many programs use some in my opinion, broken heuristics in order to guess like how wide it is. And just yes.
So yes, for example, if I want to send my diagnostic to an LSP server, if I want to send my diagnostic to an LSP server, they have expectations about how they measure positions. So is it possible to at least respect that from using your library?
Okay, so we have managed to come up with other ways which do not depend on the feature widths. So that's our solution.
But is there enough information in an SI report so that I can at least give the position to the LSP server that they expect, so that they do something useful with the diagnostic?
I see. Okay, so the more technical answer is that the LSP is actually not using feature widths. It's using the number of units in the UTF-16 encoding. So I'm going to just say that this is, for example, the 1, 2, 3, 4, 5, 6, 7, 7th code point. I'm not talking about the feature widths, but I'm talking about some kind of unit in some encoding. So in that way, I'm not referring to the how wide is it really on the screen, so I can avoid this problem. Yeah, so there is a way. Just forget about feature width. Okay, forget about feature width, and you'll be okay. Yes. A second.
Can the programmer use the zero width character on its own to sort of hide code, let's say, inside of the character?
Okay. So let me just bump up the game even further. There are ways to even change the direction of the characters from right to left, inside the left to right, and then inside the right to left. It's recursively defined. So you can have a program where if you naively rendered, it will even change the semantics of program because you are going to render, for example, the different cases of the pattern matching differently. Yeah. Okay. Is that cool enough? Okay. There was some Unicode recommendation. Yes, Unicode is very horrifying. So we haven't even touched that part yet. Just don't have any naive assumption about Unicode. Every assumption you are making is basically false. Yeah, yes, I can justify that. Okay, this is my biggest rant ever, and then, so this is some messages from relatively naive tool. So you're going to have, using this ASCII, right, to kind of guess, like, to approximate the visual length. And as I just showed you, this is just mathematically impossible. So we just feel like, no, we don't want to do it, and we are going to uphold this as much as possible. So if your tool doesn't work for emoji, then it doesn't work. Okay, that's it.
So what do you do instead?
Oh, we're going to. Okay, I'm going to have a demo in the end.
Okay, cool.
Yeah. Okay. So and the other thing I want to share with you when we are working out the design is a tutorial-oriented design. I think this is something we learned. So we write out a tutorial, like this link. And the point is that if you couldn't write a tutorial, then your design, in my opinion, is just bad. Like if you want to test, like, does this API make sense? Well, try to write a tutorial. And if you could explain it, good luck. But if you couldn't, then you have to go back to the design and change it. And we're going to call it rubber duck design method. I mean, there's a rubber duck debugging method where you just have a rubber duck and explaining why your program makes sense to the rubber duck. And here it's basically the same thing, right? You are explaining to a rubber duck why your API makes sense. And if you couldn't do it, you should change your API. So I think this is one of the meta principles we are holding. What else? Okay, so there is some OCaml library just came out very recently that is called Grace. It's very similar, but since it came out, I think I will have to put on some related work section. So this is one of the latest slides I just put in. So it's very similar. It's just our representation is based on the LSP. LSP stands for Language Protocol. And then the Grace is inspired by Rust. So we have different representation, but otherwise very similar. And we are using algebraic effect to generate these diagnostics. So there's lots of care to make sure that it's kind of easy. I'm going to show you easy to generate the diagnostics. And I don't think Grace has something as fancy as ours. And the rendering, we are basically focused on emoji. Emojis is the only thing we care about. And Grace is embracing more the traditional view of the diagnosis and then having all these ASCII R's to point out where it is. Okay, so, but our design, both libraries actually separate the rendering from generation. So after running some bridge code, we can actually use Grace to render our diagnostics and vice versa. So there's no fundamental incompatibility, between these two libraries. Okay, I'm almost done. So I have some success stories that I want to share with you. Well, first of all, we actually just created a prototype to make sure that we are not lying to ourselves, that it's working, and it appears to work with our prototype. And then there's some interesting customers of our libraries. One is that John Sterling actually just created a tool to generate his website. What else can be better than your own tool, right? So he created this, and the point is that it's not a proof assistant. We created it for proof assistant, and then we insist that it should work for emojis, but then it turns out to be also useful for other things. And then there is a work in progress type checker by Max Schulman on the HOTT. This is not public yet, but it's public that he's working on this non-public project. Okay, and then we are basically looking forward to more customers of this library, and because we actually learn a lot from our users to improve our design. Their feedback is really important, and we also want to hear from you. So I would like to invite you to consider our library in the future when you are creating your own tool. So this is, I think, the shortest URL that I can come up with. Okay, I think I have 2 minutes, so I can really show the thing. Let's see. So, I thought I need a Q&A for. Oh, I thought it's 20. Oh yes. Okay. Yeah, but can I switch your mic to this? Okay. Right. So the thing is, in order to use this library, first of all, you of course using open install RSI or something like that. But I'm going to skip that part. The actual change you have to make to your code is to create a module like this. Okay. There are 3 things here. The first thing is to define a type T that is basically kind of the data type I'm talking about to represent all your possible errors.
Why doesn't unbound variable carry to variable name?
What's that again?
Unbound variable should be of string or whatever.
You could do that, and that would be more structured, but you also don't have to do that because we do have another way. You can just attach that as a part of the unstructured part of your diagnostic. You can also put it in structured. As I said, we designed the API carefully so you can just do your own style. So this is a very relatively unstructured, right? It only has some very rough classification of the errors, but that's okay. And then you have a default. Basically, this is to tell the user how serious it should be, and we just said everything is an error. But it's a pattern matching function, so you can just map, for example, type error to a warning if you want to, or something like that. And I actually didn't expect that I would have time to explain the code. So I apologize if I appear to be unprepared because yes, I am. And then there's a short code. This is to map every error to Googleable term. And if you feel like, okay, Fafonia, I cannot remember this. Remember, we have spent all the time writing out a tutorial which explains every step you have to follow. And actually, it says much more than I do now. Okay. So you have this module, and then finally, you just include this, and this is a function which takes your definition of error message, and now you are ready to go. Okay. So this is I think, very easy to adopt. So now I'm going to change the main file. So this is a file where you are going to add in the generation of the error message and other things. So this is a typical, let me actually zoom out a little bit. So this is a typical, just a very simple MBE for, actually not MBE, bidirectional type checking for the lambda calculus. And then there are two things that you can do. So I'm going to search for reporters. So one thing is that you can report an error. Well, yes, because I mean, what's other thing this library should do? So you can have a report fatal, and then this will be, the first argument will be the thing you just defined. So what the error is, and then here is the unstructured part. And you can see that you can even have a formatting because that's the F variation. So we really try to make your life easy, okay? So if it's just a string, you can just have a fatal, but if you want to have a formatting, you can have an F version, like print F, just like F, which allows you to have this kind of formatting. And then how do you generate the semantic backtrace? This is done by calling this trace function and just putting this will be the content of the frame. So it means that when you're calling this function, you're going to push a new frame in the backtrace, and when eventually all this backtrace will be collected and then printed out in the renderer, okay? And then what else? So you can just go through this file and then put in the fatal F or emit F or whatever to the places where you want to report the error, and then add a trace to the places where you want to create a new frame in the backtrace. And then finally, you just, let me scroll down, and then you have just use some algebraic effects to kind of pick a renderer. I know this, I don't expect that any of you can understand the code right now, okay? And then that's why we have a tutorial. You can just pick a renderer, and that will print out everything on the screen. So I'm going to just show you what will happen on the screen. So, but the main message is that you don't have to do much in order to adopt this library. So after all this work, this is an exciting part. So I think because everything is expected to fail during live demos. Actually it works. Why? Okay. So here is an error message. It's saying that this doesn't have the correct type. This is checking. This is bidirectional type checking. And you see that we're using the coloring and underline instead of color number to overcome the Unicode problem. And this is saying that when checking this against this type, and then you go into the term, and eventually the actual error is here is that saying this is not in the scope, okay? And you don't have to worry about this fancy ASCII art. We are already done that for you. You only have to provide the content of your message, and we are going to put together everything that you have told us to render it beautifully on the screen. So that's what we have done for you. So please consider this if you want to have this, okay? Yes?
So suppose I have like a type checker written in monadic style. Yeah, so I have some type checkers. They're all written in monadic style. If I add ASCII, will there be like bad interactions between like effect handlers and the kind of monadic style programming, or do I have to switch to using effect handlers as well?
Oh, that's an excellent question. So unfortunately, the interaction with the monads and algebraic effects, or in general any kind of like exception and also algebraic effect both, they do not interact very well with monads. And I don't feel this is our fault. It's some kind of fundamental limitations that maybe someone should publish a POPL paper to deal with.
Okay, so we're pretty much out of time. There's time for a quick question, I think. Go ahead.
So, asked about column numbers, and you said you're going to show us. So you showed us, right? You're going to change the colors and do the underlining, which you presumably do by sort of fumbling around in some Unicode string and adding extra characters that do underlining and coloring. So your library somehow does that. How do you? What's the generic way, application-independent way that you manage to do this coloring and underlining business?
So underline really depends on the actual renderer. For the terminal renderer, we're using there's some there's some ASCII control code that you can use to change the color. So that's one way. If you're using HTML, then there are other ways to do it. It really depends on what kind of backend you're using. And for terminal, I think this is the best way that we can find without depending on the color level.
Maybe I can ask in a different way. So this backend thing that renders it, right? The renderer must have some input that is kind of like the original program, and then some spec for which bit should be underlined.
Oh, that's a
right. What is the spec if not column numbers?
Okay, we're using bytes because bytes is the most efficient and the best way. And we have a section dedicated to why all other choices, in our opinion, are worse.
I see. So sort of byte offset in the original
byte offset.
String.
Everyone should use byte offset. Really, seriously.
That was the missing piece of information. Thank you.
Okay, I see.
Okay, this will need to be the last question, I think.
Thanks for the talk. That looks really great. 2 questions. So first, is it a camel-specific tool? Like, can I use it from other native languages or perhaps JVM-based languages?
It's right now written in OCaml, but I believe the design is not dependent on the language. It's just that we love OCaml, so we use it. But I think the design is not specific to OCaml. Yeah. So feel free to copy the design, and we want to. You might have to if you want to copy really the entire design, yes. But I think you can still use Monad to do this. What's the second question?
And the second question is, so the thing with like error F or trace, it reminds me a lot about the logging I would add to my type checker. So like, what's the reasoning? Like, what if I want to have both the logging and this form of like fancy error reporting?
So what you want to do is to go to our GitHub issue, because there is an issue trying to create the best API which does both. Because it's very similar to logging, but logging is for developers and diagnostics are for users, and they are different things. But often the developer want to see both and more, right? So we should be able to use the API in a way that the diagnosis is actually part of logging. And that is what we are working on right now. So there's a GitHub issue, and please join the discussion and give us feedback. Thank you.
Okay, thank you very much, Favonia. Let's thank the speaker. And our next speaker is going to be Andras Kovacs, talking about unfolding, controlled definition unfolding, which I need to know about myself.
I guess this microphone. Okay. Okay. Hello, everyone. I'm Andras Kovacs. I'm going to talk about efficient elaboration with control definition unfolding. So there is a slight change compared to the program, because in the program I wrote evaluation, but then I thought that there are many things that I actually want to talk about, which is more related to elaboration. And fortunately, once again, I can say that all the previous talks talked a lot about elaboration, so now I can be double, triple thankful for everyone else who already explained what elaboration is. Okay, so what do we want? We want to fill holes during elaboration with nice terms, and we want to present nice terms to users during interaction. And unfolding all definitions everywhere is usually not nice. So we want to avoid that. But not unfolding anything can be also really bad in certain situations. So what we want to do is to preserve all these unfoldings. Essentially, we want to preserve the ability to make unfolding choices until we can actually make a good decision. And we also want to do this in an efficient way. So, like, for example, we don't want to recompute expensive computations from the scratch using a different unfolding mode. So let's start with some performance concerns related to unfolding. So there is this very classic Hindley-Milner type inference example, where we have a bunch of lets, and you can see here that I'm defining by let a pair of booleans, then I define another pair and another pair. And if we do type inference for this thing, then the elaboration output would also need to annotate these pairing constructors with the types, because they are some kind of polymorphic data constructors. So at each step, the size of the type involved here would double, and then in the end, we would get like 2 to the power of n size of types. So this is a very classic example for exponential inference in Hindley-Milner. And you might ask, well, who writes code like this? So why do we care? But apparently, EGDA users, including myself. So there are quite a few EGDA examples when we do some very crazy dependency type formalization, and actually we are doing some kind of essentially like a layering of indirections in dependency, which can result in exponential blow up. And we can also talk about quadratic elaboration. So quadratic elaboration is surprisingly common if we have fancy types. So here you can see an example where you have a cons, which is just, so this is some kind of pseudo AGDA. So the cons is just a constructor for a vector of booleans. And here I have a definition for a vector where I'm consing together a bunch of truths to define some vector. And these underscores are just holes standing for the length of the rest of the vector. And if we do an elaboration and we unfold everything, then we will get a quadratic output, because here we have a suck, here we have a suck. And you can see that this doesn't quite fit, so I'm illustrating that this is too big in a sense. And sometimes people might actually want to copy-paste maybe a vector of size 100 into code, or maybe they have some tactics which output a vector of a size of 100. And there's also a related GHC, so there is a blog post about this, when writing essentially generic programs with heterogeneous list, exactly the same issue happens. And then the solution would be to have some kind of type level let, which can be used to introduce more sharing so that we do not have to unfold all of these lengths or types in the elaboration output. Okay, so hash consing is kind of a well-known solution to prevent size explosions. But I say that hash consing is not sufficient, because hash consing doesn't know about beta expansions. So if you have like unary natural number, and then we might define 1 million, we can define 1 million in a very compact way using just a bunch of recursively defined operations. But if we actually evaluate it, the end result is incompressible by hash consing. And also hash consing, it doesn't really help with preserving unfoldings for the purpose of user interaction, but it can be still very useful to clean up very bad input. And it's kind of a general phenomenon is that whenever people write code, it's good input. But when tactics or programs write code, it can be really, really bad. And in that situation, hash consing can be still essential. Okay, so let's have a very basic setup. So this setup is getting more and more popular, and I've been trying to make it more popular. But just to give a quick summary, so the core terms, so inside our system, there are core terms, the same way as in GHC, the same way as in Idris, essentially everywhere. This is a very standard thing to do. But here we say that core terms are viewed as immutable program code during elaboration. And the core terms can be evaluated into semantic values. And the semantic values are a bit richer. They contain more information. And such that all kinds of expensive computations can be implemented using on these kind of semantic values, most notably reductions, conversion, checking, and unification. And this is also the way Idris 2 works. And then there is a quotation operation which converts these semantic values back to terms. So in the end, the elaboration has to produce something which is a core term. So then we have to grab a bunch of values and convert them back to terms to be able to fill some holes in core terms. So this is kind of an interleaving of normalization by evaluation and elaboration, and I think this originates from theory Cocon. Yeah, so let's try to do some kind of super minimal normalization by evaluation with top-level unfolding control. And probably I will skip over some details, but maybe just let's do a quick overview. So we have terms. This is just essentially untyped lambda calculus extended with the notion of top-level variables. So there's some kind of implicit top-level scope with a bunch of definitions, and then we have top vars pointing into that, and the local vars are just the local bound variables of lambda calculus. But then we have the semantic values, and in the values, we have the neutrals. So the neutrals are just a local bound variable being applied to a list of things. So this spine is just a list of values. And this is just a stack application. So if you try to evaluate a bound variable, then it can get applied to a bunch of things. But of course, this evaluation cannot proceed further because it's being blocked by a variable. And then we have lambdas. So you can see that the body of the lambda is a function from value to value. And I'm writing some kind of pseudo Haskell here. You might even see the strict progba, which is a feature of pseudo Haskell. So this is a bit like we are working in strict Haskell, but the point is that almost everything is strict here, but at some places laziness will be very important. So we have closures for lambdas. And then we have this extra thing, which I call V unfold. And this is a delayed choice about definition unfolding. So this part of this data constructor, this top name and a spine, is a top definition, and the unfolding of this top definition is being delayed, but then it can get applied to a bunch of function arguments. So this is this spine. And the other thing, which is explicitly marked as being lazy, is the result of performing the unfolding and computing it until the next head construction in this language. So this is very similar to what was mentioned in Idris 2, but I'm not sure I fully understand it. There might actually be some difference between this implementation and that one. And then we can write an evaluator. And so we have an environment, we have a term, we do a case on the term. If it's a top-level variable, then we return this delayed unfolding choice. So we just return the top-level name together with an empty spine of applications, and then we lazily perform this top-level lookup. If we have a local variable, we just do a local lookup. So there's some kind of implicit top-level context here that I'm not writing here. If we have an application, we do some kind of semantic application, essentially an application of values to values. If we have a lambda, I just return a closure. And so the interesting part here is this value application, because, okay, so I'm trying to apply a value to a value. If the value is actually a lambda, I just call the function closure. If it is an unfolding, I just return a new unfolding such that I perform the application on both branches of this unfolding decision. On one side, I just extend the spine with the argument. On the other side, I just create a new thunk, which recursively tries to perform this application operation on this value. So essentially what happens is that I am accumulating a bunch of thunks during evaluation, such that at any point, I am able to just choose one branch of this unfold or the other branch. But if I choose to look at both branches, computation will be, I would say, maximally shared between these two branches. So VNE, so this is a neutral value. So this is something which is being blocked by a bound variable. So if a computation is being blocked by a bound variable, there's nothing I can do. It just stays neutral forever. So this happens when I'm trying to evaluate expressions under a binder, for example, for a lambda binder. Okay. Okay, and then the other part of the story is going from values back to terms. And I call this operation quote. So, so maybe this is the more interesting part. I have essentially some supply of fresh variables, or I mean, I have some supply of free variables, and then I can use this to generate fresh variables. I have this Boolean, which is actually the unfolding option. So if the Boolean is true, I'm performing all unfoldings at this point. If it's false, I don't do any unfolding, and then I can go from a value to a TM. So if I have a neutral value, I can essentially just generate a nested application as a term from it, because the neutral value just represents an iterated application to a bound variable. If I have a lambda, I can grab a fresh variable, and then I can create a term for the body of the lambda, and then recursively proceed. And if I have an unfolding, then I can do this if only unfolding. So if I'm doing unfolding, I'm just converting the unfolded result to something. And if I'm not doing the unfolding, then I'm just converting this part of this value into an iterated application. Okay, I know maybe there are some questions related to this. Yeah?
Maybe I'm just misreading this, but your v-unfold case says if unfold, then call quote again with ends unfold. Yes. Oh, okay, there's an extra v. That's what's different v. Okay, got it.
There's a v here. So this v is essentially the result of performing a top-level unfolding, and this is the result of not performing a top-level unfolding. If unfolding, I'm recursively quoting this result. Otherwise, I'm just creating the term and returning that.
I've kind of lost track of where you go from when you call eval and when you call quote. You define them both, and you can sort of go to and fro. But I've lost track of when you would call either.
I mean, we would call these, so I guess this is out of the scope of this talk, but in this style of elaboration, the eval and the quote is completely interleaved with the elaboration. So, for example, when we do a bidirectional type checking, sometimes we might want to know whether a checking type is a function type. And at that point, we need to have a value for the checking type and then match on it to see whether it is a function type or not. And that would be, okay, maybe it's not such a good example, but a very good example for calling this quote is when we solve a meta variable, because unification problem has values on both sides. And if we have a meta variable on one side and then a value on the other side, we need to convert the value to a term, because we can only insert a term into the elaboration output. But the whole reason of doing this is essentially for dependent type checking, we need to do conversion and we need to do reductions and evaluations for arbitrary functional programs, because we have a dependently typed language. And we don't want to do some kind of naive substitution or some kind of slow stuff to do these reductions and these conversions. So we want to use essentially some kind of efficient abstract machine, which looks very much like a functional language interpreter. And we don't want to do expensive computation on terms ever. We want to evaluate terms into some semantic runtime objects. And then when we actually need the terms, we want to convert back from the runtime object. I'm not sure how clear that is.
So can I just ask a follow-up, which is, you began with a slide about nested tuples and blah. How does that connect with what you're just telling us now?
So this is kind of a very basic setup, but the way that this could connect, and actually it does, I mean, in some of the, I'm not sure, maybe this would also work in the new Idris too, as well. You can try. So So the way that this would work, so what I showed is kind of not sufficient to handle this case, but it's just kind of part of the basic infrastructure. But the idea is that we want to view meta variable solutions as definitions, which we don't necessarily want to unfold, because if we unfold all of the meta solutions, we get the exponential blow-up. But if we don't always unfold them, we can just get a linear number of small size definitions, in which case this example can be still linear time elaborated. So we would just say that let some type equals bool per bool, another type equals pair of previous definition, and so on. So. Okay. Yeah. Yeah. I don't think anything like that comes up in this talk. So the two branches that we can take yield convertible values and terms. So they are always convertible. They live in the same environment as well. Okay. Okay, so yeah, probably I will need to speed up. But then so an additional detail is that usually, so this was just a basic infrastructure, but usually we need to work with pairs of such values during elaboration and unification and conversion checking, because so these pairs of values, because sometimes we kind of force some values to weak at normal form, but when we do that, we do not want to forget where we started from, because where we started from can be still very useful to present to the users and to quote into terms which are probably smaller than the unfolded versions. So that's why in the bidirectional elaboration algorithm, we have these gval is just a pair of values. And essentially, we have checking, inference, and unification. And here, the checking type is actually just a pair of values. And when we do inference, we are also returning such a pair of values. And then in unification, the unification also works in pairs of values. So for the left-hand side, we have a pair of values for the right-hand side. Because, for example, I have a meta variable on the left-hand side, and I have something on the right-hand side, and I want to do a meta solution. It might happen. I always want to be able to grab the least unfolded value, because then the least unfolded value usually will be the smallest. Okay, I'm not sure how clear it is, but you can see that this weak normal forcing is quite simple. So we are just peeling off these unfolding nodes until we get something which is not an unfolding, but then we are losing information about some unfolding. So that's why we want to hold on to a least unfolded and the most unfolded version of values. And so this is an example for when we actually do want to unfold something during elaboration. So you can see here that elaboration input is just some map, some call to two map functions in some kind of Agda-like syntax. And the way that Agda works is that these map functions have some implicit arguments, and the implicit arguments will be top-level definitions. So they will be top-level functions, and the top-level functions all take all bound variables in the scope as argument, and this is called contextual meta variable, and this is used in Lean, I guess in IDRIS as well, and Agda. So GHC is the system where this is not being used. I guess in OCaml, this is also not being used. Yeah, so we get a bunch of top-level functions for all the meta variables, and then the elaboration output, if we don't do any kind of unfolding or inlining or optimization on this particular piece of code, we just get a bunch of quite ugly function applications here in the output. And I do know that in Coq there is like some optimization to compress these application spines. But in general, there is still a bit of overhead when we when we keep around these meta solutions. So what we really want to have is that because all of these meta solutions are completely trivial, we want to inline them. So we just inline them, and then we get some desired output, which looks pretty nice. And so this is the idea that when we are doing this elaboration of, I guess, dependently typed languages, we want to do some kind of early core optimization. And the two principles is that the user-written code should be preserved by elaboration, but the code which comes from elaboration or tactics should be optimized, ideally soon after it is being produced, because we do not want to hold on to lots of garbage, and we do not want to compute with terms which are kind of poor quality. But in my experience, a very simple and fast optimizations like very basic inlining and let motion and maybe eta reductions make a big difference. So for example, what I implemented in some system is that we take some kind of top level binding block, like binding group, we elaborate it, we get a bunch of metas, but immediately after that, we do an inlining and optimization pass so that the next thing that we elaborate can already refer back to the nice looking code. And I have found that this is also super useful for getting a human readable elaboration output during elaboration. And this is a major issue in Agda right now. So because in Agda, elaboration does this in a very naive way. So pretty much every meta solution is unfolded by default. We get a huge garbage as output such that no one wants to read it. But because no one wants to read it, no one wants to develop and maintain pretty printing for it. And because we don't have a good pretty printing for it, no one even knows anymore what is in the elaboration output. So recently there were some issues when it turned out that Agda developers thought that some things are in the interfaces of modules, but the reality turned out to be quite different. So I think it's a very good kind of rule of thumb is that one of the most important points of this optimization is to make your elaboration output human readable. Okay, and I guess I don't really have time for anything else. I have a bunch of other things. Maybe just one very, very kind of a fun thing. So this is kind of a small and fun thing to mention at the very end. So what's wrong with this definition in Agda and elsewhere? We just have a record, and then we just have the fields. So this is just a record definition. We have like we have to give definitions to each field. So what's the issue with this? And I think Agda users probably know that this pattern can behave very badly in type checking. Okay, so I guess it's already spoiler. Yeah. So the issue is that there's no way to share field definitions in elaboration. So if there's a meta variable in big defn, in the solution of that meta variable, all of these previous things must be unfolded because there's just no way to refer to them as a definition whatsoever. And I think the only way to actually fix this is to say that the construction of a record brings into scope each field name as a definition, which is kind of weird, but I don't see any other way to do it. So the veteran Agda users know that they have to use copatterns instead of this, because the copatterns actually require an elaboration to a top-level copattern matching definition, and it also makes it lazier to perform all these unfoldings, and then the performance can be actually fixed. But I think users should be able to actually write a local inlined record definition. I think it's a good feature to have. Okay, so and there are a bunch of related implementations. So like implementations which take some part of these features that I mentioned and implement them in some way. And so I also put this edges 2 here. Thank you.
So I think we have time for another question or two.
So I understand what you're proposing to keep the unfolded thing around and not unfold things too eagerly. So what I'm wondering is, why do you need to keep this distinction between the semantic domain and the syntactic domain? Can't you just do everything in the same domain and just use sharing everywhere? And when you reconstruct an actual program term, you can reinsert a where clause, right, where you put all the sharing definitions.
Mm-hmm. So you say maybe, for example, let's just use maybe terms all the time?
Yeah, and use variables that preserve all the sharing, which is the normal thing to do when you implement a unifier. You keep all the sharing, right?
So I think there's a reason. So if you look at like all of the functional programming language implementations like OCaml and Haskell, the way that the programs are being compiled and executed is not by doing substitution on terms.
Yeah.
So because that's horribly slow. So the idea here is almost exactly the same, is that instead of doing substitution on terms, we have abstract machines with some closures and environment, and then we can potentially do a bytecode or machine code evaluation. Like for example, the Coq VM also uses this bytecode evaluation with closures, and that's way, way faster than trying to do substitution on terms. And I guess that's the basic idea.
Okay, I'm not proposing to do substitution on terms. I'm proposing to keep all the sharing you have. When you have a variable and it needs to be unified with something, you just keep track of this unification and you don't do a substitution, right? And then whenever you look back at this variable, you can look up the fact that it's been substituted.
I mean, so we need to run essentially arbitrary higher order programs during dependent type checking. So I don't see an easy way to make this proposal work with terms, and even if we try to do this sharing.
All right.
In the values, you had this v-unfold case, and later you again work with these glued values. Can you explain again why you need both?
So this stuff. So for example, it can happen. So we just want to do unification, and one of these values is actually something which is a nesting of v-unfolds, like potentially a very, very deep nesting of v-unfolds. And then the way that we implement this unification algorithm is that maybe we force one side and we look at like, is this a meta variable? And if this is a meta variable, we want to solve it with the other side. But then, if we are doing this recursively, at any point we need to hold onto the most forced version when we peeled off all the unfolds, but we also need to hold onto the version which has not been unfolded, because if we just lose track of the least unfolded version of the value, then we lose this opportunity to generate like sharing in terms. I'm not sure if that's clear.
Yeah, I think so.
Okay.
Okay, so we're pretty much out of time. So thank you very much, Andras. So the last talk, I believe, is remote, so I'm looking forward to finding out how this works. Implementing separation logic using an SMT-backed frame rule.
So I don't know anything about that. Someone else. Okay.
Please, I need some signal that I'm heard.
Oh, he's there.
Hello?
Hello, can you hear us?
Yes, can you hear me?
So we cannot hear you, but we're working out the audio here. 1 second. You could write in the chat. It's less than ideal. Can you try to say something again?
Hello, 1, 2, 3. One, two, three, 1, 2, 3. 1, 2, 3, 4, 5, 6, 8, 10, 11, 12, 13, 14, 15.
Well, he could hear us before.
20.
Can you hear us still?
Yes.
You can hear us, we can't hear you. You can hear us, but we can't hear you.
Okay, can you say something again? Ah. Thank you very much. We can hear you now.
Hey.
Sorry about the delay.
No, that's okay. Okay, I think I can begin. Good.
I believe you can begin, yes.
Okay. Hello, my name is Kirko, and I want to talk about how we implement the separation logic by representing triangle application as this work. This work is done in the context of finite type system for Java, called Java, which is with separation logic. But the talk itself is not about liquid Java precisely, but about things that found in our work. So there are many things, many tools which allow a programmer to reason about code with some kind of special logic, and some of them are compiled by synthesis solvers like pipers, notebook, stuff. And from a certain point of view, there are some applications they look pretty much similar. And the code analysis which they perform needs some logical statements here. And these logical statements are transferred to first-order logic, is then fed to synthesis solver, which provides feedback with errors and warning. But logic statements are not created equally, and some of them are easily translated to first-order logic, some not so much. And the spatial logic falls into not so much category. If one gives a closer look to the tools that I mentioned, it will become clear that each of them pays a lot of attention to how this translation is made, which I showed here. And it is important part of the design with no obvious way to reuse it. But there is another way. While limited and underused, it makes it possible to leverage the translation of separation logic to SMT solver. And only mainstream SMT solver which supports separation logic is specified. And to the best of our knowledge, there is no tool that utilizes this feature. And comparing with C3, for example, which does not support separation logic at all. So now I will dive into some more details, and along the way I will tell how to apply the translation. So if you have any questions, you can interrupt me and ask them, or you can save them to the end. So at first I will start with describing liquid Java and a bit of separation logic and why we want them together. And I will talk about the algorithm to translate frame rule to SMT solver queries, which for the solver which understands separation logic. And then I will talk about limitations of this approach and testing benchmarks we perform. So, liquid Java. Oh, no. Are there any questions so far? Liquid types for Java allow to add predicates to restrict values on built-in Java types. So, for example, here the refinement allows only the doubles which are greater than 0, and the main goal of this tool is to leverage some errors which are usually runtime errors to compile back. Like here, we can check that the value we are providing for square root is indeed greater than 0. There are implementations not only for Java, but also for Haskell, C, and some other languages. Haskell's one of the most mature ones. Then I need to talk about separation logic. Not all of it, but rather about things that are relevant to this talk. So separation logic is an extension of our logic, and it brings the means of reasoning about heap, and then tries to solve the mixed problem of our logic with the lack of modularity. First, we have ownership predicate that describes the singleton heap. Here it's a pointer P pointing to some memory cell that in this example contains fun. Then there is a way to join these descriptions, heap descriptions together via separating conjunction. And the idea is that it is possible to separate the memory, the heap, in two parts, which are disjoint, for which A holds and B holds respectively. And then there is a frame rule which allows to reason about code independently of the context. So we can reason about, for example, about some function, and then reuse it in a large context, relating our knowledge to the context on the call set. We are adding separation logic to liquid Java because before this extension, liquid Java allowed only reasoning about reference types or about primitive types because of Alessi problem. Then we discovered that it is possible to, with the fragment of separation logic we implemented, it is possible to express simple resource allocation consumptions, mainly files. Then it is possible to make API for interface data structures like link, list, and binary search trees, and then to detect the usage of variables, for example, spend streams and iterators. We couldn't implement the whole separation logic because the whole separation logic is undecidable. So we restricted it to a small fragment by saying that it is only permitted to have our logical context, like as we implemented our separation logic part for Java symbolic execution, it has had state. So this logical state of our symbolic execution procedure can be in the form of Boolean context conjoined with a simple heap description. So no nested pure Boolean statements inside, only points to predicates and separating conjunction. Then the Java itself provides simplification. As there is no referencing operator, we can replace all values with 5 constants, which represent initialized memory. And the final restriction is that 5 supports grass fragment of separation logic, which, for example, disallows quantifiers inside predicates, which restricts the usage of recursive predicate. Basically, you can't have them like from a box. Let me show the simple example of how this symbolic procedure is reasoning about code. But first, we need to familiarize you with the heap precondition and post-condition syntax. So here you can see function foo, which expects some argument x, and the precondition means that it should be x, which is just initialized. Then the post condition is that this function spits some other variable which is also initialized, but as x is locked in the output, x is consumed. Then there is new. New is not a function, but can be treated as one, and it does not expect anything, so empty heap as a requirement, and then it spits out some initialized memory, which is written in post condition. As pure Boolean part and the heap description are disjoint in this fragment of separation logic, we can split the annotations also, so one can add here the pure Boolean annotation and will work just fine. So as a symbolic execution, one starts with the empty heap, and then applies framework to add new pointers to the heap. Then the second new, it also applies framework and it adds the second pointer to the heap. And then, interesting part, one needs to consume A, but as pure Boolean context here it is discarded for brevity, but it actually can be that it's not A here, but some other pointer which is equal to A. So one needs to determine which pointers are from precondition and which one are from the rest of the heap. And this is the core of SMT backframe application. Some magic happens here, which I will describe later, and then the old pointers are consumed, the pointers in the rest of the heap are attached, and the new pointers are appended to the heap description. So how we should go with the implementation of this heap disjointment to the post precondition and the rest of the heap. So at first we need to check if the precondition is consumable from the heap, which is described by the state of symbolic execution. And then we need to split our heap to 2 parts, to the precondition and to frame the rest of the heap, and then to replace the precondition with a post condition. And the key part which will help us to implement this is that to make the heap description that contains at least A, we can append start root to it. So for example, if you want to say that our heap contains pointer x pointer to some initialized memory and something else, we just write this. So it's a good place to ask questions if you have any.
Yes, but not yet. Okay, that was a yes, but not yet. So carry on, Eric.
I can hear you. Ask the question.
I have a short question if you want a question. How do we know that we need to check pre? So how do we know a priori that it's pre that we want to check and not something else in the whole pre times frame that we have?
We're arriving, if I understood your question correctly, we're arriving with some heap. And we need to check if it's possible to consume the precondition.
So the precondition is given to us from the function call, right?
Yes.
Okay, you don't have to guess how to split the heap.
Yes, but we can check if, we can't, if we don't know which pointers, we know which pointers are equal to which from the Boolean context, but we need to, we need to match pointers from the precondition, which we know, to the pointers in the heap description, which with which we came here. Does it make sense?
He's nodding. Nodding. Yes.
Okay, I didn't hear the last part, so I will carry on. Okay, so the check of the precondition is relatively simple. We're sending the SMT solver negation, because the SMT solver checks for its viability. The query, if you want to check if it holds for every variable which is there. So we're joining the Boolean context with the heap obtain the full context, and then we are checking if the our full context implies the precondition and maybe something else. And if one plays a closed loop here, it is also can be treated as, is it possible to consume precondition, which you know from the notations, from the context we came here with. So it is it makes sense to call it the consume predicate. Then we need to apply post condition. We're starting with the empty rest of the heap. We're iterating through each pointer and checking if the pointer which we're iterating with and precondition are consumable from the heap we're arriving with. And the idea is that it is only consumable if it's not duplicated here. And if it's consumable, we are adding to the rest of the heap. And if it's not consumable, it means that it's already contained in precondition. Then we're appending the post condition to the frame, and the post condition replacement is complete. So this algorithm brings the overhaul of linear amount of SMT queries with respect to the symbolic description size, and the later benchmark the Java to see if it is forbids the interactive value. So the limitations of this approach, the main two are that we tested on the consequential program and symbolic execution setup, and the most game-breaking ones is that it is very hard to obtain, for example, fractional permissions with this approach, because one need to modify the logic that is understood by CVC5. The other limitations are that we chose to test this solution with very small subset of separation logic, because we just wanted to see if it's possible. And then it also assumes that it is possible to iterate over description over the pointers in the heap description. So we performed some testing benchmarks. We measured the compile time increase, because the liquid Java is plugin for Java compiler, and the increase of 30% does not forbid the interactive value liquid Java is made for. there is no formal proof of the algorithm above, we just tested it with a bunch of annotated parts of the Java. We applied this algorithm in 3 instances. With function invocations, as I talked about, then the assignments, because if one assign one pointer to another, it might be possible that the heap descriptions no longer hold, and one needs to go through in the same manner as for function invocations to reassemble the heap that is still hold for the after the assignment. And then branching. Ifs are splitting programs into parts, and then one needs to merge the heap descriptions in the end of each. This also can be done by the algorithm Capra. We are to the conclusion. And the main benefit of this approach is that it completely bypasses the right translation to separation logic. The first order logic by hand. It is bound neither to Java nor to liquid types, and is relatively easy to implement comparing with the manual implementation of this translation. Then there is parse of A. This approach supports only a small subset of separation logic. It is also hard constrained by logic understood by CVC5, and to extend it, one need to extend the CVC5 itself. So our implementation is available here. If one wants to check out the best place to start test. I'm happy to hear your questions.
Okay, let's thank Kirill. And I believe there are questions. We'll pass the mic around.
Hi, thanks for the talk. So you mentioned that you were looking only at sequential programs, but I'm curious if you, so separation logic is being extended by Hearn to concurrent separation logic so that you can reason about concurrent programs and maybe verify concurrent programs. Have you looked into concurrent separation logic support?
As you can see here, it was only tested for sequential programs. It was just not enough time to see if it's possible to support parallel programs. But I believe in the symbolic execution step it is possible. It is just not explored for liquid Java because of the time end. We just
another question. You said that a limitation is that if you want to add more, you need to extend CVC5. Have you looked at how hard this actually is? Because maybe it's not so hard.
Like the main problem with extending CVC5 in the point of separation logic is that it is very underused. So while we were working on this project, we found the bug in separation logic in CVC5, and it was fixed almost immediately because it was relatively simple and very apparent bug. Just nobody uses this part of CVC5, and to extend it, one needs to write C code. I tried to look into the code of CVC5, and it doesn't look like it.
Okay, any final questions? Doesn't look like it, and we're about out of time anyway. So thank you very much for your talk, and yeah. I think we're handing over to Richard for some closing comments, yes?
I promise this will be very quick. If we can get, oh no, it changed size. I can fix that. Can we see that? Yes. Is this the whole? Yeah. Yes, it is. Okay. Thanks everyone for coming to WITS. I just wanted to take a moment to thank the program committee here who are up on the screen. So thanks to them who helped us select this program today. If we could. And thanks to you all for coming. Expect to see us again at POPL next year in Denver. So long.
And since I have a mic, let's thank Richard for putting this all together.